Hello, everyone. I always wanted to say good morning, everyone, but it's just morning in our place. If anyone from the speakers of the next session want to try sharing a screen or anything like that, we can do it at any time. One moment, where am I here?
Hi, Anna, can I try my...
Yeah, one moment, I'll just stop sharing. Oh no, I don't look like... I don't share anymore. Wonderful. Okay. Sorry, morning here. Yeah, please do.
So, can you see the screen?
Yes, in the proper
presentation
mode.
Okay, thank you.
No worries.
Anna, can I try next?
Yeah, sure.
Yeah, cool. Are you seeing the presentation mode?
Straight away.
All right. Okay, perfect.
Yep, looks good. Looks good, sounds good.
Thanks.
Can I try sharing my screen as well?
Go for it.
Yeah. So can you see my slides?
Yep. By the way,
my cursor as well?
Yes. By the way, hi. Because I'm recognizing your name, and I'm really definitely on a few papers recently sent, well, past few years by a student, by Min Hyun.
Yeah, I mean, nice to meet you. I think we met sometimes
we did.
At ICRA a few years ago when I visited.
Oh my God, I am so sorry. Are you sure?
Yeah, I was visiting Min Hyun with Jacinta Delays and others. So, but
I don't recognize your face.
Probably 4 years ago. So
I'm sorry.
Nice to see you again. Anyway.
Yeah, nice to see you again. I think that's the way to say it.
Thanks.
Good morning.
Morning.
Should I test my slides super
quick?
Yep.
Anyone can jump in and test it. Actually, I should check. Right. I tested things. Hang on. Oh, yep. This was straightforward.
Looks good.
Yep.
All right.
May I test my slides?
Absolutely, yeah. You're first, Catherine. In the
so
session
not a bad idea to check in that case.
Yeah.
Does that work?
Straight away. Yeah.
Can you tell me, can you see my cursor?
It's big. Yes.
Or not?
Yes, I can, and it's very big, which is probably good.
I made it extra big specially, so.
It is. So it is very easily seen, yeah.
Lovely, lovely. Thank you very much. Right, I will now stop sharing.
What else we have here? So I have to... Oh, Beanie, did I see? Beanie. I'm sorry, I don't know how to pronounce your name.
Beanie.
Beanie. Okay, I was good the first time. Do you want to try it out?
I just tried it out in the beginning.
Oh.
Yeah.
Did I miss it? No, you did. Sorry, I'm just half asleep. I'm not sharing the session. Frank is. So that's probably good. I'm so sorry. I'll take you off.
I'm also not the most awake.
More than I am.
I thought it was really kind of you to give the Europeans the talks at the start of your day. I don't think I'd have wanted to start speaking at midnight here.
Yeah. Well, it was Amy Miroszewski that was organizing it. So like the setting up the program, and I think she had to sometimes mix the subject because of the time zones, but yeah.
Incidentally, I presume that you can hear me clearly.
Absolutely. Well, yes.
Good.
I'm just saying.
Because there was one speaker yesterday who I think was putting their hands down on their laptop speakers.
Oh, that's what it
Um,
was.
It was just coming and going a bit. I mean, I think in the enthusiasm of delivering the talk, but
Okay, because I think I might have heard that because then I was trying to see who is not muted, but everyone was apart from the speaker. So yeah, that will make sense. No, but I can see hear you very well. Regina does not. Who else do we have? Victoria Hines. Okay. Frank, you're starting in like 8 minutes or something, right? Is that
Yeah.
you who's taking it over first?
I think so. I sent Steve an email. He knows what I'm planning to do.
Okay, good. Could you just actually no? So okay, I have to tell it to Stephen. He's the last one. Just to make sure that people wait after the very last talk. So we will try to do another photo. But okay, I'll tell that to Stephen. Everything else, other than that, I'll leave it to you. I can leave it to you now if you'd like to.
But you can are you gonna open? Oops.
No, it's you.
I open it.
Yeah.
Okay.
Yeah, I think everyone heard enough from me by now.
Right. I can mention it.
Oh, actually, if Stephen is finishing the session, maybe Stephen can do that. Or you can mention it and then Stephen can mention it again. I see Steve is online.
Yep,
Yeah.
I'm here.
And he acknowledged my email.
Yep.
I'll make you co-host. And Steve, so did you hear that I told Frank if you could mention when you're chairing just before you let people go for them to hang around so we can take another group photo.
Right, that's before the break, at the beginning of the break.
At the beginning of the break, I think that's the best one to do, yeah.
Okay,
Cool, thank you.
I will try and remember that.
I might try, if I remember, I might message you, but if you're sharing that, you may still miss it. Okay, and Nick. Oh, Heinz. Heinz, I see that you're online. Would you like to test your screen sharing? Oh, there you go. You're muted if you're speaking.
Okay, I'm sharing screen.
Right now?
Yes.
No. Oh, yes. Okay, maybe that was just a delay.
Well, you will. I'm opening the PowerPoint. Go to the first slide. Can you see it? It's not yet in full screen mode. Can you see something?
I think there's a delay. Yeah, now we can see that. Yeah.
Okay, now I go to full screen. And does it appear?
Oh, so maybe it's Socorro that is just slow.
Yeah.
Yes.
Okay. So the next slide, does it advance?
Yes.
You'll recognize this from yesterday. I took the liberty to take a screenshot and make some comments on that.
That's what it is. Okay. Yes, I do.
Stop share. So fine.
Thank you.
I'm a wolf now.
Sorry, Rick.
Yep, you're a Canadian wolf.
Not you. I'm quoting you for the wolves.
Wolves.
Okay, so I'm feeling better now. But Hans, I mean, I don't know, were you ever involved in this trying to get 2 hours of time?
Oh yes, I was. I'm explaining that in my slide.
Oh, okay.
I got the
'Cause-
time from 2 to 4 a.m. in the morning.
Yeah,
and
I mean, it was truly an amazing social phenomenon watching or actually participating in that business.
Yes. I hope I didn't offend Fraser when I mentioned that I didn't remember you to clutter the computers, but people were saying that Fraser was sending batch jobs from home.
Well, I don't remember that one actually, but
That would be amazing in those days.
Yes. Mhm.
you could, there was a batch option for apes. I guess nobody is probably still there, but I don't think anybody uses it now.
Oh yeah, Ananda, did you want to give it a shot at screen sharing?
Yes, please. Thank you. I was not interested in interrupting them.
Yeah, I mean,
Can you see my screen?
Screen, yep.
In presentation mode?
Yep.
It's fine.
Yep.
You can see my cursor as well.
Yes.
Great. We are done.
Fantastic.
Thank you.
Yeah, thank you. I think so. We have 2 more minutes. Maybe I should leave it at this stage. Frank, it's all yours.
We'll give it a minute while people are still trickling in, but then we'll get started. All right. We don't want to delay our start too much, and we'll let people trickle in. Welcome to the third and last day of this science program for the VLA 40th. And I'll be chairing the first half of this session, and Steve Myers will take over the second half. And most of the day will be devoted to extragalactic talks. So we have reached the extragalactic universe. And and so the first speaker is Catherine Blundell. It's an invited talk. So I'll give a 5-minute warning before. And she'll be talking about the VLA and the jet age. Go ahead.
Thank you very much indeed, Frank. Well, I will just share my slides, I hope. And the title of my talk today is The VLA and the Jet Age. And it's quite a story. Indeed, you might even call it a Southwest Side story. Now, for those of you who aren't so familiar with Leonard Bernstein's musical, perhaps I can remind you of some of the salient features. Leonard Bernstein's musical is set in New York. Ours today, in honor of the VLA's 40th anniversary, is of course set in New Mexico. In the West Side Story, Bernstein's original musical, it's about the jets and the sharks. But today I'm going to be talking about jets and shocks. The leader of the jets is called Tony, and the director of NRAO is of course one Tony Beasley. In Bernstein's musical, the leader Tony falls in love with Maria and becomes obsessed with Maria. In our story, it's the NG VLA that takes that place. So the VLA and the jet age. Why do I contend that the VLA has absolutely propelled the astrophysics community into the jet age? I think the VLA demonstrated, way beyond the iconic Cygnus A, the ubiquity of jets, meaning the fact there are jets everywhere. And that paved the way for us beginning to understand the importance of jets. Why do I say jets are important? Well, they're certainly not just for decoration. They tell us about how you can efficiently extract energy from a black hole and an accretion disk. And as I say, this happens all over space. You can transport energy, matter, and enthalpy to large distances from the black hole. Large here meaning a megaparsec. They are beginning to be increasingly acknowledged as important in terms of radio mode feedback, also called AGN feedback. Lots of people are increasingly saying in their in their simulations of structure formation that AGN feedback needs to be accounted for. All too often thus far, I fear, the AGN physics is rather missing from that AGN feedback acknowledgement. Jets give rise to locations in space where we can attain the acceleration of the highest energy particles. I don't have time to talk about cosmic rays today, but they are nonetheless responsible for that. They are a key process in the evolution of massive elliptical galaxies and clusters. Jets ionize and heat hydrogen and thereby suppress star formation. So it's impossible to imagine modern astrophysics without appreciating and acknowledging the importance of jets. And I find it impossible to see how that would have come about without the VLA. Besides their intrinsic astrophysical interest, jets give rise to so much interesting physics, and it's just an absolute joy to study that. So I'm showing here Rick Perley's beautiful image of Cygnus A, which so strikingly demonstrates the centrality of jets to the classical double radio galaxies and quasars. I hope we all agree that beautiful images such as this owe a great deal to the magnificent mathematical mind of Eric Bryson. And I hope you will all agree with me that the whole radio community is greatly in Eric's debt. If you look in closely at this sort of image, then you will see that in fact the jets are not straight. Catherine Steenbrugger and I studied this some years ago, and we fit a jet precession model developed by Bob Jelming in the early 1980s for the Cygnus A jet, finding that you can fit a precession model with a precession period of about 250,000 years, with an opening angle of about 1.5 degrees, for surprisingly slow speeds in the context of relativistic jets. We fit a speed of less than about half of c. And so this is one of many indicators that jets do precess. They change their orientation in space. Here is another, this one looking at 3C294, which is showing as green contours the 1.4 gigahertz emission, and as blue contours 8 gigahertz emission, superimposed on color scale from Chandra X-rays. Chandra X-rays, X-rays which arise from inverse Compton scattered emission, live for a whole lot longer than radiosynchrotron. So when we see extended X-rays in association with radio jets, we're able to look back in time. We can use spectral binocular vision to gain a sense of where the jet was pointing previously, delineated by the X-ray emission, and where the jet is pointed now, denoted by the radio emission. One of the many wonderful things about the VLA is that it is not a spectrally chauvinist instrument. The VLA has fabulous complementarity with X-rays, with optical spectroscopy, and with cosmic rays. I want to talk briefly about two X-ray phenomena associated with the extra nuclear classical double FR2 radio galaxies. There's compact emission and there's extended emission, as I've already shown you. It's the compact emission that tells us about shocks and particle acceleration. It's the extended emission that gives rise to that relic synchrotron plasma that I was just indicating, the plasma that arises as X-rays from the inverse Compton scattering of CMB photons by the relic synchrotron plasma. Let me show you this beautiful giant radio quasar, 4C74.26. This, if you zoom into the southern hotspot here with both Merlin and Chandra, blue contours are Merlin radio emission, the green on the left is VLA, and the red is Chandra, then you can see two very distinct shocks. I'd like to emphasize the size scales here. Over a megaparsec for that VLA structure shown in green at 1.4 gigahertz. Even the shocks itself, the shock structure itself, which remember is a zoom in of the southern hotspot, is over 20 kiloparsecs in extent. For this audience, you might prefer to appreciate the unit of the number of M87s that you can squash in there, with apologies to Fraser Owen for using his exquisite image of M87 in this gratuitous and frivolous way. Back to this giant radio quasar, 4C74.26. It is unusually nearby, it is unusually large. And as I've shown you, that southern hotspot contains two very different shock structures at the X-rays. We can only discern it because it's unusually nearby and unusually large. The first one is X-ray synchrotron, which is where the jet first shocks. As plasma flows out of that, it fades, but then it shocks more weakly on the intergalactic medium, giving us a radio synchrotron shock and X-ray inverse Compton. The first one is X-ray synchrotron, the second one is X-ray inverse Compton. This business of the X-ray peak being upstream, nearer to the nucleus than the radio shock, seen as the conventional hotspot, is characteristic of all jet hotspot shocks where these are resolvable. Another example, also a giant, 0.5 megaparsec in extent, shows here as green contours, which are at 8 gigahertz from the VLA, superimposed on a Chandra color scale. This shows the exact same feature, that you get gaps in the sense of the X-ray shocks are closer upstream to the nucleus, the radio shocks are further out, now with offsets of 35 kiloparsecs, not just 20 megaparsecs, as we had in the previous example. this particular case study is fascinating because the outside dangly bits beyond the hotspot speak of pre-existing magnetized plasma from relic radio lobes that have been re-energized by another episode of jet ejector. It's important to appreciate that when we do combine studies of radiosynchrotron with X-ray inverse Compton, I'm showing here a plot of the synchrotron energy spectrum, plotting Lorentz factor gamma of the synchrotron particles on the horizontal axis and the number of those particles on the vertical axis, purely for synchrotron emission. When we combine the two, this communicates to us that counterintuitively, the X-ray emission is telling us about the lower energy particles, the particles which had previously been excited as radiosynchrotron. The combination of these two is such a powerful tool in our toolkit. It is really wonderful to be able to use both. And we did just that in the case of another giant quasar, this one nearly a megaparsec at redshift 2, so a long way away. White contours now, VLA radio emission. Color scale is Chandra. And again, we see the same characteristic, radiosynchrotron further out, X-ray further closer in within those shock structures, and then closer in still, X-ray inverse Compton. The fact that we can get successive episodes of jet activity is something that's been identified through a slightly different study by a number of people, for example, Lakshmi Sarapelli, with this beautiful VLA image showing what we call a radio double-double. You can see, I hope, this inner small double planted in the center of this outermost, much larger double. And the thinking is that you get successive episodes of jet ejection, which of course you can only get if your radio telescope has resolution and it has sensitivity. So this is one way in which we can glean time resolution in the studies of radio galaxies and quasars. You can also see X-ray radio doubles, for example, in a paper by Tanmoy Lasker and co. The truly sensitive future technology might see double triples with 3 lots of jet episodes, so roll on the NG-VLA. But for the time being, the time resolution that we have in studying the jets in radio galaxies and in quasars comes by a combination of radio studies, X-ray studies, and of course, theoretical simulation. This paper, Philip Mox et al., demonstrates how the dashed lines here are showing you how the luminosity of a lobe falls with time. This is in mega years, while the solid line is showing you the X-ray luminosity. So the crossover of fading radio luminosity and rising X-ray luminosity in combination with astrophysical models gives us time resolution in the study of these beasts in the extragalactic universe. But what about the radio quietness of quasars? Some years ago, Steve Rawlings and I gave consideration to how to piece together this so-called FR1 classical double, FR2 classical double, FR1 centrally brightened radio sources. That criterion comes from a low radioluminosity division, which gives rise to an incredibly robust structural division, telling us about how the astrophysics of these lower jet power, higher jet power objects plays out. But if you start thinking at much higher luminosity frequencies in terms of radioluminosity, that's where the division for radio quiet and radio loud kicks in. Combine the two and you start to get a context for what we often call radio quiet quasars. There's a radio quiet quasar that Tony Beasley and Jeff Bicknell and I studied some years ago, which fits in that bottom left quadrant in the sort of FR1 radio quiet territory there. So how do the radio quiet quasars, those with rather weedy but nonetheless relativistic jets, fit into what we understand about radio-loud quasars. There's evidence from physical arguments that Steve Rawlings and I did in '99 that radiolobes must disappear on relatively rapid timescales, those timescales becoming more rapid the higher redshift we're talking about. With Carlo Nipotti, we drew a comparison between the duty cycle of intermittent jet activity in microquasars, the so-called flaring mode or radio mode, and the fraction of quasars that are radio loud. And this led us to conclude that radio loudness is something that depends on the epoch of observation of these quasars. It's important to appreciate that kinetic jet power, the bulk power going down a jet, being transported to vast distances away from the event horizon of the black hole, doesn't seem to be governed by jet speed. That example I briefly mentioned with Tony Beasley and Jeff Bicknell, that jet's relativistic, and yet it has very low jet power at present. Jet speed, in turn, does not seem to be a function of black hole mass. And you can get that just by comparing the microquasars with the quasars. Someone who's really pioneered precision jet physics is Robert Lang, together with Alan Bridle. And he has combined the resolution and the sensitivity and the polarimetric capability of the VLA to demonstrate exquisitely detailed analyses of the jet speeds and the magnetic field configurations within the jets of the low luminosity, low powered FR1s. This work is absolute poetry. Thank you. This work is absolute poetry. And if you're not familiar with this, then I recommend getting started with Lang and Bridle 2013. It's worth noting that the detailed analyses done by Robert Lang are not possible with the current VLA on the FR2s, the classical doubles, the distant quasars. We really need the NG VLA to do the same kinds of studies on the more distant FR2 classical double radio galaxies that Robert Lang and Alan Bridle have done in the nearby universe on the FR1s. Going back now to my point about the ubiquity of jets, I want to do a slight detour into optical spectroscopy. During lockdown, there were various explosions of classical novae, and I made studies of these with time-resolved optical spectroscopy, fitting their Balmer H alpha line to different dynamical components. And we found if you deconstruct these Balmer H alpha complexes, that you see components that are widely separated and fast now meaning not relativistic, but a few thousand kilometers a second, that precess in and out. These are jets of line-emitting hydrogen. How might these connect up with the synchrotron jets that we know and love in the context of black hole quasars? Well, in the case of another iconic object, SS433, much worked on by Bob Jelming years ago, this is a VLA image at 5 gigahertz of SS433. This image inspired me to do combined optical spectroscopy and radio studies of this beautiful microquasar. If you take optical spectra of this particular object at different epochs, then you find that the jet coming towards you gives you very blue shifted emission in terms of your hydrogen line, and the jet going away from you gives you very red shifted emission going away from you in the due to the hydrogen going away from you. If you piece together a whole succession of spectra, which I did, then you can predict what your jet trace ought to look like if you can lay your hands on a radio telescope. So Robert Lang and I did this with ALMA. That's the overlay of the image there. So we think we understand a lot about how the hydrogen emitting jet gives rise to the synchrotron emitting jet. Polarization was absolutely key here. There is a transition about 10 to the 14 meters away from the black hole where there is a sudden change in polarization angle, which is exactly where we expect the hydrogen emitting bolids to shock into one another and give you particle acceleration and hence synchrotron radio emission. We've got an image from the VLA for the exact same epoch as our ALMA image. Sadly, this image is still hindered by delay clunking, but it does show a lot more precession cycles than ALMA, and we look forward to being able to combine that in, and we really look forward to being able to study this beautiful object and many other microquasars with NGVLA in due course. So that's a very brief southwest side story of the VLA and the jet age. I hope you'll agree with me that the VLA has propelled us into the jet age, and it's even unthinkable, I feel, that the field of astrophysics could be anywhere near where it actually is without the immense contribution of the VLA and all the many people whose tenacity and whose ingenuity were critical to its success. Continued emphasis on resolution, on sensitivity, on polarization will mean that the NG-VLA becomes a worthy successor to the VLA. Thank you, Frank.
Great. Thank you, Catherine. That was excellent. So do we have any questions? We have had quite a bit of chatter going on in the chat, but no question, really. I don't see any hands up yet. I have, let me ask a question that is maybe not so much radio focused, but more on the X-ray side. I'm wondering about, from looking at the X-ray catalogs, I don't find that there are a lot of our known radio or well-known radio quasars are producing significant X-rays. And I'm wondering what that tells us about that there is there's no initial, we're missing the initial shock information. And we see the radio, so we see the history, but we don't see what happened before that. And so I was wondering why we don't see so many radio quasars in the X-rays.
I think that's a very interesting question, and I think it relates to the fact of simply the limitations of the sensitivity, the collecting area of Chandra. If you consider some of the other X-ray telescopes, for example, XMN Newton, that has nowhere near the resolution needed to discriminate between cluster emission, nuclear emission, and all the rest of it, to separate it out from that emission which is caused by the jets and shocks. So I think it underlines the fact that to make real advance in this area of astrophysics, you have to have resolution and you have to have sensitivity. We've done various calculations for what sort of Chandra time you would need to, say, consider quasars at the relatively moderate redshift of 2. And there's no existing generic sky survey in the X-rays that get you anywhere deep enough as you would need in order to make the kind of detections that I showed you in the subset of examples that I showed you in my talk. We've got up to about 10 now, but those only come from reasonably long integration times that are pointed and dedicated to studying those single targets. You don't get this kind of astrophysics with just, very shallow surveys.
Yeah, makes sense. All right. I don't see any questions here being raised. Just discussions. So I guess we'll move on. Thank you very much. All right, before we move on, I'll make one announcement that there will be another Zoom picture before the break. So this is just as a reminder now, since we're pretty much everybody has joined who wanted to join this session. And now we have our next speaker, Ananda Hota. And
Hi.
Yeah, we'll wait for the screen share. And
I will start the screen share.
Yeah, and he'll be talking about understanding beyond classical radio galaxies.
Can you see my screen?
Yes. The
And
floor is
my
yours.
audio, everything fine? Everything fine?
Yeah, everything is fine. Go ahead.
Thank you, Frank. Thank you, the organizing committee, for giving me this opportunity to speak our work. I'm Ananda Hota, UGC faculty at Center for Excellence in Basic Science, Mumbai, India. I'm a principal investigator of the Radioatom Astronomy Laboratory, member of ASI, IAU, SCA working groups, and PSSCG, etc. Title of my talk is Understanding Beyond Classical Radio Galaxies, Spiral Host SPECA, and NGC 3801 like AGN feedback caught in the act. Just before me, Catherine gave a wonderful introductory review, making my life a little bit easier for people who are new to understand. Let me move. I would basically focus on radio galaxies and connecting them to galaxy evolution that one can observe in detail. You all know that radio galaxies come in various shape and size, luminosity. They are all exotic, black hole forward. You have already heard this. But from my personal understanding, living in the different communities, that they don't really interact with the stellar content of the galaxy. So galaxy evolution, people who are looking at optical UV, IR, etc., they don't really find them impressive now. They are far out away from the galaxy. Looking at galaxies, they don't feel interacting there. Until the Chandra X-ray images started showing the X-ray cavities where the radio lobes are filling with the plasma. Sometimes with GMRT, one can see the old plasma filling, even if they are missing in the VLA, that is called radio ghost or ghost cavities or something. So then everybody started believing that yes, they are powerful enough and they are impacting the environment. So they must be impacting the gas falling on the galaxies as well. So everything falling in place now that when the AGN feedback models are proposed, the simulation started supporting them, observation started supporting them, they started explaining almost everything. Color magnitude diagram, M sigma relation, luminosity function, why the massive giant ellipticals are not growing in mass now, not growing star formation, not looking blue, and the cosmic star formation history density also falling fine. There is low, there is a cosmic noon or quasar era, radio galaxy era. They are all picking around redshift 1 and 2, and then falling again. Simulations started showing that during the merger, they blow away the gas content, and at the finally, the remnant doesn't have much gas to form star. And time to time, the radio jet also comes out, and the brightest cluster of galaxies at the center, the heats of the environment, and removes the gas. So this being the minority, they remain in the maintenance mode kind of feedback. Most things are happening from the quasar. So even the large, giant, powerful impact are insignificant. They are happening in the few of cases only, giant elliptical. So the small, where the radio jets are coming out in spiral galaxies like Seyfert galaxies, they are also insignificant. They are common, but they are insignificant as far as power is concerned. So then the connector comes between the giant elliptical, which are hosting the radio galaxies always, that they have a massive spiral, massive elliptical there because of the merger they have formed, and the massive spinning black hole there that can launch the massive jets. So the giant jets. Here the Laidlaw, Owens, and Keel, 1998, they spotted the first one, this one, that there is a disk galaxy, and there is a giant 100 kiloparsec size jet. For next 12 years, basically, people did not pay much attention because there is only one there until we spotted in 2011, the second one, that is a spiral host episodic radio galaxy. So SDSS can show the edge on disk as well as two episodes of radio lobes. One outer one is remnant-like, and the inner one is properly active. So let's see. Soon after the 2011 finding of ours, then Bakshi et al. Found in 2014 another one, then 2015 with Singh, 2015 with Mao and Mulke. Sorry, I don't know how to pronounce that. So there are roughly 6 of them. They are rare, but they are certainly there. There is a spiral arm. They are large as standard radio galaxies. Also, this particular case and SPECA, they are giant, like 1 megaparsec, 2 megaparsec size. So then where do they fit in there? Let's put everything in the perspective by putting the power versus linear size. What is happening? That the GPS and CSS and the FR2, powerful ones, small ones and big ones, and then the FR1, slightly less in luminosity, but relatively large in size, and the safer the galaxies, sub-KPC size, and then few of them are with 10 kiloparsec size kind of lobes, like teacup galaxies, etc. The speckle-like galaxies, spiral host large episodic galaxies, they are falling in this kind of a gap. It is very interesting to notice that whether are they actually filling this gap? Is it the observational gap actually? Or is kind of a evolutionary understanding that they are filling the gap? They are rare, but they are there. As I said, where do they connect? Because these spiral galaxies are merging and becoming the giant. Continuously, this episode must be happening. So slowly we are feeling that it's our personal feeling that Seyfert jets may be too low in energy, but they are actually too frequently happening, few million years. Radio galaxy is too giant, big hit probably, like that of a blacksmith or ironsmith, but they are powerful but too less frequent. Let's move ahead. So here is a chance to understand how to go forward from here. In feeling currently that although there are supporting evidences, there is no smoking on evidence of Bayesian feedback yet. What I mean is that there is no plasma or any kind of relic of the Aegean activity that has been spotted as a relic evidence, and with the time scale that since then the star formation should be declining. This cause and this should be the effect, merger imminent early type galaxy. There is one interesting point to note here that the citizen science process is spotted finding this kind of optical relic also of a quasar-echo, that is Hani's object. So this time scale of this thing is at 20 to 70,000 years, whereas in some cases the imminent relic lobe that one can find in radio galaxies, dead radio lobes rather, they can be several 100 million years. So there is an opportunity that we can track back the black hole's activity history even farther back in the history of the black hole activity. Here is one example that we have spotted, and this is 3801 caught in the act, a post-merger star forming early type merger imminent galaxy with an Aegean jet feedback. This looks like a star formation is long back over. And here ultraviolet, UV, ultraviolet stellar populations, this we have done radio jet at the very center within the stellar light emission block. So what is the story understanding of all this time scale, structure, dynamics, etc.? What we interpret from this all multi-organ survey is that two spiral galaxies may have merged, they have different orientation. At the end, they have formed a kinematic, a decoupled core-like thing. H1 observation, H alpha observation have given the kinematics there. And then they must have some kind of outflow there that has give them in the red color already. Then a couple of million years back, the radio jet has started. And it is creating a shock cell already seen in X-ray that is expanding at 850 km/s speed. This is going to affect the outer region, which is still forming star as seen in the UV. So in the next 10 million years, this galaxy is going to hit the outer star forming region. So the color that you see is the effect that the star formation is over, but the Aegean here, not the cause, the radio jet. So there could be, I wish there was another lobe that we can detect, but not the case. This is another case. The spiral galaxy, bar spiral galaxy, radio bubble at the very center, and this is 6764. Radio bubble one can see here with the VLA, of course, and the H alpha emission filaments one can see. With the Chandra, we could see the X-ray is filling up this bubble exactly nicely. And with modeling the precision of the central jet-like thing, we could interpret this way, that there are two episodes of star formation, 3 to 5 million years ago and 15 to 50 million years ago. And the radio bubbles expansion time scale is 20 to 21 million. Is it filling nicely in the middle? Whether the break in the star formation is caused by the outflow in the radio bubble outflow. So there is a lot of interesting thing can be done. Let me connect to the Speckle galaxy now. So a nice one, say 200 kiloparsec jet, say 50 million years ago. It could be 100 million year old. We cannot do the aging analysis here because the speckle index here is flatter for some practical really accretion related reason, or it is particle acceleration something, or the measurement error. We're not very sure. We are following up. These are the published thing in 2011. Let me show you what are the new things that we have found. New thing with Subaru, XMM, sorry. Oh, something wrong happened. I missed the XMM picture here. I'm sorry. So XMM picture is that the galaxy is here, but the XMM X-ray emission peak is somewhere else. It is not at the brightest cluster galaxy, which is this galaxy. And the Subaru spectroscopy tells us the rotation speed is 350 kilometers more than that. So it's a massive giant spiral galaxy rotating. There is no sign of merger anywhere. and it is not at the center of the cluster. It is episodic. That is definitely clear. So there is, after that, where to go next? After finding couple of like this Speca-like galaxies, spiral radio galaxy, large radio galaxy, here we spotted a large radio galaxy in a narrow line Cepheid-1 galaxy. Speca was the highest of that redshift, 0.137, but this is beyond that. So connection is in narrow line Cepheid-1 galaxies are actually young AGNs. Most of them are late type, like their color says that, dusty star forming objects. Most of them are too far that we can resolve the disk. So can we push this kind of objects to find high redshift Speca? Let me come to the second part of my work. That this is looking at using the GMRT primarily, supported by many institutes which host our citizen science training programs. Citizen science are coming from all over India, and they are trying to discover, what are they trying to discover? Looking at the TGSS data, faint and fuzzy relic-like emissions seen anywhere. They are given FITS file, and they are supposed to search anything that is there. So let me, as a summary, I'm invited to speak at a IU meeting in the IUSO meeting for astronomy for all, astronomy education for all. Let me summarize what is Red at Home is doing. Red at Home is a nationwide inter-university collaborative of professional astronomers, trained citizen scientists, technical administrative facilitator. It is the only citizen science research platform in astronomy in India. Nearly 30 institutes and similar number of professionals have contributed to its growth since 2013. It's a flying pyramid model. Scientists are facilitators as wings, and large number of trained citizen scientists at multiple levels of expertise make the multi-layer pyramid. It has 150 astronomer, 1,000 eye astronomer, 2,500 active planners, 4,700 total number. This way, citizens achieve GMRT telescope time, co-authorship in papers on galaxy evolution, and MS or PhD selections abroad. All kind of growth is also connected. So basically, not only discovering by the scientists, they are trained people actually. So how do they achieve this thing? They are achieving in a social media group, Facebook basically. What are they doing? That roughly on average per day they are posting 2 RGB images of galaxies, 20 image or text comments per day, 40 reactions a day. This is basically the statistics there. And this process basically, how they are able to do so many things, because we have made through the NASA Skyview, now we have made a Python-based small interface where people can simply put the galaxy name, simply put the coordinate, and get a multi-wavelength images, optical RGB, ultraviolet, IOU RGB, infrared optical UV optical IR RGB. And then they can also make a radio optical radio RGB, where NVSS and TGSS are put in blue and red respectively, and optical is middle. So by looking at this, they are getting trained to identify faint and fuzzy things and characterize them, and submit like a Google form. So they spot this kind of a RGB image with TGSS and VSS, and then if it is a good enough object, looks like faint, fuzzy, crazy like thing, relic like thing, maybe a remnant lobe of something, we follow them with GMRT. With a project called 4 times we have got GMRT time, GMRT observation of object discovered by Red Home Astronomy Laboratory. See the beautiful difference. Few minutes in the sky in 150 megahertz, to a couple of hours at 327 megahertz. The beautiful sources that this host galaxy is here, completely relic and distorted or displaced plasma there. Another object, possibly a Speca-2 like thing. Here is that same ROR, radio optical radio, that people make, citizens make. And here you see the host galaxy is here, one lobe here, another lobe, both NVSS contour and TGSS contour. Unless they were same, actually one could not trust that this is really there. Then this is the optical thing, it's so small, radio lobe is large. And one can say the UV, looking blue, is actual arc-like structure. And here it's like a distorted spiral galaxy, probably interacting with this one. So what we can say that this 100 kiloparsec large relic lobe, up not so looking smart, looking really like a radio galaxy lobe, but it's not looking, it is really a spiral galaxy that is interacting. So this kind of sources, maybe many of them may be there. The luminosity is such that it's actually filling the gap that I described. So relic limb and lobe of 100 kiloparsec size, both lobes are on same side because the ramp pressure like wide angle tail we experience. UV arc possibly interacting. UV arc is also because of the ramp pressure triggered star formation. Smaller on one side with the galaxies. Such faint sources may be numerous in the nearby universe if you look at them. Another one, There's possible case, if it is really the case, really proven by further observation.
Ananda?
Maybe sure. Yes.
You're almost out of time.
Okay, within a minute I will finish. 1 minute. Is that okay?
More like 30 seconds.
Okay, fine. Here is another target that if it is true, then it is actually a first spiral-like galaxy with a large lobe. Another one, episodic radio galaxy. Probably during the merger, the plasma got stuck there. With GMRT, one can detect beautiful one side. In summary, I will say that this is combining kind of research, education, and outreach. Discover speckle-like galaxies more, investigate details, find a faint and fuzzy relics with citizen science, multi-wavelength follow-up, and a collaborator is trying to address both the scientific discovery as well as the development of the human resource there. Welcome for all the collaborations through this. Thank you very much.
All right, great, thank you. Well, we're out of time for your time slot, so we don't really have time for questions. I don't see any burning question right now. If people have questions, there's always the Slack and also the chat.
Sorry, I didn't listen to the warning, so I missed the time.
All right. Let's move on. Thank you, Ananda.
Thank you everybody.
The next speaker we have is Binny Sebastian.
Hi.
All right. Yeah, your slides are up, and you're going to be talking about understanding radio outflows from Seyfert galaxies, and I will try to give you a 2-minute warning.
Okay, thank you. So hi everyone, I am Binny Sebastian. I am a postdoc at Purdue University. So today I'll be talking about the work that was carried out as a part of my thesis. And this is the list of collaborators involved in this work. The main aim of this work was to understand radio outflows from Seyfert galaxies. So despite several decades of research in the field of AGN jets, there are still a lot of things that we do not know about these jets. We know that only 10 to 15% of AGN have large-scale jets. So why is it that only some AGN host jets that extend up to kiloparsec scales, whereas most of them don't? What are the factors that affect jet formation? Is it the black hole mass or the spin or accretion rates? Another question is regarding their duty cycle, and for how long do one episode last, and how often do they restart, and how does it depend on the type of AGN? So majority of studies trying to understand jet formation has had their focus on powerful jet systems. We, on the other hand, were mainly looking at Seyfert galaxies, which are classified as radio quiet. I would like to mention that it is as important to study weakly jetted systems as much as the powerful jetted systems if you want to get the full picture. So it was known from high angular resolution studies that Seyfert galaxies show radio structures on 10 to 100 parsec scales. Some of them had double or triple structures, which were immediately suggested to be evidence of jets. Then the question was, why does Seyfert galaxies not host kiloparsec scale radio jets like those seen in radio galaxies? So Baum et al. 93 and Colbert et al. 96 carried out lower resolution studies of these objects using the VLA, and what they found was that most of these galaxies actually hosted kiloparsec scale radio emission. But again, the origin of this kiloparsec scale radio emission was not readily attributed to jets. For example, Baum et al. Suggested that the radio emission is coming from starburst winds rather than being jet related. Whereas Colbert, who had a comparison sample of starburst galaxies along with the Seyferts, claimed it's more from a jet-related origin than from star formation. Gallimore et al. 2006 had a larger and a complete survey of Seyfert galaxies, showed that more than 44% of Seyferts show kiloparsec scale radio structures. Again, although they preferred the AGN origin, the study was not conclusive. So before we really get into understanding the jets in this system, we need to disentangle the radio emission from jets versus that from other possible contributors. So now I'll talk about the possible pathways or mechanisms which are discussed in the literature, which can lead to the radio emission that's seen. So the first one is starburst driven winds. So what happens here is that the star formation that's going on in the center will lead to supernovae and stellar winds, which in turn leads to galactic superwinds. Another possibility is AGN winds. So there are several mechanisms which can give rise to an AGN wind, for example, radiation pressure driven, thermally driven, or magnetohydrodynamically driven. And the last possibility is, of course, jets, in which case the plasma and the magnetic field are probably being provided by the central engine. So with our study, we're trying to address the question of what leads to the origin of radio emission in Seyfert galaxies. Is it star formation or shock acceleration by winds or AGN jets? So in particular, can we make use of radio polarization to disentangle the contribution? So to answer these questions, we observed a sample of 9 Seyfert galaxies, along with a sample of 7 starburst galaxies using the VLA in full polarization mode at 5 and some at 1.4 gigahertz. So on this slide, we present some of the VLA images from our study. The background shows the color composite image of the optical host galaxy, whereas the white represents the radio condors. So the 4 on the left are starburst galaxies, whereas those on the right are the Seyferts. As is evident from the images, the radio emission from starburst galaxies closely follows the optical features and the star formation disk, whereas in Seyfert galaxies, they show more lobe-like features which do not have evident counterpart in the radio. Also, we detected polarization in only 4 Seyfert galaxies and in 1 starburst galaxy. This might be due to a variety of depolarization effects that are at play. So we further observed these sources at 10 gigahertz. Our initial analysis shows that most of our sources do show polarization. I'll now talk about NGC 3079, which from our sample, which is both a star forming as well as a Seyfert galaxy. The new EVLA image at 5 gigahertz of the source is shown on the left, whereas the speckle index image from the Arcwell VLA data is shown on this side. So the red vectors represent the inferred magnetic field vectors. It can be seen that the red vectors are aligned parallel to the edge of the lobes. Also from the speckle index map, you can see that there is some evidence for flattening of the speckle index. So the high fractional polarization, about like 33% in the ring, along with the flat spectral index and the magnetic fields that are aligned along the edges, all of these point towards a shock origin of the radio emission. So shock acceleration leads to the flattening of the spectra, whereas shock compression leads to the magnetic field amplification. But then we further analyzed the rotation measure map of the northern lobes, which is shown here. It was also seen previously by Cecil et al. In 2001 that there is an inversion in rotation measure as one moves from the inner edge to the outer edge of the lobe. So this does not favor a scenario where only shocks are involved. We require organized magnetic fields in this case. Hence, the jets might be playing a major driving role in this galaxy. From this study, we conclude that while the electron population itself is being fed by the jet, the entire morphology most probably is a result of an interplay of the jet, the winds, and the large-scale magnetic fields threading the galaxy. So now coming to the polarization properties itself. So Seyfert galaxies showed a wide range of polarization fraction. Some of them had 20%, 30%, and NGC 4388 shown here, for instance, showed 13% in the inner lobes and 24% at the edges. At 1.4 gigahertz instead, we only detected marginal levels of polarization, about 1 to 4%. So what we can conclude from our data is that the Seyferts show more fractional polarization compared to starburst galaxies at the resolution and frequency of our observations. Again, this is tentative. We need more to confirm this with further observations. Now, regarding the polarization structure itself, in NGC 4388, also we see that so what is shown here are the electric field vectors. So the magnetic field vectors are parallel to the lobe edges, as was seen in the previous case. On the other hand, the inner lobes show polarization vectors which are perpendicular to the lobe axis, implying poloidal or longitudinal magnetic fields. So we compiled our results along with other sources from the literature which showed polarization, and we find that most of them have parallel fields along the edges. That's the most remarkable result. Other than polarization, we also looked at a few other sample properties, including radio FIR correlation. And here the red and the yellow dots represent Seyfert galaxies which host kiloparsec scale radio emission, whereas the black ones are those Seyfert galaxies which did not have any evidence for kiloparsec scale radio emission. And the stars are starburst galaxies, especially the green ones are those starburst galaxies which had super winds but did not have any AGN. So what is immediately noticeable is that the kiloparsec scale radio emission hosting Seyfert galaxies lie above the 3 sigma line. So this was also previously noted by Gallimore et al. In 2006. So that immediately rules out the scenario where the radio emission is merely a result of winds that transport the material from the star formation disks. But also from this plot, we notice all the starburst galaxies with super winds, but not an AGN, also tend to follow the radio FIR closely, implying that there is not much contribution from shock acceleration of winds to the radio excess. So that implies the radio excess in Seyferts is most likely related to the jets. Another interesting...
2 minutes.
Thank you. Another interesting result that we see from our sample of Seyfert galaxies is that most of the Seyferts show episodic activity. So for instance, we carried out a detailed study of NGC 2639, in which we saw the lobes were aligned in the north-south direction. The previously known lobes were aligned in the east-west direction. And these lobes are highly polarized with 21% degree of polarization. So we considered several models to explain the double lobes, including environmental impact and dual AGN, precession of jets, episodic activity, etc. And our data favors the episodic activity model the most. And on this slide, I show other sources in our sample which shows similar properties. For example, in the images of both NGC 3516 and NGC 4388, we can see two distinct lobes aligned along two different directions. Similarly, in NGC 2992, the second pair of lobe was identified using polarization previously by Irwin, which Judith had flashed yesterday in her talk. Hence, we find that majority of our Seyfert sources show some tentative evidence for restarted jet activity. So that's like 5 out of 9, which in comparison with the large radio galaxies where they show only 10 to 12%. So to summarize, we carried out an in-depth study of two Seyfert galaxies, and we find that the jet might be playing a major role in determining the morphologies in this system. And polarization can indeed be used as an effective tool for distinguishing between various models of origin of radio emission. And the radio FIR correlation study suggests that the jet is most likely responsible for the excess radio emission seen in Seyferts. Finally, many of our Seyfert sources showed tentative evidence for restarted jet activity. So that's where I'll stop. Thank you for listening.
All right, thank you, Bini. Do we have some questions? I don't see any raised hands. I don't see anything in the chat. And Anne made a comment or a question. Is that I see large fluctuations in the RM map that you showed of NGC 3079. What is causing this?
So there are errors. The errors are large, but then we made that conclusion because from a lower resolution image that was previously made in Cecil et al., they also see the inversion just as we see in our images.
Yeah, there's another question Kelly is asking. I might be missing something, but for the radio infrared correlation study, how did you distinguish between AGN jet and AGN winds?
So we can't really distinguish between the AGN winds and AGN jets if the wind is magnetohydrodynamically launched. But if it's launched by a thermally or radiation pressure driven, we would expect that the shocks are giving rise to the radio emission. But then if shocks are giving rise to the radio emission, we would expect in the starburst galaxies where there are winds, you would expect to see a radio-fire correlation, which we do not see. So that's how we concluded it. But this is like a hand-waving argument. But again, if it's magnetohydrodynamically, I missed that point. If it's magnetohydrodynamically launched, there's no way of distinguishing it.
Okay. Great, thank you. Well, I think let's move on. Thank you very much for your talk.
Thank you.
And the next speaker we have is Nicholas Seymour.
Hello.
Yes, hello. You're going to share your slides?
Oh, 1 second, yeah. Sorry.
All right, yeah, so Nicholas will be talking about finding the first black holes from radio surveys.
Sorry, just need to give Zoom permission to share the slides. Sorry about this, let me try again. Sorry about this. Problems when you have software reinstalled. Oh, it's going to make me leave Zoom and come back again. Apologies, I'll be right back.
Okay. We didn't have a copy, Anna, of his slides.
Oh, I'm sorry. Yeah, I should have checked. 1 second.
Hello, I'm back. Let me try again.
We see your screen, not your slides.
Okay. Let me get the slide up. There we go. Right. Sorry for the delay. I will crack right on. Good evening from Western Australia. In fact, it's going to be Saturday in a few seconds. I'm Nick Seymour from the Curtin node of the International Centre for Radio Astronomy Research. I'm very happy to be speaking at this meeting. I have fond memories of the VLA as it was part of, too many slides, as it was a major part of my PhD, and very fortunately the film Contact was on TV the night before my PhD defence, which was quite inspiring to see Jodie Foster and the VLA on the screen. So the work I'm presenting on the high redshift radio galaxies is part of a moderate sized collaboration, but most of the work I'm going to be presenting is either by myself or by the two first names there, Guillaume Jouard and Jess Broderick, who are both here at Curtin with me. So we're now finding many massive black holes in the early universe from optical surveys of QSOs. And with these massive black holes that are being found, the big question is, how do they become so massive so quickly? So the plot on the right from Bernardos et al. Shows the mass of these black holes if you go back in time, assuming maximum Eddington accretion. And you can see that while the growth is exponential, if the growth is only from Eddington accretion or accretion at the Eddington limit, then the seeds of the black holes would have to be very massive, thousands or tens of thousands of solar masses. So we want to find new ways of finding these high redshift supermassive black holes. And optical surveys, of course, miss obscured AGN. And so radio surveys are a great way to at least find those obscured AGN, which happen to be radio loud. So this will allow us to study the host galaxies, as well as the environment, and also allow us to understand how the jets might be interacting with the circumgalactic environment in the early universe. And in the bottom right is a picture of the spiderweb galaxy from George Miley. Another exciting reason to study radio galaxies at high redshift is the potential to probe the epoch of reionization through looking for absorption of the redshifted H1 20 centimeter line if the radio galaxy happens to be bright enough and within the epoch of reionization. So in the bottom left is a simulation in a paper from Chris Carilli back in 2004. So we've been using a novel technique to find our radio sources, different from the classical traditional ultra-steep spectrum technique, which you can see on the plot on the left, where high redshift radio galaxies tend to have steeper spectral indices. We've been using low frequency information from the Merchant Wide Field Array across 70 to 230 megahertz. And in particular, we've been looking for curvature in this spectrum. The hypothesis that we're testing is that the radio galaxies in the early universe will be very compact because they're confined, and they might demonstrate synchrotron self-absorption or free absorption. So the plot on the top right, I have taken a model of a redshift 1 gigahertz peak spectrum source. And all I've done is simply shift it back in time, where of course it becomes fainter and the peak shifts to lower frequencies. And what we see is that in low frequencies, the flux doesn't decrease very much, and the SED becomes curved over the MWA band due to the peak of the SED moving into the low frequency band. And of course, at high frequencies, the flux decreases very quickly because it's moved to high redshift very rapidly and doesn't have the advantage of that favorable K correction as we do in the low frequency. So in addition to being compact, as we use VLAS or FIRST to confirm that our targets are compact, the other main selection is that our sources are faint in K-band, which would suggest that if they're large galaxies, they're going to be at high redshift. So what are the results of our pilot? So we had 4 sources in a gamma 9 field selected with these criteria, principally starting off with the MWA, and we followed them up with deep K-band imaging from VLT and ALMA 30 gigahertz spectral scan to search for CO, and also in the continuum to map out the synchrotron emission at high resolution. 2 low redshift radio galaxies on the right slipped through the net, and these are brighter and more extended than what we really hoped for. But so these are sort of not of interest to us, but we did manage to confirm one at redshift 5.5 from 2 CO lines from ALMA, and one at potentially higher redshift, which is distinctly more compact. But these are all very luminous. So if we look at the properties of these radio galaxies, Looking at their luminosities, the redshift 5.55, seen as the red point in the left-hand plot, is the most luminous radio galaxy we know of above redshift 5.5, and is comparable to other well-known radio galaxies at slightly lower redshift. So it's extremely powerful and luminous, suggesting that it is hosting a massive black hole. Of course, the other galaxy with the unknown redshift is indicated by the yellow line, showing it could have a range of luminosities depending on its redshift. If you look at the KZ plot in the top right, we can see that both the 5.5 redshift source and the unknown redshift source are very faint in K-band compared to most other known radio galaxies. And if we look at their radio to infrared flux ratio in the bottom right, we can see that these two sources have extreme flux ratios, with, in this case, the green point being the redshift 5.5 source, and a yellow line indicating the unknown redshift source. So it's about the third highest ratio source in the radio to K-band flux plot, regardless of redshift. What we can do for the redshift 5.5 source is estimate its jet power from modeling using the RAISE model by Turner and Chavala. And we estimate a jet power of about 10 to the 40 watts. And we can use this jet power in combination with the upper limit of the mid-infrared luminosity to probe what regions of the black hole mass Eddington accretion rate parameter space this radio galaxy could lie in. So I don't have time to go through the full details, but the plot on the lower right, the shaded regions represent the acceptable parameter space for the jet power in blue, and the upper limit from the mid-infrared non-detections in red. And assuming that at high Eddington accretion rates, the disk switches from a thin disk to a slim disk and produces powerful radio emission, then the black hole mass must be around 10 to the 9, and with pretty high Eddington accretion, very comparable to the QSOs discovered at redshift 6. So this is very encouraging that we can actually find these equivalent black holes from radio surveys. Moving briefly on to the unknown source, Gleam J0917, which we initially thought was at redshift 10, which of course was very exciting for a while, but follow-up observations with the VLA for 5 hours and ALMA for 2 times 40 minutes did not confirm the lines we would expect for such a very high redshift source. So this perhaps wasn't too surprising given how unprecedented a redshift 10 radio galaxy would have been.
2 minutes.
However, thank you. We've had a go at estimating its redshift from its SED. We only have one detection, but we have many upper limits. And a paper by Guillaume has suggested it's either a very dusty starburst at redshift 3 or potentially a Lyman alpha dropout at redshift 7.5. However, these are quite uncertain. We do have Hubble follow-up with GRISM spectroscopy and deep imaging, which is still being written up at present, so I can't say any more about that. But here's just the Hubble image underneath the ALMA contours. I'll briefly mention we're looking at a full sample of 55 candidates above 1200, over 1200 degrees squared, with similar selection techniques. And we hope to find perhaps tens of radio galaxies above redshift 6 and hopefully into redshift 7. So I'll just put up my conclusions and say that we've got a success rate of 25 to 50% for finding radio galaxies above redshift 5.5. We're finding radio galaxies with similar black hole masses and accretion rates to the redshift 6 QSOs. There's a plethora of follow-up of our 2 radio galaxies going on. And of course, we're beginning work on our full sample of 55 sources right now. And this is all due to the unique combination of MWA, ALMA, and VLA. And of course, in the future, we're going to have the unique combination of the SKA and the NG VLA. And I'll finish there. Thank you very much.
All right, thank you. This is very promising, and hopefully we'll find a lot more high redshift galaxies. Do we have any questions? We have time for maybe one question. I don't see anything.
I'll be on Slack if anybody has any questions.
All right, well, thank you very much, and we'll move on to the next speaker. Next, we have Pallavi Patil.
Hi. Can you see my screen?
Yes, so we see your slides. Yeah, she will be talking about young radio AGN in the VLA and NG-VLA, or go ahead.
All right, thank you, Frank. Hi, everyone. My name is Pallavi Patil. I'm a Jansky Fellow here at NRU in Sapporo. So today I will be talking about young radio AGN and some of the studies that we can do with VLA and some of the prospects when NG-VLA comes online. So to start with, here I'm showing a schematic of life cycle of a radio AGN. Starting with a newborn jet, the jet evolves to become these compact young radio AGN. And there are many samples, and they have been named differently depending on how you identify them. Typically, most compact scales are called CSO-HFP, with slightly older sources becoming GPS and then becoming CSS. And eventually, these sources either can die or continue to grow and become these large-scale FR1 or FR2 radio galaxies that we know of. And FR1 sources have been very well studied with VLA for many, many decades. Now, once the jet production stops, the source can go into this Velic phase. And if somehow the jet is triggered again, then you start seeing this restarted AGN that we have started seeing with lower frequency surveys. And then the cycle can go on eventually. So now in all this picture, there is a hidden axis of luminosity. So far, our basic understanding of life cycles of radio AGN is only limited to the luminous and powerful radio AGN, especially on compact scales. As you can see, here I'm showing radio luminosity versus linear size diagram. And most of the CSOs GPS that were observed before are the most powerful radio sources. And that was because those were the ones that were easily observable with early radio telescopes. With the sensitivity upgrades and the wide bandwidths that are being available with recent VLA upgrades or other upcoming facilities, we have started looking into this lower luminosity region, but it's still largely unexplored area. So today I'll be limiting my talk about to these more luminous or moderately luminous radio sources. So what are the key properties of these compact and young radio AGN? Starting with morphologies, they are defined to be sources that have subgalactic or linear sizes of about a few kiloparsecs or so, with CSS becoming few kiloparsecs in size. So I'll also try to highlight some of the contributions from VLA. VLA has been quite essential for many of the follow-up studies for compact sources. For morphologies, VLA can provide sub-arcsecond resolution, which has been quite useful to either constrain the linear sizes for the extremely compact sources or map some of the older sources that are about few kiloparsecs or so. The other key feature is the radio spectra. There is a characteristic turnover at low frequency. And to study the spectral turnover, you need a broadband radio observations. And VLA has been quite useful to constrain the high frequency part of the spectra. Young sources are also shown to be variable. I mean, there are some imposters. For example, blazars can also show this turnover. And so you need a broadband monitoring of these sources to truly identify the young and compact radio AGN. So VLA has been quite useful there. And these sources are expanding, and hence their spectra can evolve. Although these evolving spectra isn't noticeable for slightly older sources, but for extreme compact sources, as I've shown here in this example, you can see the change, you can see the evolving spectra. Especially for newborn sources, these timescale can reach human years. And Christina, who will talk just after me, will talk about this interesting sample that she's finding with VLAS. These sources also have polarized emission, and VLA has been quite useful there as well, especially for CSS sources. So let me shift gears and talk a little bit about my sample and how some of the topics that I just discussed are quite relevant to my sources here. So now this is a sample of heavily obscured quasars with compact radio jets. It was selected by Carol Lonsdale, and she used WISE extragalactic catalog to pick out the sources that had the reddest colors. Now, there have been many samples like that with very red WISE colors, and they are associated with this very transient phase that happens just after major merger. But the unique feature of our sample selection was the addition of the radio selection. We picked out sources that had a bright or unresolved radio source in NVSS. So we have a radio AGN associated with these unique sources. And such major merger driven phases are more likely to be common at cosmic noon. We used SDSS to pick out sources that were optically faint or undetected to ensure these are heavily obscured and high redshift sources. So what do we know so far? These are some of the reddest and most luminous sources at epoch of cosmic noon, that's Z of about 2. They're extremely rare. We only found 800 sources in all sky, of which 150 are being followed up with our follow-up surveys. So to summarize, these are heavily obscured systems that can be found just after major merger. At least different signs are showing that this is the case. And the question that I have been looking at was the radio properties of this unique sample. Since we are expecting the sources to be in a post-major merger phase, is the radio emission consistent with being a recently triggered radio jet episode? So this has been the question of my thesis, and I'll just quickly give you some results that have come out of that. So NVSS resolution isn't sufficient to probe more into details of the morphologies of spectra. So we followed up our sample with VLA. To get the sub-arc second resolution, we used 10 gigahertz observation in 2 configuration A and B. The main result, now going back to this figure, was that about 70% of our sample was indeed unresolved at 10 gigahertz with limit to their linear sizes of about 2 kiloparsecs or so. And they are shown by this orange arrows here. Some of our sources did show some interesting morphologies at VLA resolution. These are those blue stars. And here I'm just showing the morphologies that we end up seeing in our sample. There's a quite wide range of morphologies, starting with the most compact sources being only resolved on VLBA scales, and with the 30% being resolved by VLA on scales of about few arc seconds. So today I'll try to just keep my discussion on these sources, because with VLA you can do a lot more interesting investigations to understand the astrophysics of these sources. So in the evolutionary stage, these sources would be slightly older CSS type of sources where the jets have just started to come out of the host galaxy. Now, we also talked about radio spectra. So I tried to investigate or constrain the spectral shapes of my entire sample of 150 sources. To do that, I used different surveys. To start with, I had just NVSS and 10 gigahertz. So I ended up using different archival radio surveys that are available right now. And just to highlight VLA's contribution, starting all these surveys that have been right above it are all the surveys that have been conducted with VLA. So it has been a quite useful instrument for my thesis as well. Here you can see a schematic diagram just showing the kind of heuristics we have developed to characterize the spectral shape. So the main result that is coming out of our spectral analysis was that about 40% of our sources do show a characteristic turnover, confirming that these are indeed CSS, GPS, and HFP candidates, and they're likely to be young radio AGN. About a quarter of them did show curved spectra, so there could be a turnover below 150 megahertz. So there could be some signs of absorption, but we need some follow-up data. So from radio side, there have been quite a promising result, and we are indeed finding some of our sources could be compact and young radio AGN. But when we actually go to MIR properties, there's a quite drastic changes, quite drastic differences. Most of our sources, as you can see in the green here, are quite red in Weiss colors. But if you look at the radio AGN, the orange ones being the compact GPS and CSS, there's almost hardly, there's only one source here, and there's no overlap with CSS and GPS. It could be a selection effect because the redshift could be different, or some of the physical reason could be that indeed we are identifying sources that are caught in this quite short phase after the major merger. So our snapshot survey has been quite successful. It has led to identification of two interesting subsets that we are currently following up. Yes. 12 of these sources have structures on VLA scale, and 20 have structures on VLA scales. Those are the slightly older ones. But no matter which subset that source belong to, we have followed all of these sources with VLA to get a deep multi-band imaging. And we have started working on this data set. To start with, we picked this source. The reason for picking this source was that this source has an interesting and very promising ALMA data as well, and it has a quite broad CO line detection. This is the work that's been done by my summer student, Camilo Vasquez. He worked on this data, this source, particularly this summer. Some of the signs that we are planning to follow up with this data set is that trying to obtain high sensitivity map, we are requesting for at least 5 to 10 times better sensitivity than our snapshot observation, so that we can probe the low surface brightness emission if it's present. Look for evidence of jet-driven outflows. We'll use ALMA data and our VLA maps for that. And we'll also try to look at polarization properties, because that can tell us if some polarized emission is detected. That can tell us a little bit more about the ambient medium in which the jets are expanding. And on the spectral side, we are aiming to build up these integrated as well as spectral maps, at least for the sources that are resolved by VLA, and try to look into spectral aging study if we end up seeing some break at Ka band, or have some limits to the spectral radiative ages through that. So this is still a work in progress. So there's going to be a lot more studies that are coming out of this VLA data set that we have. Now to wrap up my talk, let me just quickly tell you about what NGVLA can do. So far, our studies are very much limited to only the luminous radio AGN, and that too would take a lot of hours of VLA or VLBA to conduct these study for larger samples. But with the high sensitivity and the resolution of NGVLA, we can do this for a much, much larger sample and in a statistical sense. Here I'm listing some of the AGN science book chapters that are discussing some of the very cool AGN science that you can do with NGVLA. Now, just focusing on compact radio AGN, NGVLA will help us map the morphologies of, even on the parsec scales, if we combine the continental baselines for a Z of 2 radio AGN over a much, and those radius can be over a much large range of luminosity than we can currently study. And on the spectral side, NGVLA in the combination with NG-LOBO or any other low frequency survey, such as SKA, we can robustly characterize the turnover as well as the higher frequency spectra, and do some spectral aging studies for a much larger sample of compact and young AGN. So with that, I'll just summarize. VLA is being quite crucial to do follow-up studies of these compact and young radio AGN. And till NGVLA comes online, I'll keep working on this interesting sample of heavily obscured and luminous quasars with VLA. And once NGVLA is available, it is set to revolutionize the field of young radio aging. Thank you so much.
All right, great. Thank you, Pallavi. We have one question already in the chat and about time for one question. Do you have any clue about, so this is from Sandor, do you have any clue about the redshift distribution of your heavily obscured sample sources, or are they mostly invisible in optical?
So we, for now, we are just limiting our observation to 150 sources, and about 73 of them were followed up with VLT. I'm just seeing if I have the redshift distribution here. Oh, no, I don't have the redshift distribution plot, but the redshift range, we have spectroscopic redshift for about 73 of them, so that's half of them, and they go from 0.5 to 3 with a median of 1.5. So the follow-up spectroscopy is giving us kind of in the right cosmic noon epoch that we wanted. Yeah.
Okay, thank you. There's another question. Let's do that one quickly. Last question. Did you see any difference in the morphology for the sources with an inverted radio spectrum?
Oh, so the inverted radio spectrum is compact, mostly unresolved, and that's the case for most of our inverted OR sources that have a clear turnover. That's because of just the resolution limit of VLA. We do have a snapshot imaging with VLBA, and my advisor Carol is working on it. And once we have that paper out, we'll know more about the relation of the radio spectra with the morphology of inverted and turnover spectrum, peak sources.
All right, great, thank you. Nice talk. And now I will hand things over to Steve to chair the remainder of the session.
Okay. Next up is Christina Nyland from NRL. Hopefully you can share your screen. Speaking on newborn quasar jets that have switched on over the lifetime of the VLA.
Okay, thank you, Steve. Does everything look good?
Yep.
Okay. Thank you very much to the organizers for putting this meeting together. It's a pleasure to be here, and I've really enjoyed the science and all of the stories, the real history of the Very Large Array. So my name is Christina Nyland, and I'm an NRC fellow based at the Naval Research Lab in Washington, DC. And today I'll be telling you about a recent study that I led of quasars that were known at infrared and optical wavelengths, but appear to have suddenly switched on in the radio in the past 10 to 20 years. And for those who are interested, here's just a screenshot of the paper that came out late last year. It also highlights all of the co-authors and collaborators who contributed to this effort. So just a bit of historical context from my point of view before I get into the science. We heard from Ron Eakers a day or two ago that one of the key science drivers of the VLA were radio galaxies, quasars, and cosmology. And we heard today from Catherine Blundell that really the VLA has been a huge success in these areas. But of course, the VLA was designed to be flexible, and it has gone on to produce great science in many other topics as well. So it's beyond the scope of this talk to provide a comprehensive history of radio AGN. And I think we already have had a really nice overview from the previous talks in this session, but I just wanted to share this picture of Cygnus A from Perley et al. 1984. I like this picture for a number of reasons, but this year is also the year I was born. So I am younger than the VLA, but I have really enjoyed spending time at NRAO. I got my PhD at New Mexico Tech. I was there from 2007 to 2015, and I have a lot of fantastic memories. And for those who are interested in learning more about the history, I learned sort of in preparation for this talk about these two recent books that are open source and have fantastic historical and technical context. And I encourage you to check those out. Okay, so this is a talk about quasars, about accreting supermassive black holes or active galactic nuclei. And I just want to give you my perspective on why they're important. We've heard all the other views on this from the previous speakers. But one thing that hasn't been highlighted yet is the role of AGN for human exploration. So we've sort of come to take for granted as radio astronomers that we have observing calibrators to use for calibrating fluxes and for phase referencing and other things. And these are all compact radio AGN. AGN are also important for navigation and timing. They make up something called the International Celestial Reference Frame. This is based on very long baseline array imaging. AGN are also important probes of extreme physics, including supermassive black hole accretion, gravitational waves, and cosmology. And I have a few pictures here of M87 over a wide range and spatial scales, including this beautiful Event Horizon Telescope image from earlier this year. And then finally, AGN are important for galaxy evolution. And this is the aspect that I am most interested in my research. So we know that AGN reionize the universe. And then we also heard today a really nice overview of how energetic feedback by AGN plays an essential role in galaxy evolution. And so the question that I'm really interested in is, how do jets form and grow, and how do they ultimately influence their environments, including on ISM scales? So this is sort of moving from studying the large scale, hundreds of kiloparsec wide sources like Hercules A here, and studying the smaller kiloparsec scale jets in great detail. So we do have reason to believe that jet ISM feedback is also important for galaxy evolution. And this is an area that I've worked on in nearby galaxies. This is NGC 1266, one of my favorite galaxies. It was part of my thesis work. This is a sort of a wimpy kiloparsec scale jet in this nearby early type galaxy. And this object is special because it has a multi-phase outflow. We see it in atomic, molecular, and ionized gas. And we, through a series of papers, more than are listed here, we believe that it's driven by turbulence from the jet disrupting the ISM. And of course, we heard some great talks about jet-driven feedback in nearby galaxies earlier today. Simulations are another thing that I don't have time to go into in detail, but we do have modern hydrodynamic simulations of jets propagating in a dense ISM. They support the importance of even lower power jets as being influencers of ISM conditions, and potentially more important than the higher power ones, which may just drill through the ISM without disrupting it. Okay, so it's pretty clear that to answer the questions that I've raised, we really need to study the young and/or compact radio jets. And so the key properties of these sources are that they have kiloparsec scale extents or smaller, they have peaked spectral shapes, and they also are well known to be variable, either due to intrinsic or extrinsic effects. And I'll just emphasize, this is a 1981 paper, review article by Kellerman and Polony Toth. And in this paper, these basic properties were well understood, before the 1980s. So what's really new is understanding the context with galaxy evolution and the cosmic importance of these compact jets. And we, of course, heard the last two talks before mine were on this topic as well. Okay, so the science I'll be showing you utilizes data from the Very Large Array Sky Survey. I think we've all heard quite a bit about VLAS in this meeting. So 2 to 4 gigahertz survey. It covers the entire northern sky, and it has a multi-epoch observing strategy, which is really cool for these slowly varying dynamic radio sources. So with the goal of identifying young radio AGN, I started this project a couple of years ago comparing FIRST and VLAS. And so here's just a quick comparison of those two surveys. They're similar. The biggest difference is when the data were taken. So this is actually work led by Dylan Dong. He did all the hard work of human vetting these data, and he found 600,000 sources and 10,000 square degrees of overlap and thousands of VLAS sources that are not in FIRST. And these sources are a mix of slow radio transients like tidal disruption events, and then also radio variable sources due to propagation effects, as well as intrinsic AGN variability. So what did we find? So sort of the punchline of this whole talk is that we compared known quasars in the optical and infrared that had no radio emission at FIRST. And then when we looked 10 to 20 years later with VLAS, there were clearly identified bright sources. And this was a fun NRO press release. And there was also an NRL press release highlighting the role there as well. And this is an artist's impression of what we think is going on. So we do think we are catching the onset of jet activity, radio jet activity in pre-existing quasars. And just because this is a history conference, where this is the VLA's birthday party, I've just got a couple pictures showing some things from the 90s when the first data were taken, and from today. So music, cars, and science have changed a lot, even in this short time frame of the VLA's lifetime. So our selection criteria, just to go into a bit more detail on that. So we started with 2,000 variable sources over 3,400 square degrees of VLAS. And then we cross-matched with SDSS and WISE within an arc second and above a millijansky. And then we refined the sample down to require fluxes of in VLAS above 3 millijanskys so that we could rule out the steady but optically thick sources. So we of course did some follow-up. We obtained simultaneous 1 to 18 gigahertz VLA data in the A configuration to look at the single band variability in the spectral shapes. And here's what we found in terms of the variability. We found that on timescales of decades, we had amplitudes of 100, increases in flux amplitudes of 100% to more than 2,500% in the most extreme case. But we had relatively steady fluxes at S-band on timescales of months. And so the details we can talk offline or on Slack or in the questions, but this is most consistent with intrinsic radio AGN variability rather than things like propagation effects. And so here are the radio spectral shapes. So there's a simple power law model here. You can see clearly that doesn't fit. A curved power law model fits beautifully. And we know that peaked spectra are consistent with absorbed and compact jets. And so this was really exciting to see this. So just to convince you a little bit more that these sources likely are young jets, we can use the turnover size relation. So this is a relationship between the spectral peak and the size. So if we take the spectral peak of one of our sources, this one peaks at 15 gigahertz or about 40 gigahertz in the rest frame, given its redshift 1.5, we find that it has a size estimate of something like 1 to 10 parsecs. And if you assume a velocity of 0.1 c, you get an age of something like 30 to 300 years. So roughly consistent. Of course, the goal is to get VLBI data from the VLBA or possibly EVN data and to really pinpoint that a bit more.
2 minutes.
So what are the sort of big picture implications of this in terms of what role young and compact jets might play in galaxy evolution? So we did, this is something that is an ongoing goal that will benefit from improved statistics on this compact and faint population of young jets, but we did find a sky density of 4 times 10 to the -3 per square degree. And we found that to be consistent with a period of occurrence of about 100,000 years. Now, this is, of course, a shorter time scale than the typical like 10 million years age assumed for a large-scale source. And so we interpreted this as evidence that episodic short-lived jets appear to be common, especially at redshift 1 to 3. And this raises this interesting possibility of jet ISM feedback that is going to be worth exploring as we go further. So there's lots of ongoing multi-wavelength work happening with existing instruments that I don't have time to go into now, but I'm happy to talk about. And just really quick, I think that the next generation very large array has a lot of exciting new opportunities to really get a handle on jet ISM feedback and its impact on galaxy evolution in new ways that we haven't been able to do before. And NG-VLA will measure both the continuum emission from the jet, of course, and then also molecular gas in the ISM. And I have a paper that provides a review of AGN science with NG-VLA, Nyland et al. 2018, and you can check that out for more info. Just real quick, as I think I'm out of time. In the paper, we do consider imaging simulations with NG-VLA, and NG-VLA will really be an ideal instrument for compact jets. It really won't have the surface brightness sensitivity for the large scale ones, but SKA and other instruments will excel at that. And finally, this is slightly outdated band and telescope distribution information, but the point is that we'll be able to reach parsec scale resolution at redshift 2. So with that, I will end. And I just want to emphasize that multi-epoch radio surveys catch newborn jets. And it's really exciting that short-lived jets may be common at redshift 1 to 3, and we'll be able to really study that in more detail with NG-VLA. So I'm happy to take questions.
Okay, thank you, Christina. We have a question from John Tobin. Have there been searches for jets turning off, detections in first, but missing from VLAS?
Yeah, that's a great question. The reverse transients, those are harder to identify just based on the relative depths of first and VLAS. It's easier to find something that turned on in VLAS. Just if you think about the typical optically thin power loss spectrum that like a normal radio source has, it's going to be harder to rule out that it wasn't just like a steep spectrum, ultra steep spectrum source. So hopefully that sort of answers your question. It's definitely worth pursuing in the future. It's just harder to really fish out the real ones.
Okay, and Greg has his hand up.
Yeah, so this is in line with the past question, but I was wondering that when a jet turns on, that is sort of clearly a sort of binary choice. But given the long synchrotron ages of radio emission, do we actually have any hopes for detecting jets turning off if we found on order 20 sources that turned on? You know, finding one that turned off via this anti-transient method seems like that might be hard. Am I missing something?
Well, it depends what you mean by turning on and turning off. I'm using all of these terms very loosely, I guess. Yeah, I see what you're saying. There could be other effects that would cause a dramatic decline in the flux. For instance, like variable Doppler boosting, if it was, you know, you check the numbers to make sure the physics works out, but you could have a source that was more aligned and then became more misaligned, and so it's declined in flux, which is not incompatible with a jet being compact and also young. By the way, it just makes things more complicated. But I think there is some hope. Is a short answer. It's just tricky.
All right, thank you.
Okay, there is another question chat, but need to move on. Ivan Del Vecchio from Max Planck, talking on clues on the evolving infrared radio correlation from deep surveys.
So hello everyone, I hope you can see my screen.
Yep.
Okay, great. So let me go full screen. So Good afternoon or good morning, everyone. My name is Ivan Del Vecchio, and thanks a lot for giving me the opportunity to speak at this nice conference. I'll be talking about recent results regarding the evolution of the so-called infrared correlation thanks to deep VLA surveys. So as we have already heard today as well, the infrared correlation sets an important benchmark between thermal, infrared, and non-thermal radio continuum light at gigahertz frequencies, both arising from star-forming processes in galaxies. And this has been widely known since a few decades to show a tight correlation, at least in the local universe, between infrared and radioluminosity that is usually referred to as QIR, which is the logarithmic ratio between total infrared and monochromatic radioluminosity. And the tightness of this correlation has been a strong motivator for using this correlation for a number of extragalactic studies. First of all, because it allows to jump directly from monochromatic radio power to star formation rate, which is really important. But it's also important for the AGN community because it allows to easily identify the so-called radio excess AGN, so sources that stand out from the correlation because they show extra radio emission due to AGN-driven jets or lobes. But of course, in order to push the full potential, to leverage the full potential of this correlation, especially in the Irish universe, and especially also in the upcoming NGVLA era for the faintest radio detections, a critical question that we need to address is whether and how this infrared correlation varies with redshift or across different types of galaxies. And this is a quite controversial topic, actually. So we try to tackle this question by studying the infrared correlation over an unprecedentedly large range in redshift and stellar mass in order to establish whether it evolves with either of them, and if any, what is the primary driver of its evolution. So for this reason, we have studied the infrared radio correlation starting from a purely stellar mass selected sample of galaxies in the cosmos field, because this field boasts exquisite quality photometry and redshifts for over 500,000 galaxies. And in this catalog, the Cosmos 2015 catalog, we have essentially near infrared selected galaxies, so essentially stellar mass selected, from which we have drawn our final sample that we analyzed in this work. The sample counts over 400,000 mass selected galaxies, also selected to be star forming based on blue dust corrected optical colors. So this huge statistical power allows us to span, as you can see from this gray box, an extremely wide range in both stellar mass on the y-axis and redshift on the x-axis. And this statistical power also enables us to bin our sample across both parameters, which are the gray dashed lines, which I hope you can see. And ideally, what we would like to do is to study what is the average QIR, so the average infrared to radioluminosity ratio across this plane to check what is the primary driver of its evolution. So for this reason, we made use of ancillary infrared and radio data that are available in the Cosmos field. Infrared data come predominantly from Herschel, Scuba, and Aztec facilities. All these fluxes are deblended thanks to higher resolution priors. And for the radio, we used the VLA Cosmos 3 years dataset, which is a sub-arc-second resolution and extremely sensitive radio continuum survey at 3 gigahertz, which covers the entire Cosmos area. However, as you may see from these histograms here showing in red infrared detections and in blue radio detections, these flux-limited samples are strongly biased against low-mass galaxies. For comparison, the gray histogram shows our parent mass-selected sample of star-forming galaxies. And you can see that by starting from a mass-selected sample, we can strongly avoid the bias inherent to any radio or infrared selection against low-mass galaxies. But of course, there is also a large fraction of infrared and radio non-detections that we have to deal with. And for this reason, we performed a multi-band stacking analysis. Namely, within each and every bin in this diagram, we stacked all infrared and all radio images in order to assess what is the average infrared and radioluminosity of the entire underlying mass selected population, and which is useful to compute QIR and to study how QIR evolves across this plane. So essentially, for each and every bean, we measured an average QIR. And this plot here shows essentially our average QIR measurements as a function of redshift and color-coded by stellar mass. So as you may see, there are large fluctuations here, also because there's a big caveat that I haven't yet addressed here, which is radio AGN contamination. You have heard about radio AGN today. They can, of course, boost radio emission and therefore strongly lower the final QIR. And so in order to identify and remove these contaminants, we investigated the observed QIR distribution traced by radio detections in each and every bean, attempting at decomposing this distribution between a contribution from star-forming galaxies that we parameterize with the log normal function and radio excess AGN at low Qs. So for statistically disentangle the two components, we set a simple threshold, which is placed 2 sigma away from the star-forming peak, where sigma is the dispersion of this function, in order to confidently disregard bona fide radio excess AGN. And then extending this correction for radio AGN contamination at all beans, we managed to purify our QIR measurements. And here you can appreciate the difference between before versus after removing radio AGN. By definition, all our points move upwards in QIR by a certain amount, which is on average a factor of 2, but slightly larger for more massive galaxies. So essentially, this right-hand plot shows finally our purely star-forming driven QIR measurements as a function of redshift and color-coded by galaxy stellar mass. And as you can already see by high, there's a clear stratification of QIR with galaxy stellar mass. In particular, more massive galaxies in red or orange display systematically lower Q, so higher radio over infrared emission compared to less massive galaxies in blue. And this is after removing radio AGN. Similar results have been interestingly reported by other independent studies from the LOFAR team at low frequencies, and also in recent results, in recent works in the local universe, which are converging to the same conclusions. That is, that the infrared correlation is not universal. It does not really evolve with redshift, as you can see from this expression, but it does evolve with galaxy stellar mass, showing a slight but significant dependence on galaxy stellar mass, with a slope of about minus 0.15 in log stellar mass. And remember this number. So in the last few minutes of my talk, I'll try to address what could be physically driving this mass-dependent QIR. So in order to get some more physical insights on this dependence, we looked at some model predictions to compare our data with. In particular, interestingly enough, some models already postulate that QIR evolves as a function of a surrogate of galaxy stellar mass, that is the star formation rate surface density, or sigma SFR. That is simply the star formation rate of a galaxy normalized by its surface. And so to make a fair comparison with these model predictions, first of all, we calculated our own sigma SFR using star formation rates that we obtained from infrared stacking and galaxy sizes from radio stacks at 3 gigahertz, which are mostly resolved. So on the left, I'll be showing our average QIR versus sigma SFR measurements. As you can see, again, each star represents a given mass redshift beam. So these are all average measurements that we fitted with a simple straight line. And this line has a slope of minus 0.13 with log sigma SFR that, as you may recall, is very similar to the minus 0.15 found between QIR and log stellar mass. So we can actually explain empirically the mass dependence of QIR in terms of sigma SFR. And this is also corroborated by recent findings by Alghera 2020 for high redshift sub-millimeter galaxies that lies very close to our extrapolation. So actually extending the validity of our trend even towards the highest sigma SFR. Finally, what do models predict? So on the right, I'm showing as a reference the predictions from the Lucky and Thompson 2010 model, one of the most widely used in the literature, which makes a number of predictions as a function of redshift also, where the redshift is increasing in these colored lines from bottom to top. Okay, so for simplicity, I summarized only a couple of predictions. Thank you. A couple of predictions of this model that are directly testable with our data. The first is that QIR broadly flattens towards high sigma SFR according to the model because of a conspiracy or a balance between competing energy losses in the radio, namely synchrotron and inverse Compton versus Bremsstrahlung and others. However, our data do not really seem to support such a flattening, even though we lack strong statistical power at the highest sigma SFR. And the other prediction is that all these trends in the model are expected to be highly redshift dependent, in particular to steepen a lot with redshift. Why? Because at higher redshift, inverse Compton scattering of the CMB photons becomes strongly dominant over synchrotron. And so it induces a stronger and stronger radio dimming that steepens the relation at the highest redshift. This is again not really mirrored by our data that are consistent with a nearly redshift invariant relation. So broadly speaking, despite our data are simple average measurements, they can't really capture the complexity of the model. There is a lot of food for thoughts, and we really hope that this data model comparison can be looked in more detail, maybe using our results and others as observational benchmark to better constrain these models and to get more physical insights on the drivers behind this correlation. So to leave you with my take-home points, our main result is that the infrared correlation seems to be primarily driven by galaxy stellar mass or any other surrogate of galaxy stellar mass, such as sigma SFR. We believe that these trends are not due to residual radio AGN contamination that we have properly accounted for. And finally, we strongly argue that in agreement with other findings, and also in the light of the next NG-VLA era, in order to assign reliable star formation rates, even to the faintest radio detections, it will be really important to rely upon mass-dependent radio star formation rate relations. And with this, I'm done, and thank you all for your attention.
Thank you, Ivan. Time for a question, if there is one. Chat or raise hand. Okay, what's the next steps here?
Yeah, there are actually several next steps. First of all is to get better insights in this data model comparison. And one way is to select representative samples of massive compact galaxies to increase the statistics at high sigma SFR and follow them up with radio observations at different resolutions in order to measure sizes and spectral indices that can be directly tested with these models. And other steps are, of course, studying also the AGN population, because here I only talked about the behavior of the star-forming population. But of course, if we rely on this QIR decomposition, we can also look at the other side of the distribution and look at the average radio power and the incidence of radio AGN and how this incidence changes with galaxy stellar mass and redshift, which boils down to the relation between kinetic AGN feedback and galaxy growth, which is one of the hottest topics in extragalactic astronomy. This is broadly what are the next steps in mind.
Okay, Jean asks, what could one change in Lackey's model to better match data?
Yeah, also very good point. So there is also a high degree of fine-tuning in these models. Although, as I said, our data are average measurements and they broadly trace the behavior of typical main sequence galaxies. So they are not formally starbursts according to a sigma SFR threshold, even though some of them fall in this regime. There could be also additional radio boosting mechanisms to be implemented in the model, such as magnetic field compression that will actually help reproduce a smoothly declining trend between QIR and sigma SFR. But each ingredient that you add to the model requires a lot of fine-tuning, because if you add magnetic field compression, you'll get a radio boost, but you also get an infrared boost. And so in order to explain why you get a net radio boost, invokes a lot of fine-tuning.
Okay, and Min had a question is normalization by galaxy size reasonable for the radio?
Yeah, okay. So if galaxy sizes are trustable. So as I said, we estimate the galaxy sizes from our radio stacks at 3 gigahertz, which is the only data set that is at sufficiently high angular resolution to be able to resolve the stacked emission for a decent number of bins. And so, as I said, these sizes are estimated for radio non-detections that we stacked in the radio. So they should be representative of about 90%, 95% of the mass selected sample that we started from. And plus, we also compared our radio size estimates with those inferred from Jimenez Andrade from the same VLA survey, finding a very good consistency, which I think is reassuring for our purposes.
Okay, well, thank you, Ivan.
Thanks a lot for your questions.
Next up is Silpa Sasikumar, exploring outflows in quasars with the VLA.
Hi, can you hear me?
Can hear you.
Yeah, I'll try sharing the screen. Can you see my screen?
Yes.
Yeah, that's fine, right?
There we go.
Yeah. Hello, everyone. I'm Shilpa Shashikumar. I'm a PhD student at NCRT for India, and I'm working under the supervision of Preeti Kaur. And here is the list of my collaborators. So today I'll be highlighting the major results from our work where VLA has played an instrumental role in exploring outflows in quasars. So AGN are the energetic centers of galaxies, which are powered by accretion of matter onto supermassive black holes. And this is the current understanding of an AGN model. It has a supermassive black hole at the core surrounded by an accretion disk. And this donut-shaped structure is the dusty torus. We have VLA regions, which are responsible for the broad emission lines in the optical spectra. And these comprise of gas clouds moving really fast and are dense. And further away, we have narrow line region, which comprises of gas clouds that are relatively less dense and move slowly and give rise to narrow emission lines in their optical spectra. We have bipolar outflows such as jets that are launched perpendicular to the black hole accretion disk interface. And AGN is further classified into type 1 and type 2 based on the presence of both broad and narrow emission lines versus only narrow emission lines in their optical spectra respectively. It is not clear why only 10 to 15% of the Asian population launch powerful outflows such as jets that extend to hundreds of kiloparsec to megaparsec scales, the so-called radio loud AGN, whereas the vast majority of the Asian population launch weak outflows such as small-scale jets or are often diffuse and wind-like. That's radio quiet AGN. So this is the radio loud, radio quiet dichotomy, and this problem has been quantified by means of the radio loudness parameter given by Kellerman et al. 1989, which is the ratio of 5 gigahertz flux density to optical B1 flux density. So according to this definition, radio loud AGN has an R value greater than or equal to 10, and radio quiet AGN has an R value less than 10. There's yet another class of AGN with intermediate radio loudness values, which is the radio intermediate AGN, and which have been long known in the literature to be the relativistically boosted counterparts of radio quiet AGN. So the current understanding is that we need to determine the dominant radio emission mechanism in each of these class of AGN in order to address this question better. While there is a general consensus about the origin of radio emission and radio loud AGN, which being the relativistic jets that are powered by electromagnetic extraction of rotational energy from a spinning black hole, that's the Blandford-Sarnik mechanism, the origin of radio emission and radio quiet and radio intermediate AGN is poorly understood. We do not know whether it's the Blandford-Sarnik mechanism or the Blandford-Payne mechanism, which magnetically extracts angular momentum and energy from an accretion disk and powers the AGN winds, or is a combination of both the processes. Also, why the radio outflows in radio quiet and radio intermediate AGN are stunted is also an open question. Possible origins of radio emission in radio quiet AGN include low power jets, winds, star formation, and coronal emission. Recent studies have shown the ability of radiopolarimetric observations to distinguish between these emission scenarios based on the differences in their degree of polarization, which is the which is the ratio of polarized intensity to total intensity, magnetic field structures, and rotation measures. These, in conjunction with spatially resolved emission line observations, can further provide insights on the properties of different media that coexist and influence each other. So moving on, this is the first source that I'll discuss in the talk today. So this is 3Zwicky-2. It's a radio intermediate quasar, and it's the first Seyfert galaxy where a superluminal radio jet was discovered. It's also a member of the Paloma Green quasar sample, which is the focal sample of my thesis work. The main panel shows GMRT 685 MHz contours in green superimposed on the optical STS's image in color. And the inset is a zoom in of the southern part of the source. In the next slide, you will see the full structure. And the inset has VLA 5 GHz contours in green superimposed on the HST optical image. In both images, we detect a triple radio structure comprising of a core, hotspot, core. The VLA image clearly detects a curved jet, and interestingly, it does not terminate in compact hotspots that are typically seen in FR2 sources, but rather in a bow shock-like morphology, which is represented by this white curve. The fact that this morphology is also seen on the counterjet side, which you'll see in the next slide, rules out the possibility of this being a sharp jet bend that may have arisen when the jet encountered a density inhomogeneity in the IGM. But it's rather an intrinsic effect. And this morphology is similar to the simulation works carried out by Clark and Burns 1991 and is indicative of the presence of a restarted jet activity in the source. And this is further supported by evidences for intermittent jet activity on parsec scale reported in the source. The GMRT image also detects a misaligned lobe, which happens to be not a relic lobe based on its spectral index and electron lifetimes. Now this slide shows the polarization images of the source. The left panel are the GMRT contours, the right panel are the VLA 5 GHz contours. So now you can see the full radio structure. The red ticks are the electric polarization vectors or the chi vectors whose length are proportional to fractional polarization. Now, one thing to note is that in optically thin regions such as the jets and lobes, the inferred B fields will be perpendicular to the chi vectors, whereas for optically thick regions like the cores, the inferred B fields will be parallel to the chi vectors. So in both the images, we find that the inferred B fields in the southern lobe will be aligned with the lobe edges, and this is consistent with the magnetic field compression due to shocks. Whereas in the GMRT image, you will see that the inferred B fields in the jet will be like this, that is parallel to the, perpendicular to the chi vectors. Hence, they are transverse to the outflow direction all the way from the core to the edge of the lobe. This could represent a series of transverse shocks like that are seen in the VLA jets, or could represent a toroidal component of a large-scale helical magnetic field associated with the jet. Coming to the VLA image, this inset is a zoom in of the core where the vectors are now the polarized intensity vectors. So in the core, as I mentioned, it's optically thick. So the B fields will be in the direction of the chi vectors, which happens to be transverse to the direction of the VLBA jet as well as the local jet. Coming to the jet component J1, which is optically thin, B fields will be parallel to the local jet direction. So the parallel B fields could then represent the poloidal component of the helical jet B field. But that's not the end of the story, because recent works by Miller et al. 2012 and Maithipur and Constantine 2019 have shown that toroidal B fields, which will appear transverse in observations, can be threaded by MHD winds, the magnetized accretion disk winds, and poloidal B fields can be threaded by jets. If that is the case, then one cannot rule out the possibility of these transverse B fields being the toroidal B fields threading an AGN wind that has been sampled on larger spatial scales than sampled by the VLA observations. And if that is understanding, then this J1 component represents the poloidal B fields threading the spine of the jet. And here, when we talk about the AGN wind, it could either be the accretion disk wind or could be the outer layers of a widened jet, like a jet sheath. So this is the first source where we have demonstrated that polarization observations can probe different layers of emission that are sampled at different resolutions, like the spine of the jet versus the sheath of the jet / wind. We move on to the next source, which is Markarian 231. This is another Seyfert type 1 galaxy and has been known to be transitioning from a radio quiet to radio loud state. So in that regard, it may share attributes similar to the radio intermediate quasar 3Zwicky2 discussed in the previous slide. Here we present historical VLA images of the source at 1.4 gigahertz on the left and 4.9 gigahertz on the right. Now here, in both images, the green contours are the lower resolution contours, so with a resolution of around 12 to 14 arcseconds, and the blue contours are the higher resolution contours with a resolution of 1 to 3 arcsecond. The black vectors correspond to higher resolution and the red vectors correspond to the lower resolution. And here the vectors are the magnetic fields which have been obtained by rotating the chi vectors by 90 degrees, assuming optically thin emission. So in the source, the higher resolution images detect a poorly collimated jet structure extending to around 30 kpc towards the south, whereas the lower resolution images detect a lobe-like diffuse emission extending to 50 to 60 kpc to the south. As far as the polarization is concerned, we find similar polarization signatures as that we saw in 3Zwicky2. So we see that in the higher resolution image, there is a region close to the core with poloidal B fields. Over here also, so this is a zoom in of this core region just to make it more clearer. There is a region of poloidal B fields close to the core. So this is consistent with, so these are parallel fields. So these are consistent with the poloidal B fields threading the spine of the jet. And in the lower resolution image, you will see transverse B fields all the way from the core to the edge of the lobe. And this will be consistent with the toroidal B fields threading an Asian wind. So this is second of the source that shows that polarization observations can identify different emission components that are being sampled at different resolutions. Thank you. So then we put, so this is a cartoon which tries to summarize our findings in the context of the radio loud radio quiet divide. We know that intermittent jet production has been often associated with changing spectral states of the accretion disk in both microquasars and quasars. The soft spectral state, which is this, is accompanied by launching of suppressed jets and strong winds, whereas the hard spectral state is accompanied by launching of powerful and steady jets. So what we find is a composite jet plus wind outflow model, which can be explained like this. So the wind is launched from the outer regions of the accretion disk and the jet is launched from the inner regions of accretion disk. And such a coaxial jet plus wind model can appear co-spatial in projection as we see in our sources. Also, when you have a coexisting jet and wind, it's possible that the jet will interact with the wind plasma and that will cause the jet to disrupt, or that much of the mass and energy is being carried away by the wind rather than the jet. So this could explain why the outflows in radio intermediate AGN are relatively low powered and small scale as compared to the radio loud AGN. So our findings are pointing to the idea that radio loudness is a function of the epoch at which the source is being observed. Another interesting finding from the Markarian 231 project is the following. We found that the outflow is matter dominated based on from a rotation measure analysis. So when we say matter dominated, the jet as it propagates through the ambient medium, it will entrain thermal ionized gas from the ambient medium. So there's a lot of mixing and one would expect the outflow to be matter dominated. But the question we want to ask is what is the fraction of mixing of this thermal plasma with the synchrotron plasma? So that takes us to the last piece of work, which I quickly go through. Here we have carried out VLA 5 gigahertz radio polarization study in conjunction with O3 emission line study of 5 type 2 radio quiet quasars selected from the quasar feedback survey sample. The sample will be discussed in detail by Aishwarya Girdhar in later today. So
you're
these
in
sources
question time now.
Okay. So I'll just quickly summarize. So what we find is that there is an interplay between the various emission components and the surrounding environment, which are likely responsible for the stunted outflows in radio quiet and radio intermediate AGN. Thank you.
Thank you. There are a couple questions in chat having to do with Faraday rotation. Do you have estimates or limits for these objects? And it looks like in Markarian 231, there is Faraday rotation. Has it been corrected?
You mean in the rotation measure image?
Okay.
Can I just go through the question once? So yeah, I mean, this, so yeah, so these are the rotation measure estimates. One second. So we actually see a gradient here, and the rotation measure seems to be increasing with distance from the core, and that's how we infer that beta, which is the magnetization parameter, increases with distance from the core.
But you showed us 1.4 gigahertz vectors and interpreted the angles. Have those 1.4 gigahertz maps been completely corrected for RM?
Sorry, could you repeat the question?
Have these vectors on the plots been corrected for rotation measure?
Oh, no, but actually, because we found that we tried to look in the in-band depolarization, what is a fraction of in-band depolarization, and that turned out to be very small. So yeah, so then we didn't go for the correction.
Okay, thank you. Next talk is Sina Chen from Technion, simultaneous radio X-ray variation of radio quiet Seyfert galaxies.
And thank you. And can you see my screen? No.
We see you.
And what about now?
Yes.
Okay, thank you. Okay, thank you for the opportunity to present my work about the simultaneous radio and X-ray variability of radio quiet Seyfert galaxy. And so, okay, so first about the AGN, and AGN can typically divide it into two classes, radio quiet, radio null, and radio quiet. And the radio emission in radio null AGN now is believed and they are basically dominated by the jet. However, where is the radio emission in radio quiet AGN from? Possible mechanism including weaker jet and AGN driven wing star formation, free emission of the accretion disk coronal. And this is still an open question. And there is a similar relation about the radio and X-ray luminosity. The radio luminosity and over the X-ray luminosity is approximated to 10 to -5, and both coronally active star and radio quiet AGN follow this relation. And even though the difference in their luminosity is about 15 order of magnitude, so is the radio emission and in radio quiet AGN also for the coronal. And in the cruise star, there is a Neupert effect, and that radio flare is followed by an X-ray flare. And so, if the radio emission in radio quiet AGN and is also originated for the coronal, can we see such an effect in radio quiet AGN? So, and suppose for a synchrotron and synchrotron optically sync source and the size of the radio emitting region, and is decreased with increasing frequency. Is increase with decreasing frequency. So assuming radio quiet AGN with the radio luminosity is about 10 to 13 erg per second per hertz, and bolometric luminosity about 10 to 14.8 erg per second at 5 gigahertz, the size of the radio emitting region, and for an optically seen source is about 0.1 per second. So the size of the corona is about 100 times smaller than the size at 5 gigahertz. So in order to detect the synchrotron emission for the corona, and we have to go to a higher frequency at about 500 gigahertz. However, if the radio emission is physical, and the radio emission and the X-ray emission are physically correlating, and it's interesting to see if there is a correlation between the radio and X-ray variability in this band. So we carry out a simultaneous radio and X-ray monitoring in 3 radio quasi-safer galaxy, Macarian 110, Macarian 716.6, and NGC 14593. Radio observation carry out with VLA ABD configuration at 8.5 gigahertz, and X-ray were observed at 2 to 10 keV. We show the image here. The optical image is for pan star, and the counter is for the VLA map. And for the figure for the left to right, were observed with DB and A configuration. We see that in the radio quasi-safer galaxy, there is very compatible in the high resolution image. So in fact, in order to detect the variability for the central core, we need to go to higher resolution observation in order to exclude the extended emission for the host galaxy. Then this is the image of Macarian 716.6, and the final one is NGC 14593. We create a radial line curve for this free source and calculate the amplitude of the variability, use the equation in here. And we the radial line curve for left to right is the integrated first density, P first density, and the extended first density. And for the top to bottom, the line curve will observe with D, B, and A configuration. And in the analyze, we also check the extended first density because we want to confirm that if there is some systematic error here. And so in here we can see that in the D and B array, the radial line curve almost show no variability or a very weak variability. And in A array, both the integrating and P-first density show a certain percent of variability, and the extended first keep constant, consider the error. So we think that the P-first density and observe with A configuration and indicate that there is some intrinsic variability in this source. The second source is Macarian 716.6. We also see that in D and B configuration, no variance in this source, so a very weak variability. And then in A configuration, we see there are about 7% variability in the P-first density, and the extended first is keep constant. However, we don't see the variability in the integrated first density. So suppose the peak first density indeed vary. I think that we should also see such a variation in the total first density. So we still think that the variation in the peak first density is not real, might due to some artificial effect. Then the final one is the NGC 14593. In the configuration, the variation is very weak. And then in B configuration, we see a huge amplitude of in the variability and in the extended flux density. And this means that there might be some systematic or some background error during this observation. So the variability in the integrated and peak first density is not real, just might be just due to some systematic error. And finally, we see that in A configuration, both the integrated and peak first density show about 10% of variability. And so, this indicate that there is some intrinsic variability and when the source is observed in A configuration. And we also plot the X-ray night curve here. All these three sources show relatively large amplitude of variability in X-ray for about 20 to 13%. And we perform a peer recent cross correlation on the X-ray and radio night curve. And in the radio night curve, we only use the peak first density night curve and observe A configuration for two sources, Macarian 110 and NGC 14593. That we think that their variability is intrinsic, we discussed previously. And so, this image showed the X-ray night curve of Macarian 110 overlaid with the radial night curve that moved to a specific day. We found that there is significant correlation, a positive correlation when the X-ray night curve like the radial one at about 22 days. Thank you. And also a negative correlation when the radial like the X-ray one at about 15-6 days. The same correlation also performed on the NGC 14593. However, we only find very weak correlation compared to the Macarian 110. So finally, a summary. We found radial variability in the Macarian 110 and NGC 14593. There are possible positive and negative time lag between the radial and X-ray phase in Macarian 110. And however, due to the low amplitude of the variability and the short periods of the night curve, we currently cannot reach a conclusion that if such a variability is intrinsic, what is the mechanism that lead to such a time lag? So more simultaneous radio and X-ray monitoring are required in order to confirm this result. We're also interested to find out if there is some Newport effect in radio quiet agent, and such a study can improve our understanding of the heating mechanism in agent coronal. Thank you very much.
Thank you. So there's time for a question or two. Greg's got his hand up.
Sure. So given the lag, potential lags between the radio and the X-ray, do we need simultaneous radio and X-ray monitorings, or do we just need, sort of programs going on so that we are continually monitoring the same source, albeit it doesn't have to be the exact same time?
I think that we need simultaneous radio and X-ray monitoring both in the same time scale. Because this is such a the flux and the arrow, and this case is not something that we can produce by a program. Is the data for the real observation. So we think that we have to need the observation and the simultaneous in radio and X-ray at a similar time scale, probably not exactly the same, but at least at a same period.
Yeah, it would seem that similar timescales are what you really need, and by removing the simultaneity, you may be able to get more things through time allocation committees.
Sorry, can you repeat the question again?
It seems like similar times between observations are what is needed as opposed to the exact same time. And by removing the same simultaneity, you'll be more likely to get through time allocated committees.
Why don't you discuss this?
Yeah, we can discuss this offline.
Offline chat.
Sure.
There is one more quick question from Larry. Did you look at lags for pure noise with a similar power spectrum?
Sorry, is this another question?
Yes. In chat.
In the chat, did you look at lag of a pure noise or similar power spectrum?
Yeah.
No, we didn't. We currently didn't try to look for the lag and the noise, and but we try to measure the amplitude of the noise to check that if there is some background noise or that. We are similar parallel spectrum, but I mean,
just as a null test, yeah.
But I mean, the data currently we have and have a very large error. So in fact, we cannot if such a variability is really, and also the Nike only have a very short time. The period of the Nike is very short. Sometimes if we do the cost correlation, we can move it to somewhere.
Okay, well, we're behind schedule, so thank you.
Thank you.
And the next talk is Victoria Fawcett from Durham, Peculiar Radio Properties of Red Quasars.
Hi. Yeah, hopefully everyone can see my screen. My name's Vicky Fawcett. I'm a third-year PhD student at Durham University, working with Dave Alexander and David Rosario. And I'm really happy to be here today to talk about some of our radio work that we've done on red quasars over the last few years. So just briefly, what is a red quasar? So the majority of the quasar population have very blue optical colors, and this is typically due to an unobscured view of the accretion disk. But we find an important fraction that are red at optical wavelengths, and we call these red quasars or RQSOs. So the red colors typically indicate that the accretion disk is obscured by some amount of dust, but this could be due to an inclined dusty torus or a phase in the evolution of quasars. So I think we've seen both of these schematics in some of the earlier talks. So on the left here is the orientation model. So this is the classical unified model of AGN. And here a blue quasar has this unobscured view to the accretion disk. And then you could imagine a red quasar having this grazing angle through the dusty torus. So in this scenario, a red quasar is just an inclined blue quasar. On the right-hand side, we have the evolutionary scenario. And this is where red quasars could be this potentially earlier phase in the evolution of quasars. And this little comic strip's taken from a press release from a former PhD student of ours, Lizelka Klint, her 2019 paper. And this is just one of the models you could imagine where you start with two merging galaxies, which then produces a lot of star formation, igniting a red quasar, and then through feedback and winds, you then reveal this unobscured blue quasar. So at Durham, we've been really interested to try and distinguish between these two scenarios. So to do that, we use quasars from the Sloan Digital Sky Survey. So these are optically selected quasars. And then we select our red sample as the top 10% of the optical G-I color distribution. And then we also, very importantly, choose a control sample as the middle 50% so that we can actually compare all of our results. And we do this in a redshift dependent manner, as you can see from this plot here. So what kind of kicked all this work off was Lizelka Klint's 2019 paper, as I just mentioned. And in this, she found fundamental differences in the VLA first radio properties of SDSS DR7 red quasars, first at 1.4 gigahertz, 5 arc-second resolution. So I'll just summarize the three key results from her paper. First of all, we find a factor 3 higher radio detection rate in the red quasars compared to typical blue quasars. We find this enhancement arises around the radio quiet threshold, but as you move to more radio loud systems, we don't see any difference between the two. And finally, if you look at the radio morphologies, we find red quasars show this preference for faint and compact radio counterparts. But as you move to the more classic extended and double lobed FR2 systems, we don't find any difference. So these results were really, really exciting, really unexpected, and they rule out the simple orientation model alone, suggesting there's something more special going on with these red quasars. So we don't think red quasars are just normal quasars seen edge on. So since then, we've done a lot of work, and in my 2020 paper, I use higher resolution, deeper radio data to try and kind of expand on a few of these results. So the first survey I look at is the VLA Stripe 82 survey, Hodge 2011. And this is 3 times deeper than first at a resolution of 1.8 arc seconds. So down here, I have a little thumbnail, a 1.5 arc minute cutout from a source in first at 5 arc seconds, and then the same source in the Stripe 82 data. So with this data, we can really probe down to much smaller scale radio emission. And the idea was to use this to test this morphology result. So what we find is that even on these smaller scales, we confirm the previous result. We still find that red quasars have this preference for faint and compact counterparts. But we now actually find a small enhancement, very tentative, in the extended category, which we don't see at the 5 arc-second scales. And this suggests that the enhancement is driven by emission on scales less than about 40 kiloparsecs. So we're talking about host galaxy scale. So since then, we've, in a paper that's just been published by our group, we've used eMerlin data, which is even higher resolution data to really confirm this morphology result. And again, down here, I have a 12 arc-second cutout of a source in first, and then the same source in this really impressive 0.2 arc-second data. So with this, we can probe radio emission down to kiloparsec scales. And what we have this eMerlin data specifically of 20 compact red quasars and 20 compact control. And remarkably, we still find these red quasars are compact down to these extremely small scales. But we also find an excess in radio emission confined to about less than 10 kiloparsecs. And that's what this plot on the right is showing. So this dotted line is the first resolution limit where we don't find this difference, all the way down to the eMerlin resolution limit. So below this, we would call this nuclear, where we still find this difference, but we find a slight enhancement in this, what we call galactic scale as well. So this was really interesting. And these small scales could suggest these red quasars are in a younger phase, as you've probably heard in previous talks. So the next survey I look at is the VLA Cosmos 3 GHz survey from Smolchik 2017. And this is 30 times deeper than FIRST at 1.4 gigahertz. So with this, we can really start to constrain the origin of the radio emission as either AGN or star formation. So to do this, I look at this radio loudness plane again, that similar to the Clint 2019 plot, which I have overlaid in this pink color. And just to note here, radio loudness, we define as the ratio of the 1.4 gigahertz luminosity to the 6 micron luminosity. And that's because 6 micron luminosity is less affected by extinction, which is important for red quasars. So although we don't have a great source statistics in these smaller samples, what we find is we confirm this result, we find this peak around the radio quiet threshold, but now we have this deeper data, we can push to much more radio quiet sources. And we find this sharp decline, which we weren't really expecting. So we wanted to then investigate what causes this decline as you go to this really radio quiet end. So to do this, we use the wealth of multi-wavelength data available in the Cosmos field, and we can actually split this lower spin into sources that are either have their radio emission dominated by star formation or AGN, using the infrared radio correlation. And although we have very few source statistics now, we've had this tentative evidence that the star formation dominated quasars have an enhancement consistent with unity. So what we think is happening is this decrease, less than a radio loudness of -5, is due to an increase in the relative contribution to the radio emission from star formation. And we actually have an ALMA study that's in the process of being written up, where we don't find any difference in the star formation properties between red and typical quasars. So what we think is happening is this enhancement in the radio is driven by some kind of AGN process. So what AGN process? Well, there's a lot of work been going on to what drives radio quiet emission, and it's quite difficult. It could be differences in the accretion properties, winds, or small scale jets. And in the interest of time, I'm just going to focus on the first two, which is something I'm exploring in my latest project using optical to near infrared X-shooter spectra of a sample of red and typical quasars. So first of all, with this X-shooter data, quite an important result is that we confirm that the majority of red quasars, well, at least our red quasars, are consistent with dust reddening. So what this little movie is showing in the blue is a control composite, and then we're adding different amounts of dust, which you can see in the bottom right. And what you can see is that just adding dust to this composite, we can recreate the shape of the majority of the red quasars very well. So we think dust is behind the red colors. We want to look at accretion properties. So to do this, we fit a thin accretion disk model to both the red and the control quasars. And what we find is that the majority of both the red and control sample can be fit very well, thanks, with this simple thin accretion disk. And we also find no significant differences in the mass accretion rate or the spin. So we don't think there's very different, many differences in the accretion properties between the two. We do we are starting to find a lot of evidence for wind. So for example, in a paper earlier this year by Gabby Calistro-Oliveira, she finds broader O3 wind components in the red quasars compared to blue quasars. In my X-shooter study, I find tentative evidence that for any given black hole mass, red quasars have higher Eddington ratios, and this would mean potential accretion disk winds. And in another study that we're looking at, we find this curious link with BAL quasars, so broad absorption line quasars known to host powerful outflows. And in previous studies, BAL quasars have been found to be more radio detected and slightly redder. But what we find is that even when we remove the BAL quasars from our red quasar sample, we still see the radio enhancement. So this tells us the presence of dust is key to this radio enhancement. So in conclusion, we find enhanced radio emission in red quasars around the radio-quiet threshold. There's a preference for compact radio emissions, so less than 10 kiloparsecs. We think it's driven by AGN processes, but it's potentially not due to differences in the accretion disk properties. And dusty winds is one explanation. And obviously it can be a combination of these. It's a little bit complicated. So in my future work, we have GMRT data of 20 red and 20 control, the same sample we did the emailing study on. So we're going to look at radio SEDs. And again, there's been a few talks about that today. So we're really keen to have a look at that. And we also have JVLA data to do some high frequency radio spectral slope analysis. Thank you.
Thank you. So time for a question, or if they're quick. So Sandor asks, do you have VLBI data or plan even higher resolution observations?
So we don't, but that's something that basically is the next step. We really want to have VLBI data of some of these to probe even further down. And we're thinking of taking these, probably the email-in sample and having a look with VLBI. But yeah, that's definitely the next step in this study.
Okay. Okay, well, thank you.
Thank you.
And our final talk of the morning is Heinz Andernach talking about giant radio galaxies in the VLAS.
Hello, can you hear me? I've just started to share screen.
And we see
going to full screen mode. Oh, wait a minute. Okay, I'm sorry.
There.
Okay. There's something. Yeah.
Yep.
Okay.
You're good.
So my name is Heinz Andernach. I'm working at the Department of Astronomy in University of Guanajuato in central Mexico. And this work has been done over the past 3 years with my summer student, Jonathan Guerrero Gonzalez, who studies at Puebla. So since this is a meeting of reminiscence, I will share a few, just one. My first observations with the VLA were in 1981 when I was living in the guest room on site. I returned for data reduction in July 1985, but signing up for computing time, I tried to avoid the wolves that were described by Rick Perley. And as a result, I usually got time at 2 to 4 a.m. in the morning. So as we saw in Farhad Youssef Sadeh's talk yesterday, here's a painting of the ape's cage. I only want to mention that there was a small error in that painting, in that at the time when Farhad was looking at his filaments of the galactic center, I was actually by his side and was reducing my own observations, flagging bad data. And upon looking at Farhad's ape's TV screen, I asked him, how would you get rid of these interferences, which are the diagonal stripes over the screen, which I've never seen. So months later, I felt with Einstein that question was possibly my biggest blunder, but I was happy to hear yesterday that even Farhad was not sure what he was seeing at the time. So back to the topic. What is VLAS? Well, we have heard enough of this yesterday. What I want to emphasize here is mainly the division in time in 6 epochs, where 2 of each cover the whole sky. And when the survey started in 2017, I was interested in what one can see in these images and what one can see, especially in areas that had not been covered at high resolution before. And this area turned out to be the North Celestial Pole, north of about 64 degrees declination, where FIRST hadn't covered this area yet. So what are giant radio galaxies? First of all, from the angular size of a source U and the host's redshift, either estimated or spectroscopic, you obtain its distance, and from that, the largest linear, always projected size, which is usually called the LSS. And the LLS, sorry. So originally in the old times, when the Hubble constant for 50 was in fashion, people used the threshold of 1 megaparsec, but more recently, authors adopt a threshold of 700 kiloparsec for a Hubble constant of 70, although there's no physical reason for that. So how many giants are known by now? I'll give a summary of the main compilations and recent listings. So we have about 700 such radio galaxies larger than 700 kiloparsecs. The graph only shows those from a compilation by Kuzmich published in 2018. But in parallel, since 2012, my students and I have found about 7 times more such giant radio galaxies from public surveys, but this is not published as yet. So why would one look for giant radio galaxies in VLAs when everybody knows that VLAs would deliberately lose sensitivity for extended emission? Well, we had the surprise from the first survey and from the Radio Galaxy Zoo project, when Radio Galaxy Zoo volunteers actually pointed us to more than 200 new giant radio galaxies that they found by visual inspection and follow-up from the first images. Now, FIRST only covers a third of the area that is covered by the NVSS. So the contiguous area covered by VLAS that was not studied in high angle resolution before turned out to be the North Polar Cap region, north of declination 64 degrees. And in this region, at the time we started this project, the surface density of giants was actually 7 times lower than in the region that was well studied by FIRST and SDSS before. But now, at the time, new optical surveys like PanSTARRS and DESI and infrared surveys like AllWise gave us the hope that we could identify faint hosts in even this region outside the SDSS area. And another thing not thought of it then, but still true now, the North Polar Cap is still not covered by the LOTS, the LOFAR DR2 survey, which will be published in late 2021. So the history of our project starts in my Easter holidays of 2018, when I decided to inspect 2,000 quick look images, or 90% of the North Polar Cap area, clicking and logging over 3,000 potentially extended sources by using Bill Cotton's OBIDU, which has 2 options to log the sources. One is by Gauss fit, which I used for likely radio cores, and normal clicks that I used for suspected centers between potential lobes. The good news is that the quick look images are virtually empty in the sense that it takes only about 50 seconds per quick look images, or about 30 net hours to go through all the 2,000 images. Happily, in July 2018, I got the help of Jonathan Gonzalez to follow up on these 3,000 clicks. So our question was mainly, how close to the galactic plane can we see hosts? How many typical shapes of Mach cones that would reveal radio galaxies could we see? And we also used the NVSS to confirm possible radio bridges between very separated potential hotspots on the VLAS images. So in July 2019, actually the missing 90 quick look images to cover the whole NPC area was completed, and Jonathan actually spent a second internship with me. So not surprisingly, most people would expect giants to be unrecognizable in VLAS, and yes, here is an example of a very large radio galaxy, very much burning the screen in NVSS and invisible on VLAS. But I have to emphasize here that the mere inclusion of VLAS data allows us 2 important things. One is to identify the radio core, which I hope to see you see my pointer is pointing at. And secondly, most importantly, the type of radio galaxy must be a remnant radio galaxy, because the lobes are generally diffuse and without any hotspots. So how would known red giants look like in VLAS? Here's an example from comparing a deep VLA image from a radio galaxy found originally in the Westerbork-Wentz survey over 20 years ago. And I must say that in VLAS, this radio galaxy of 4.3 arc-minute size is well recognizable, not with all its structure, but clearly nobody would fail to see this on the VLAS image. I have to speed up a little. So here's an example of radio galaxy candidates found with a suspected core, which is about half of all the objects. So here was the discovery image, the VLAS Epoch 1 image, where I thought there was something fishy around that very central spot. And in fact, NVSS confirms that there is something diffuse, and later on, a combination of a mosaic of epochs 1 and 2 confirms the diffuse lobes with actually two peaked lobe, very diffuse and on the southern side. Radio galaxies without a radio core are very frequent, almost half of them, but the very characteristic Mach cone type shapes around hotspots motivated me to click at the center of these two radio sources. And later on, by private communication, I got an image from the LOTS DR2 survey, which is going to be published later this year, which confirms the bridge between the two objects. NVSS is not very conclusive, but the bad news is that the Pan-STARRS image wouldn't show any optical host at this geometric center. The good news is that I got lucky that the DESI DR9 image survey provided me with very faint objects, one of which I think is the most likely host, making this giant radio galaxy of 880 kiloparsec. In general, FR2s without a radio core are frequent, and my strategy here is to look for AGN-like hosts with wise colors adequate for AGNs. The largest giant that we found with the help of VLAS is shown here. This was actually recognized by another summer student already on NVSS, but at the time we didn't have the complementary data to point to the host. We found also a few cases of very weird radio morphology. Yeah, okay. So I'm going to skip a few slides. Here's an example of an attempt to find remnant radio galaxies from an automatic search in the NVSS catalog by looking for extended sources pointing at each other. And we found many cases where VLAS clearly points us to the host. Another summer student, as I mentioned, had clicked on many candidates in the NVSS, which we couldn't resolve because of the lack of Pan-STARRS and DESI at the time. So this has led to another about 50 or 80 giant radio galaxy cases. So I will skip this again. I also inspected the Canadian Galactic Plane Survey, which covers a part of this region, and I added further candidates in the NPC region. So to summarize, the known list comparing the known giants versus the new ones that we found shows that depending on the linear size range for the real giants, to me, larger than 1 megaparsec, we managed to increase the number of objects by a factor of 5, but for the smaller ones, because they are not generally recognized in literature, we found factors of between 15 and 23. In general, there is a lack of spectroscopic redshifts, but the photometric redshifts are generally sufficient. So we also found that we could go down to the very close to the galactic plane in finding the hosts. Another interesting feature is that the published giants until now have a median redshift of 0.2. The giants that we found with the help of other surveys like NVSS and TGSS, or plus the help of VLAS, have a median redshift of 0.5. And VLAs only, the ones that are only found in VLAs, originally found, they actually go to a median redshift of 0.7. So we'll skip that also, and I will concentrate on a major find that summarizes my whole compilation of now well over 3,000 safe giants larger than 700 megaparsec. One thing that surprises me and that is a bit contrary to expectation from standard cosmology is that the median linear size does not significantly decrease with redshift as we would expect from standard cosmology. And I summarize the essential formulae in here. So, and by the way, I already came across 5 3C sources where the net database had a significant shift of the position of the optical host. This is my last slide, and I want to emphasize here that since Stephen is the moderator and he's responsible for the HIPS versions available for the quick look images, it would be very useful to have epoch 1 and 2 quick look average images online. Second thing is that the VLAS images many times reveal the radio cores at a very low significance level, so low, but still visible that they are not included in the existing VLAS quick look source catalogs. Contrary to, a bit contrary to what Catherine told us this morning, jets are actually very rare in giants. I have a suspicion why that could be. And I skipped several others and want to finish with the statement that actually in line with Ron Eaker's talk yesterday, the VLAS survey certainly produces results that it was not designed for. And I stop here. Thank you.
Thank you.
Taking questions if there is time.
Before questions, people should stick around for the photograph. Amy notes it's a good example of combination NVSS and VLAS. That's nice. Greg points out there is issues at, I think, in the north for the mosaics. I think you're well aware of those.
Okay.
And Jean's happy to see the GRG work. Nice.
Okay.
And
so
I take note of your request for a co-added HIPS image.
Thank you.
I still have a half year to do that. So.
Okay. I'm happy if it appears after finishing 2.2. So I'll stop sharing here.
Yeah, well, thank you. And turn it back to Anna, I guess.
Because we're trying to take a lot of photos to make sure that everyone can be in a photo, even if they are just joining for one or the other session. Please, whoever would like to be in a photo this time around, please put on the video and I'll do the screenshots. And of course, I'll collate it all together. I'll take multiple pictures. I'll probably take the best one. You have to, you have to just trust my judgment. Okay. Thank you all. And I guess I'll, as I've been preaching for the past few days, if you have not claimed yet your gift bag, the celebratory free gift bag, please do so. If you have the first time you hear about that, let me know, and I'll post the notes about that. And other than that, or maybe I should ask, is there anyone here that has not have yet heard about the gift bags? Okay, apparently everyone did. Okay, great. So if there are any issues, do send us an email at vla40@nro.edu and then we will help you. And other than that, I think the next session starts at, oh my goodness, in 15 minutes. And any speakers that like to test their screen sharing, I think Amy, I've just seen Amy Miroszewski, she'll take
Yeah, I'll help with that. So
Cool.
Anna's gonna go on a break and I'm going to help out with that.
Thank you, Amy.
So who's gonna test their talks?
Me.
Okay, go ahead, Danielle, first.
Okay.
Amy, a quick thing. If I don't manage to be back in 15 minutes, just make sure you press the record. I forgot to mention it to you.
Right.
Okay. I'll make you a host just to make sure you can do everything.
Yep, thank you. Okay, it looks good, Danielle.
Looks good, okay.
And then there was a couple other raised hands.
Amy.
Okay, let's do Jackie Hodge first. And then Hanson.
Okay, thanks. I'm gonna.
Okay, we're seeing a display. I mean, we're seeing the speaker mode. There we go. Yep.
Yeah. Okay.
Looks good.
Thanks.
Okay, Hansung.
Sorry, I have some problem with line now. Okay, so let others first.
Okay, Larry, did you want to go?
I'm trying. Okay.
Yep,
we're
that looks good.
Thank you.
Okay, is there anyone else?
Yes. Can I try that?
Yeah, go ahead.
Oh, yeah, okay. Where is my share screen?
Ah, Min.
Yes.
Okay.
That work okay?
Yep, that looks good.
All right then. Okay, done. Thank you.
And then Tom Scott wanted to share.
Oh, thank you.
It would be useful if people would put their hand, raise their hand thing. That's extremely useful. Yep.
Oh, great. Thank you.
Good. Okay, Hansung, you want to go try again?
Yes, thank you. Can you see my screen?
Yes.
Okay, thanks.
Okay, is there anyone else? Okay, well, I'll be here during the whole break. Okay, someone else comes. I'll keep an eye on who is actually here.
Hello. Gonna quickly test out.
Sure.
Thank you for the reminder.
No worries. I was just looking at who was here.
Let me find it. Too many windows. This
Yes.
is good. Oh, is that? No.
That's the right thing. Yeah.
Okay, awesome.
Why don't you hit play to make sure that it. Yep. Okay.
Awesome.
Great.
Thank you.
you. Is there anyone else who would like to test their talk? Is there anyone who would like to test their talk in the next few minutes, in the next minute or so? Jin, are you going to chair the first part of the session?
Yes.
Okay, I think.
And I pass it to Vinny after each song's talk. Do you have any announcement?
I do not. Nope. So I think it's probably okay to start in the next.
Do we want to start at 12:25 or 1 hour? I think we are 5 minutes early, but.
In the schedule I have, let me look. It says 12:20, but I will check.
Oh, really? Okay.
Yeah, well, but it appears to be an error. So let me check the one online, which I will do. Right. So I think it is a mistake. So right, we want to test. We want to start in 5 minutes. Yeah, the paper one that I have. Oh yeah, look, it says okay. No, the error was just in the one the break was. So yeah, 5 more minutes.
Okay.
So thank you for bringing that up. So we have several more minutes to test talks if anybody would like to test their talk. Okay, I'll make the offer one more time. If there's anybody who has showed up in the last few minutes who would like to test their talk for the next session, please speak up or put your hand up.
Okay, I think it's time. Shall we start?
Yeah, go ahead.
Okay, good. Yes, so I am Jin Koda and chairing the next session with Vinny Sebastian. I will cover the first half, and there are a lot of interesting results from VLA, and this session is again very packed. So all the speakers, please stay in time, and if you have any questions, you can type in your questions in the chat box or Slack. But I prefer you raise your hand so that I can let you unmute and ask the question. Okay, so the first speaker is Jackie Hart, and she will talk about the high redshift star formation. Jackie, please take it away. I think we see the presenters of you.
Yeah, I haven't started
okay.
yet. So hopefully this will work.
Okay, yeah, this is good. Yep. Good.
Yeah, okay, good. Okay. All right, well, I just want to start by thanking the organizers for inviting me. and also kindly agreeing to move my talk a little earlier in the schedule given my time zone. I also want to thank Jim Condon, who I think is the speaker who very generously switched spots with me. So I'm really humbled to take part in this 40th anniversary conference with so many of the pioneers in this field, as well as those who keep the VLA running all these years later. The VLA really holds a special place in my heart, and I feel so fortunate that it's played a huge role in my research over the years. So today I'm going to talk about the VLA's past, current, and future contributions to understanding a high redshift star formation. And in particular, I will focus on studies tracing the total amount of newly formed stars in distant galaxies, as well as those tracing the cold molecular gas that we now understand is the main factor in driving the overall history of cosmic star formation. Oops, no. Sorry, having a bit of technical issue for some reason. So you get a brief preview of everything I'm going to talk about. Okay. So first, a brief introduction to the history of cosmic star formation. So one of the major goals of extragalactic astronomy is to quantify how galaxies formed their stars over cosmic time. There's been a huge amount of effort put into this over the last 20 years or so. And through these efforts, we now understand that the star formation history was around an order of magnitude higher at redshift 2 than it is today, and that it declines again out to the highest redshifts. More recently, there's also been a huge push to try to understand why the star formation history behaves as it does. And in particular, we know that molecular gas is the fuel for star formation. And thanks to recent efforts, we've placed increasingly tight constraints on the evolution of the molecular gas density with redshift, which you see here from a number of different surveys. So these studies generally find a qualitatively very similar redshift evolution as seen in the cosmic star formation history. And this emphasizes that the amount of molecular gas is really the key factor. So I now want to back up and provide a little more context about how we got to this point, and also the role that VLA has and continues to play in constraining both the molecular gas and the star formation in galaxies out to high redshift. So it's important to keep in mind that it wasn't until the early 90s when the first redshift greater than 1 galaxy was detected in molecular gas. It was a quasar, which is the red histogram shown here. And it wasn't until the late 90s when high redshift galaxies other than quasars started to be detected in molecular gas. And the VLA plays a really important role here because due to its frequency coverage, it's able to detect the low J transitions of carbon monoxide, which have historically been the best way to trace the total molecular gas reservoirs in these high redshift systems. And not just that, but the VLA has the ability to resolve these gas reservoirs. And because of that, the VLA has really been at the forefront of molecular gas detections at high redshift. Here you see 2 examples of some of the high impact early work from the VLA in this area. On the left, you see the beautiful sub-kiloparsec VLA imaging of CO 2:1 in a redshift 4 Einstein ring. This was providing the most direct evidence at the time for active star formation in the host galaxy of a high redshift quasar. And on the right, you see the VLA CO 3:2 imaging of a redshift 6 quasar host galaxy, which was the highest redshift known quasar at the time. Now, resolved molecular gas observations are becoming more and more common with ALMA, and the latest results are finding evidence for regularly rotating disks, even at very high redshift. But the VLA did this already a decade ago. So here you see the redshift 4 sub-millimeter bright galaxy GN20 imaged in CO 2:1 emission at 1 kiloparsec scales and showing a spectacularly resolved rotating gas reservoir. And the VLA really is still the instrument for detecting and resolving low JCO at high redshift, as well as the low J transitions of the dense gas tracers like HCN, HNC, HCO+. Here I'm showing a couple examples from my group's recent work. On the left, you see some kiloparsec scale imaging of the CO 1 to 0 in a redshift 3 submillimeter galaxy. This is some of the highest resolution CO 1 to 0 imaging of a high redshift star forming galaxy that's unlensed. And on the right, you see a detection of HCN 1 to 0 in a redshift 2 strongly lensed submillimeter galaxy. This is only one of about 3, I believe, detections of this important dense gas tracer at high redshift. So these are just a couple of examples, but the VLA continues to really push the frontiers of what we know about molecular gas at high redshift. And in addition to molecular gas, the VLA also plays an important role in detecting the dust unbiased star formation in distant galaxies. And this is important as studies of the star formation rate density need to take into account the dust obscured star formation, but tracing that component is quite challenging. So for example, here you see a comparison from a few years ago of the rest frame UV measurements in blue with the infrared and submillimeter measurements tracing dust obscured star formation in orange. So infrared and submillimeter observations can directly trace the dust obscured star formation, but are generally much more challenging to obtain at high redshift, even with ALMA, though progress has recently been made using large and shallow mosaics at 2 millimeters, for example, like you're seeing on the right here. And this is another area where the VLA has and can continue to play a crucial role. And it can do this in 2 ways. It can detect radio synchrotron emission in high redshift galaxies, which is thought to be a relatively good tracer of the dust unbiased star formation, as long as you're careful to weed out the AGN. And it also has the potential to detect free emission in high redshift galaxies, which is both relatively unaffected by dust attenuation and can be directly related to the H2 regions that contain the young stars. So this has been studied more extensively in local galaxies, including by many in this conference, but it's much more difficult to detect at high redshift, as it's really in the faintest part of the spectrum that you're seeing here. So these 2 tracers are really complementary tracers to those that you saw on the previous slide, with a caveat that you do need relatively deep radio surveys with a sensitive telescope in order to actually detect star-forming galaxies, and not the AGN that dominate at brighter flux densities and which we may associate with the radio surveys that we all grew up with. But luckily, the VLA is really unmatched in its sensitivity. And so efforts to use the VLA to trace cosmic star formation with synchrotron emission have already been going on for some time. I'll show a few efforts along these lines using increasingly deep VLA continuum surveys. So the first examples I'm showing here were done with the 1.4 gigahertz VLA Cosmos survey, which was able to trace the star formation history out to about a redshift of 1 with individual detections on the left, and then out to about a redshift of 3 via stacking. More recently, the 3 gigahertz JVLA Cosmos Large program has pushed these efforts out to even higher redshift, as you're seeing here, on the left for individual detections and on the right with stacking. So this survey has led to some really fantastic work, which was highlighted already in a couple of the talks we saw earlier today. However, due to its wide area design, the survey really only amounts to a few hours per pointing. And it's not reaching the depths required to really detect main sequence galaxies at high redshift or to attempt to detect the free emission. So that brings me to the VLA's present. And in particular, what I'll talk about now is some current work using 2 recent ultra-deep VLA surveys that are designed to study the cold molecular gas and the dust unbiased star formation at high redshift. So the first survey is Cold Z. And COLD-Z was designed to study the cold molecular gas in blindly detected high redshift galaxies by targeting the CO 1-to-0 transition at a redshift of 2.5 and the CO 2-to-1 transition at a redshift of about 5.5, and doing this blindly. This survey had a wedding cake design with deep coverage in the Cosmos field and a wider and shallower mosaic in the Goods North field. And due to the need to go fairly deep to detect these CO transitions blindly, we had the added benefit of getting ultra deep 34 gigahertz continuum emission for free. And the second recent survey I'll discuss is Cosmos XS, which is a survey designed to reach sub-microjansky RMS levels in both the X and S bands. This was designed to be matched in resolution at about 2 arcsecond resolution and matched in frequency weighted depth, and to overlap COLD-Z in the Cosmos field, and thus to be an ultra deep survey of the synchrotron and free emission. So COLD-Z allowed us to put the first detailed constraints on the shape of the CO luminosity function, which you see here at a redshift of 2.5 for the Cosmos and Goods North fields separately. That's what's in the left panel, and for the combined constraints from the 2 tiers in the right panel. We found general agreement with the higher J CO surveys that are now coming out of ALMA. But COLD-Z was able to probe a much larger survey volume, and by detecting directly CO 1-to-0 at redshift of 2.5, it was able to do this without relying on uncertain CO excitation corrections. So by integrating the CO luminosity function, then we found that these measurements are in agreement with an increase of the cold gas density from a redshift of 0 to a redshift of 2 or 3, followed by a decline out to higher redshifts, C of 5. And this suggests a first order that the star formation history of the universe simply follows the evolution of the molecular gas supply in galaxies, which is itself regulated by the gas accretion efficiency and the feedback processes. So we've also just published the first 2 Cosmos XS papers led by 2 of my PhD students here in Leiden. So this is very exciting. Here you see the radioluminosity as a function of redshift and translated into star formation rate on the right-hand axis with the 3 gigahertz detected sources overplotted. So as designed, Cosmos XS traces the dust unbiased star formation in galaxies with star formation rates down to about 100 solar masses per year or less out to a redshift of 3 using radiosynchrotron emission. And this corresponds to main sequence galaxies out to redshifts of 3 and starburst galaxies out to even higher redshifts. So we've used Cosmos XS to measure the radio source number counts down to a detection threshold of a few microjanskys. These are the black data points that you're seeing here. And these ultra faint number counts suggest a steeper luminosity evolution for the faint star forming sources than predicted in previous generations of semi-empirical simulations. So our measurements are more in agreement with the latest semi-empirical predictions from T-Rex, which you see here with the purple line from Benaldi et al. So this purple line is not a fit, but it does match the data quite well. So this is quite nice. And it also agrees with what has been found by previous P of D analyses, but here now with direct detections. And my student Hito has led the decomposition of the sources into AGN and star-forming galaxies. So we identify multi-wavelength counterparts to 97% of the sources, and then we use a variety of multi-wavelength AGN indicators as well as SED fitting to identify AGN. And we find that the fraction of sources whose radio emission is affected by AGN activity drops off steeply at low flux densities, such that the fraction of sources that are star forming is nearly unity. at the lowest flux densities that we probe. And this means that our radio sample is strongly dominated by the star forming population, which is what we expected. But of course, it's nice to see this borne out in reality. And it also, requires a paradigm shift for those of us who are used to thinking of radio surveys as primarily surveying AGN. There are a small fraction of sources which have only far infrared detections and some which have no multi-wavelength counterparts at all. We believe the majority of these are robust based on detections in multiple radio frequencies. So we do a stacking analysis of these sources in optical, near infrared, and radio wavelengths. And we find that these sources are likely to be at high redshifts of 4 to 6. So this would imply high radio-based star formation rates of a few hundreds of solar masses per year, which would mean that these sources contribute appreciably to the cosmic star formation rate density, but would be missed by optical surveys. Recently, HITO has also been working on combining the Cosmos XS and Cold Z programs, as well as with some of the other deep data in the fields. And the goal is to study the composition of the radio spectra to constrain the thermal fractions and try to determine free based star formation rates. So this is very challenging even with such deep data, but here you see a couple examples of individually detected sources where we're able to do this. On the right, you see the thermal fraction at 34 gigahertz as a function of redshift for our sources. The solid line is what you'd expect based on Jim Condon's 1992 model. So we find thermal fractions comparable to this local model, but now in galaxies out to a redshift of 3. And our free based star formation rates are also in agreement with star formation rates from, for example, the far infrared radio correlation. We also push this a step further with multi-frequency stacking in order to probe the radio spectra of the typical galaxy population during the peak of cosmic star formation. So here you see some stacked detections at 1.4, 3, 10, and 34 gigahertz, which allows us then to try to decompose the radio spectra. When we do this, we're able to try to put the first constraints on the cosmic star formation history using free emission, rather than the typically used synchrotron. And so here you see the stacked bin averages for different stellar mass spins around the peak epoch of galaxy assembly, where in general we find good agreement with existing synchrotron-based measurements, but using an arguably more direct star formation tracer. I see, I only have a couple minutes left. What we're currently working on is determining the radioluminosity function for star-forming galaxies as a function of redshift, which I'm showing here. By combining our survey with the wider but shallower JVLA Cosmos survey, we can put even tighter constraints on the luminosity function evolution, which are the black points here. So this paper is still in progress. But it will ultimately also provide new and even tighter constraints on the dust unbiased star formation rate density traced via radio synchrotron emission. And looking ahead, we have a number of exciting new projects coming down the pipeline in addition to what we have planned with Cosmos XS. So a few of these I'm listing here. We have an approved L-band addition to Cosmos XS, name TBD, perhaps Cosmos XSL. We have an approved multi-band sub-kiloparsec imaging campaign of a strongly lensed galaxy to attempt to resolve these different processes, the synchrotron emission and the free emission on sub-kiloparsec scales in a galaxy all the way at a redshift of 3. We have an approved legacy library of molecular gas at high redshift that its goal is to more than double the number of high redshift sources with CO 1 to 0 detections, really crucial for really constraining the total molecular gas mass in these high redshift sources. And we have an approved program to attempt to detect CO in the highest redshift ULERG to date, at a redshift of 7.3. So these are all really exciting. Of course, the NGVLA is really the future. So pushing to higher redshift and even more normal galaxies, of course, requires even more sensitivity than what we've achieved here. Yeah, luckily detecting the gas and dusty star formation in these galaxies is one of the key science areas for the NGVLA. So in summary, the VLA has really been at the forefront of efforts to study the molecular gas and dust unbiased star formation in galaxies out to high redshift. I discussed 2 recent ultra deep blind surveys, Cold Z and Cosmos XS, that really push these efforts to higher redshift and fainter luminosities than before, as well as providing new constraints on the first constraints on the cosmic star formation history using free emission. And there are many new exciting projects in the pipeline, with the NGVLA, of course, being the most exciting thing to come. Thanks.
Thank you very much. And thank you very much for staying on time. Any question? Please raise your hand if you have any question. Okay, while you are thinking, I have a couple of questions about NGVLA. So you mentioned about the prospects of NGVLA, but I want to know a little bit more. So optically dark high redshift objects, that's very interesting. Do you think we can detect line emission from those objects with NGVLA and determine the redshift? And the second question is normal galaxies. We are currently analyzing them with stacking, but can we study them without stacking with NGVLA?
Yeah. So yeah, regarding detecting line emission from the optically dark sources, I mean, so the optically dark sources are something that's like a bunch of people are super interested in right now, also from the ALMA perspective. Yeah, there have been some attempts to try to get redshifts for them. Of course, it helps if you can constrain the photo Z somewhat. As you saw, the ones in this particular, so this method of identifying them, the radio selected ones, we only can do kind of a stacked PDF, and it's quite broad. So we can say that probably many are kind of between these redshifts, but it would be a little difficult to have like a targeted line scan. Maybe we could do a blind line scan and try to detect them. If they have the star formation rates that would be implied by the radioluminosities, then they should be potentially rather gas rich. So it might be possible, but I would have to do the exact calculation for how long we would need. But yeah, obviously detecting the low JCO transitions with the NGVLA is something that we've been hoping to do. And your second question was
normal galaxies without stacking.
Oh, detecting normal galaxies without stacking.
Without stacking.
Yeah. So I mean, that's what we argue that you can do with Cosmos XS. Of course, the statistics are really small, right? So you could detect a normal galaxy at redshift of 3, but there are not going to be very many of them in the field. So it is possible. And of course, then, with the NGVLA or SKA, you'll be able to push this out to higher redshift.
Okay, thank you. So Min has a question. Could you unmute and ask?
Hi, Jackie. It's a very nice talk. I have a question about your Cosmos XSL project. So you have a very nice S and X band data. What's the motivation for L band data? And I don't know whether that field overlaps with Chili's field or not, Chili's control field. Depth is there, but we don't have the resolution.
Yeah, exactly. No, it doesn't. So we checked this. Unfortunately, kind of due to the design, so yeah, the Chili's is a bit south of where the Cold Z and the Cosmos XS are centered. So we wanted to overlap with Cold Z. That meant we had to sacrifice a little bit on the L band. So most of the area that we have, the deepest L band that we have, is still from Ava Schinner's VLA Cosmos program. So that was the motivation for getting an even deeper L band. It's actually pretty efficient, and those observations were partly observed, I believe. But even with the hours that we got, which is not the full hours that were requested, it's already deeper than the VLA Cosmos program. So it can help with decomposing the radio spectra, for example.
Okay, let's move on to the next speaker. If you have any questions, you can type into chat or in Slack. Okay, so next speaker is Daniel Lucero, and she will talk about H1, H2 transition in elliptical early type galaxies. Hey, Daniel, take it away.
Is Daniel muted?
Yeah, you're muted. Daniel, you're muted.
Sorry about that.
Yeah, we can hear you now.
Classic blunder. Okay, sorry about that. Yes, hello everyone. Today I'm just going to give a brief update on a project that I've been doing for a very, very long time. Letting me go to the next. Can you guys see yourselves in my screen? Okay. Anyway, a project I'm going to tell you about, the original goal was to use H1 and CO observations of early type galaxies to stress test the existing empirical and physical models of molecule formation. So the big picture question is, what are the conditions that facilitate the conversion of H1 into molecular gas? Okay, so this question really has been thoroughly explored for disk galaxies, mostly through two different methods. The first and probably the best method being the first principle approach, which you can take physics and model the chemical process and the physical processes that will regulate the balance between the formation and the formation of molecules and their dissociation. So these studies, which I'm not going to go into in depth, and I've only listed a few of them here, but they generally tend to find that the metallicity, hydrostatic pressure, and UV emissivity are really the dominant factors in determining how much gas goes into the atomic versus the H2 phase. And it is really thought that the pressure is especially critical because it's directly proportional to the gas volume density, which will affect both the rate at which the H2 forms and the probability that you're going to get gravitationally unstable dense regions within your turbulent ISM. So it also turns out that there are empirical relations out there, and really they come from the physical models. And if you want to go back to the very beginning, one of the first models was physical models was made by Bruce Elmgreen, and he predicted that the molecular fraction indeed is dominantly determined by the hydrostatic midplane pressure and this stellar volume emissivity given by J, which itself is a function of metallicity. So you still have those three components in there. So if you think about the pressure is proportional to sigma squared with the velocity dispersion of the cold gas, and that velocity dispersion is proportional to the emissivity, then you can get a relation that has a slope of about 1.2. So astronomers went out, specifically this Leo Blitz and Eric Wazowski in 2006, and gathered some data to see if they could see whether this empirical relation predicted by the physical models exists. So here's their first attempt at that, or the first attempt at that, 13 nearby spiral galaxies plus the Milky Way. And indeed, as you can see, that they find a relationship that is nearly linear. It's not perfectly linear, but it's nearly linear. Okay. This was followed up by the way, this was also a VLA observations. I believe they're D observations at the time. And this work was followed up by Adam Leroy and his collaborators using things data, which of course is much higher spatial resolution. And more or less, they get the same relationship, albeit slightly lower slope. Okay. So the empirical relationship and the physical models seem to do a fairly good job of predicting what the molecular fraction is in actual observations of disk galaxies. And because of that, that's very nice, and we can use them as an input into cosmological simulations. And so that's typically being done. But the question is can you use, for instance, the empirical model derived for disk galaxies and to represent all morphological types? And so that was the question we set out to answer. So if you think about the difference between early types and disk galaxies, well, they have very different gas contents, different stellar populations, much older stellar populations, different evolutionary histories. They tend to have very low H1 surface densities. So my particular survey and the LSCD surveys show that surface densities, at least at 50 and 15 arcsecond resolution, never seem to reach densities above 5 solar masses. And those that do are lenticulars with a large amount of dust and gas, molecular gas. So they have a wide range of H1 and H2 content. Some will have lots of H1 and no CO, and vice versa. And sometimes they have both in good quantities. So there's a large range there. Their central gas and stellar densities can be typically larger. So it's now an elliptical distribution of stars instead of being embedded in a disk. So large central stellar densities can translate to higher pressures. They may have higher metallicities that can range from 1 to 2.5 solar, and much lower UV field strengths from lower amounts of star formation, at least large stars being formed. So in the case of these higher pressures and metallicities and lower UV fields, the models will predict, the photosystem models will predict a larger molecular fraction. So this is one of the reasons why early type galaxies are very good for testing H1 to H2 physics. So our first attempts at this, when I first started, was Lisa had gathered basically some H1 data at C-array for 11 of the most CO-rich early types that existed at the time. And I think it's probably still true. They are among the most CO-rich early types known. They have a range of morphologies. So there were 6 S0s, 5 ellipticals, range of distances from Virgo to basically 80 megaparsecs. And they were in a range of field, cluster, and group environments with a range of optical luminosities, as you see there. The important thing is a lot of people used to tell me that if they have gas, they're not early types. Well, these ones are classified early type. They have an Artem 1.4 classification in several catalogs. We had prior knowledge of the location of star formation from Spitzer data, 22 micron we had, and 5 arcsecond continuum data from the VLA, which was nice. And again, with Lisa's efforts, she had obtained some VLA C-array data for all the ones that were detected, basically. And that was complemented by CO maps from BIM, okay, that were about 5 to 7 arcsecond resolution. So it's not exactly matching, which is preferred in this type of analysis, but this was the best we could do at the time. So this is an example of the data. So these are the 6 H1 detections. The other ones were not detected. So you can see the H1 in black contours, and the CO from BIMA here is in white. So the H1 distributions are actually quite well resolved at C-array if you think about the global H1 disks, but where they overlap, which is the area interest in my study, with the CO, the resolution is not that great. We did have the luck of having one galaxy that had matching, although the inclination of that galaxy is so uncertain that the surface densities we derive are actually still quite uncertain themselves. So you get the idea that this is not easy to do, to calculate the surface densities in the region where they overlap. Okay, but this is what we had to work with. So here is my initial attempt at deriving the empirical relationship. Now, incidentally, I do have a slide if anybody's interested in this, but in the interest of time, I'm going to show it, how we actually calculate the hydrostatic midplane pressure. If I don't have time to do that, you can always ask me after the talk. But you can see this, the equation you use up there that we used. It's a derived basically from Taylor series expansion of the equations of hydrostatic equilibrium with some assumptions. Okay, so as long as you have surface density of the gas, you know, the stellar volume density and a velocity dispersion of the cold gas, you can calculate the pressure as a function of radius, okay, in the galaxy. So here you see I've done that. you might notice that for a couple of the galaxies, the resolution is so poor. And of course, I've had to smooth the CO to the resolution of the H1. You don't get very many samples. So I've sampled at half beamed. So the sampling as a function of radius is half a beam. We only get sometimes two or three samples across the beam, with the exception of the one that had good resolution. But you can see already that the slope of this relationship is much different. Also plotted here are the H1 non-detected galaxies with the arrows. And like in the spiral galaxy case, they sit up from the line, but they do still seem to have a similar slope. Well, they're just H1 deficient. They're in clusters or groups where H1 has been removed from the galaxies. And with the exception of 4526, it coincidentally sits on the line, but I think if you think about, I've used an H1 upper limit here, and the actual H1 content may be much lower, so the line would shift up with the rest of them. So what I've done is I fit basically a line to just the H1 detected points. So that constitutes 5 galaxies. And that's where
2 minutes remaining.
Sorry?
2 minutes. 2 minutes.
Okay, thanks. I gotta speed up here. I wasn't very happy with using so few galaxies and that the resolution is so bad. So I'm wondering, the lower slope has something to do with not being sensitive to the higher density molecular gas because I'm smoothed a bit. And there is some possibility that we could be missing, higher density H1 as well. Also, the galaxy didn't have a lot of ancillary data. So asking the question about, well, maybe you would expect this because the UV content might be much lower, right? So in the outskirts, you may be able to remain not dissociating the CO back into H1, or the molecular gas stays in the molecular phase. Whereas in the center, and if you can probably notice, these galaxies have H1 all the way to their centers. There's no H1 hole. The H1 can stay longer in that phase in the centers with much less UV. But I don't know any of the, at the time I didn't have any information on that. Multi-wavelength data would be great, which we didn't have. So I also attempted to fit the actual physical model. This is Mark von Holt's model from 2010. And so I've made FMOL maps and molecular fraction maps. And so this is a value from each pixel in the map. And I've tried to do a fit to that. And it actually fits fairly well for these 4 cases, except for in the inner regions, the models seem to over-predict the molecular fraction. However, this also could be a resolution effect because I've had to smooth the CO, right? So not super happy making huge conclusions with such a small sample. So I want to improve some things. I've been working on increasing the sample, observe some more well-studied early types that have more ancillary data. I would like to expand the parameter space. So we have basically this bias towards CO-rich galaxies and galaxies that have CO but no H1. So to add some galaxies that are also H1 rich but CO poor. Since the H1 is still so poorly resolved, it would be great to get B array data, or better in the future would be great. I'm a little also limited by the CO resolution and the spectral resolution of the data. To get enough sensitivity, our channels have to be usually greater than 10 kilometers a second. It's not great to measure the cold gas velocity dispersion, and there aren't that many measurements of that for early type galaxies. Okay. So I've expanded the sample to supplement with galaxies from Atlas 3D. Okay, so this is a big survey of 206 early types derived from 2MASS out to 42 megaparsecs. Okay, and it has a huge amount of multi-wavelength observations, including UV metallicity information, which I did not have before. Okay, so I've added a bunch of galaxies from there with the idea that now we have a sample of 32 galaxies and added 6 new H1 poor, CO poor galaxies to complete the parameter space. So nicely, 20 of the sample galaxies have existing C2 observations from Herschel. And there is a new method of calculating the hydrostatic midplane pressure using those observations, which I won't go into if you're interested. I can talk to you about that later. but that will be a nice independent measurement of the hydrostatic midplane pressure. So we have been collecting this new VLA data for B-array for many, many semesters now. Along with, we need D and C configuration for those that don't already have them to fill in basically the moderates, the short spacings to get more to all of the flux. And we need the C observation to, in the case where we don't detect a lot in B because the surface density is just very low, which is the case, we need the C array also to match the C2 emission so that we can carry out that analysis. So finally, the observations will be completed in by February 22. And this sample actually consists, if you count up all the data from the original C array data that Lisa, the project is now over 300 hours. So it's a rather large project for the VLA. So all of the data that's already been collected is currently being calibrated and imaged by me and a lot by my undergraduate students. First started out was Izel Giovanelli, and more recently Tim Proudkey, who's done a lot of work. Undergraduates are a great resource here at Virginia Tech. Recently received an NROSS grant, which will support a graduate student to work on the analysis. So I'm actively trying to recruit one so this analysis can move forward. But once complete, we do want to release the images for all the targets to the community. And we hope that since this data isn't currently available, these early types at this kind of resolution and sensitivity will be a legacy value. So I just wanted to give, before I run out of time, some preliminary results. So this is Tim Proudkey's work. He reduced the data and did the imaging. And we've made images of very different, all of the arrays and combinations and different weightings and schemes to maximize the resolution and sensitivity we get here. So you can see at the left a C array, only B array, and then a combined EC plus B. In the bottom right panel, you see the surface density as a function of radius here. And you can really see what we gain by the combination of the data. Okay, this is
could you wrap up?
Yes, sorry. This is the last slide. So this is what happens when you take this galaxy and you put it through the pressure analysis, and we did get a surprise here. The outskirts of this galaxy actually fit the spiral relation better, whereas in the inside, it's tending toward the early type. So this is a surprise, and it highlights the reason why we need more targets and better resolution data. So watch the space. The data is coming in, and it'll be here, and the analysis will be underway coming this year. And I thank the VLA for all the time they've given me. Thank you, everyone. I'll take questions.
Oh, okay, thank you, Danielle. For interest of time, if there's a very quick question, we can take one.
Yeah, I apologize for going over. Too much.
So we can always leave questions in Slack or chat box. If there's no question now, okay, let's move on. Thank you, Danielle.
Thank you.
And the next talk is by Ming Yun about TLS Conpol project.
Thank you, Jin. So I am going to talk about Chile's Conpol project today, which is a commensurate project with Chile's H1 cosmology project. When I put this talk together, I was not really thinking about the history of the VLA, but it turns out there's a lot of history for the past and the future. The past part is that this project, both the Chile's and Chile's Conpol projects, were formulated nearly 20 years ago when at the EVLA science workshop in Socorro. So it has a long history. It took us nearly a decade, during the last decade, to collect all the data we needed to reach the sensitivity we needed, which was enabled by the upgrade to the electronics. But the collecting area didn't change. So that's one of the limitations. But what these data show us is that once we have the collecting area and computing, we will be able to study evolution of normal galaxies. And this image you see on the screen is basically one of the first images of radio sky to me that is anything like what our optical or infrared counterparts see, and that is there are sources everywhere in the night sky, and the night sky is dark. Okay, so give a little bit of a background to the project. It's an old project. So among the collaborators you see here are both historical and the future. This is this was motivated by a project to image H1 evolution from 0 to about ratio 0.5, led by Jacqueline van Gorkum as a PI. But we also recognize that during that time, we can get one heck of a deep VLA 1.4 gigahertz continuum image of whichever field we decide to observe. And then Chris Hales, who was a PI at the Chile's Compol project, took that one step further and developed a full science case with his scientific collaborators who are listed at the bottom. Well, Chris left astronomy a couple of years ago. He's still working at NRAO, I imagine, but he didn't have any science time to push his project to the end. So members of the Chile's imaging and calibration team basically took on that and seeing the end of the data reduction and imaging and providing the data products to the community. So that's where some of the collaborators on the top are coming in. And I would like to highlight in particular, Nick Bluber, who's a graduate student at the University of West Virginia, is primarily responsible for the images that you're going to see today. And Han-Sung Kim is a postdoctoral fellow at ASU and now moving to Montana State University, is doing a lot of the catalog generations and studies of galaxy evolution. As you'll see that we haven't really progressed very much in terms of exploiting the science aspect of the data yet. In fact, we're still in more or less the data verification stage. So we are going to have first science workshop among the core collaborators beginning next week. So that this is where we are. You're not going to see very mature results, but I hope the results are tantalizing enough that hopefully you'll be excited about having the data in your hands sometime in the near future and reach out to some of the people who are working on this project now. So the basic idea was that with the WIDA correlator, you have enormous capability to process all the signal that comes through the VLA telescope. And the Chile's H1 project basically uses 500,000 channels to map H1 at 20, 30 kilometers per second velocity resolution out to ratio 0.5 or so. But at the same time, there's lots of resources available in a WIDAR. So we're also using 4 subbands in full polarization to cover frequencies between 1 and 1.9 gigahertz. And so the continuum project is called Chile's Compol. Because we only have about 1% of the numbers of channels as proper Chile's project, it's actually relatively data light, meaning about 100 gigabytes of data per hour and total data volume only about 100 terabytes. So you can actually reduce data in a human lifetime. And if you do so, we were expecting that sensitivity of 0.7 microjansky RMS with about 4 second resolution. And you'll see later on that our current data images approach this sensitivity. So this is actually the good news. There are lots of different science projects that people have developed for this data set, but I don't have time to talk about many of it. I will just present mostly what the data looks like, which will be relevant to the bottom, providing the community with science products. If you have any suggestions and input on that, we'll be glad to hear. My personal interest in galaxy evolution, obviously, and so I couldn't help. I have a couple slides on that. As you saw in several different presentations in this conference and also Jackie's presentation just a little bit while ago, Cosmos field is a prime target for this sort of observations by VLA and other interferometers because there's so much information that's already known. And in fact, there are a couple of major VLA projects already done at 1.4 gigahertz and 3 gigahertz. And those footprints are these large orange box here that covers about 2 square degrees. So in comparison, the location of the Chile's pole is slightly off center to the northeast. And the area of the survey is about 10% of the full area, depending on how you count. So the footprint corresponding image is shown on the right. These are, because of the large bandwidth, the primary beam of our survey is a little harder to define. You have to essentially compute it. So we have sources going out to nearly 30 arc minutes in radius, but it just adds to the imaging challenge. And imaging challenge is enormous. And if you're curious about that, you should buy Nick Luber a drink, and he's going to spend a good chunk of an evening explain what he had to do to produce these images. But then the zoom in on the bottom right shows you, just the enormous source density and the sensitivity that gives you in terms of, what the radio sky really looks like. To reiterate, this is a full polarization data, and we have it. They are fully calibrated, and we have made images of all 4 Stokes parameters. And on the top left, this is an intensity map, and the grayscale covers between minus 10 microjansky to about 30 microjanskys. So you can see some bright sources as well as sources that are near the dirt. The eye and cube polarization images are plus or minus 5 microjanskys. So earlier I said sensitivity should be of order microjansky or slightly less. Those numbers actually come from these images that should be relatively free of the sources. Another running theme in this presentation is that once you get down to these levels, source density is so high, what you call a source and then the blending of the sources becomes a real challenge. It would have been a real surprise to us, except Herschel Space Telescope has seen this in the sub-millimeter band. So we're comfortable with that idea. And from this point on, I'm going to call all of these things components, radio components. They may or may not be individual galaxies or blends of galaxies. I myself haven't done a lot of work with polarized data, so at least information is there if there are people who are interested in using that. I just wanted to show that. And also, I wanted to give you a little comparison of what the new data looks like compared to the couple of other larger surveys that you just heard about from Jackie and others. So on the far left is the VLA Cosmos 1.4 gigahertz survey, which has the RMS noise of about 10 microjansky at about 2 arcsecond resolution. The middle is a 3 gigahertz survey with RMS noise about 2 microjansky, but if these are star-forming galaxies, effectively equivalent sensitivity at 20 centimeter is about 4 microjanskys. And the image on the right is about 5 arcsecond resolution, Chile's pole image. And basically what you see is that at 5 arcsecond resolution, and comparing that with these 2 other images, we're really not seeing individual galaxies in some cases, but there are clearly blends, like these 2 sources blends into a single one. And there are other sources that may be blends. And in fact, seeing how many sources are there, it may be that every source may be blends of something. But with the essentially a microjansky RMS sensitivity, you can see that there are a lot of individual PSF shaped things, which are essentially individual galaxies, and you'll see that shortly. In terms of just giving statistics, we estimate that the noise about 0.8 microjansky RMS based on polarization data, and also making the map like a couple degrees in size and going way outside the primary beam area and just looking at the image noise, and they all agree to about 0.8 microjanskys. And if you run a standard source detection algorithm and you recover something like 4,000 sources that are formally 5 sigma, but they're all about 10 microjanskys RMS. And in fact, this survey area plot, which is basically counting number of pixels and corresponding RMS noise determined locally, is that it never actually goes down to the thermal noise that we expected. And that's because you're basically seeing fluctuations in pixel values due to distribution of the sources. And in fact, you're going to hear a great deal about that from, I think, Jim Condon's talk on doing fluctuation analysis at the 10 to a few microzansky level. And I think we're seeing exactly the same thing here. We have number counts.
2 minutes.
Okay. I have a number count plot there, but you're not going to get a lot of that. I mean, it's just basically consistent. And even with the firebar second resolution, you have enough resolution to compare with optical data. So this, what you're seeing is Chili's Conpol contour maps, contours of 2, 4, 6, 8, and 10 microjanskis on top of HSD H-band image. And basically every one of these Chili's Conpol sources have a single optical galaxy that is primary contributor, but the contours are not exactly a point-like, which means there are other sources that are blended. In other cases, there are clear blends. This is actually trying to get a sense of what type of objects you're looking at. So here I'm showing the Chili's Conpol data in grayscale, but in contours, MIPS 24 micron image that goes down to about 80 microjansky sensitivity. And majority, more than 50% of the radio sources have MIPS 24 micron counterpart. Basically, the depth of the MIPS 24 micron sources survey here is to detect something like 10 or 20 solar mass per year star-winning galaxy out to redshift 1, or 100 solar mass per year galaxy out to redshift 2. So basically, when you see matches, those are the types of galaxies you're looking at. But there are also lots of sources that are without infrared counterpart. So that means these are probably sources that are forming either stars at lower star formation rate or higher redshift, but in the star forming main sequence. Fortunately, Chili's Conpol is in Cosmos field where there are lots of spectroscopic and photometric redshift. What you're seeing here is the residual map after running the source finding algorithm. And they remove sources out up to about 10 microjanskis. But when you put contours of the residual map on top of a Spitzer IRAC band 1 image, which is tracing mostly stellar mass, you see lots of matches, even with these 10 micron, a few to 10 micron contours. And in fact, if you look at the redshifts, they're basically redshift 1 star-forming galaxies. These are the things that people used to call faint blue galaxy population, microjansky faint blue galaxy population by Falmelon and David Koo and people in the 80s and 90s. And the history repeats again. So these are, in fact, lots of sources out there. I think you're going to hear Jim Condon describing these sources statistically. So just to wrap this up, basically, we've just produced first images and we're examining them. And it took quite a bit of work, but I think we're going to be able to do as much as we can do with the current data, with the current calibration. And we're going to start looking into some science questions doing that, but also prepare data products for the community to use, because this is one of the promises we're trying to deliver. Because Cosmos field has all these exquisite multi-wavelength databases, in fact, one of the advantages of this particular data set is that you can take advantage of it and ask a bunch of questions about galaxy evolution, which we could do. And I put in this plot of the optically dark sources that was mentioned in Jackie's talk briefly. And there are 7 ALMA detected 10 sigma sources. Now we see with a signal noise of equivalent or higher in radio continuum, and this old millimetric radio photometrics technique that Chris Krillian developed a couple of decades ago suggested these are indeed redshift, high redshift sources like redshift 4 and above, as Jackie alluded to. So this is just a taste of what you should be able to do with a data like this. And obviously, when you get to NGVLA, you can study all of these objects in the gory detail with a ALMA-like exquisite resolution and sensitivity. Thank you.
Thank you, Min. Any question? Please raise your hand. Hey, Brian.
Hi, Min. Great talk. source finding algorithm are you using? PyBDSM or something else?
Well, Hansen can answer that question better, but yes, we use PyBDSM, we use Blobcat, we tried a couple different things, but I think fundamentally there are just so many sources. You really, maybe it is silly to try to actually identify discrete sources at this point. You can take
and the hard thing is the blending. I mean,
yeah.
It's just, how do you, I remember people 20 years ago were working on fitting blended sources in back in Apes++, and it was just a really hard problem. So
yeah, I think we're seeing exactly the same problem.
yeah, good stuff though.
Okay, thank you very much. Let's move on to the next speaker. Thank you very much, Min. So next speaker is Rob Selina, and the talk is about the engineering aspect of energy VLA. Yeah, Rob.
Apologies, I was muted. Yeah, thank you for the introduction. Wanted to give you a sense of the sort of engineering challenges and solutions that are keeping us on the technical team occupied at the moment. So hopefully you had a chance to see Mark McKinnon's presentation, I believe 2 days ago, introducing the NGVLA project. But here's kind of a quick recap on the concept. We, roughly speaking, wanted to have about 10 times the collecting area or sensitivity of the VLA and ALMA at this 1.2 to 116 gigahertz windows, with resolution spanning out the continental scale baseline. So we're covering arc minute to milli-arc second scale structure. And the scientific theme that we're looking for here is fundamentally thermal imaging at milli-arc second resolution. That's kind of the frontier we're aiming at. And that drives both the sensitivity and the resolution of the system compared to where we are today with the VLA. We're presently in the conceptual design phase. So it kind of goes without saying that centimeter wave arrays have been built before, right? I mean, the VLA has been operating for 40 years and it wasn't the first. So everything's fundamentally possible here. It's not a physics problem. But the challenges that we have largely relate to affordability, either in the construction phase or the operation of the array. We consider both equally because, well, while annual operations are appreciably smaller in dollar value, spread out over the life cycle of these instruments, they actually can be the most significant investment on the part of the taxpayer. And so we try and take a look at total life cycle cost. There are some new technical challenges, though. The first is related to the scale of the instrument. So having 263 antennas, 20 gigahertz of process bandwidth per antenna, that introduces challenges in the data rates and the processing capacity. We'll speak to that. And the operations concept, kind of derived from that scale need, is that we want to deliver high-level data products to users. And if you start considering what it takes to routinely calibrate data, produce images and image cubes, you really need to be considering design for pipeline calibration. And that feeds back into the hardware design. So challenges kind of fall in these three broad categories of affordability, operations concept driven, and scale. And I'll give you an example of each as we go through this presentation. So on the affordability front, surface accuracy is an example. A typical centimeter wavelength antenna will use stretch-formed aluminum panels. And so these are, you start with a sheet of aluminum and you press it over a mandrel or a form, and then you glue on support ribs on the back. And that's how the VLA panels are constructed. And then there's a bus backup structure that ties the panels together and into a reflector. When you get into millimeter waves, that process is no longer adequate. There's too much error inherent in it. And so ALMA, for example, will use machined panels. So you start with a solid block of aluminum and you mill it out both sides to get the surface on one side and the mounting points on the other. NGVLA is operating at 3 millimeters. We're right in the middle here. Stretch form panels have a bit too much surface area for us. And so it's not an adequate technical solution, but we don't want to incur the cost of an ALMA-like solution. So what we've figured out is that one, a rectangular grid of panels is the optimal answer for us. There's no rotational symmetry in our offset Gregorian optics when they're shaped for sensitivity with single pixel feeds. And what we've been able to do, working with MTEX, our antenna vendor, is come up with a 68 rectangular segment design that uses two simple molds. So one mold for all rectangular panels, as well as a second mold for the triangular panels at the edges. and go through a process where we do cast and post-machined panel design. So you cast the panel, stress relieve it, produce lots of blanks. They're all common at this point. And then you machine it according to the required surface spec of that particular panel, given its orientation in the antenna. And what this offers us is an ALMA-like performance level, but with appreciably less tooling, courtesy of the casting and post-machining process. It works because of the scale of the array. So we carry these construction affordability ideas into the backup structure as well. All the joints at the 5 support points of the panel in the bus are either cast and post-machined or machined themselves. And then there's 3 common tube diameters and a set of common lengths that make up the octahedral bus structure. So this is all constructed on site without welding. So the assembly effort is lower. There's less total parts count and less unique parts. And so you can punch them out in greater volumes and hopefully at lower cost. And then you can see how the whole thing comes together eventually into a backup structure. It gets put on the pedestal. Now, when we consider the operations concept and that need for analog stability to enable pipeline calibration, the analog system, again, is really the key emphasis here. So a typical radio astronomy solution would be to convert RF energy to baseband where you can digitize it, and through multiple intermediate frequency convergence stages. So in the case of the VLA, if you go pick the KU receiver, it might be converted to X band first, and then eventually to S band where the digitizer actually samples it. And these systems are highly tunable by nature because you need to be able to pick the correct RF band of choice. But that makes them also unpredictable to some degree in their amplitude and phase response over frequency. And so the calibration challenge can be quite hard. What we're trying to do in NGVLA's case is digitize the full band with highly integrated modules and have the shortest possible analog path that way and move the tuning into the digital domain whenever possible. And so you can see a block diagram on the lower right of the in-phase and quadrature single stage down conversion sampling modules running at 7 gigasamples per second. And the figure at the top shows the tuning plan and how these bands overlap for full frequency coverage. And here to give you a sense of the integration we're talking about, these are very small modules. You can get a quarter for sense of scale in the figure on the right. That's a W band prototype. We've got a band 3, so a 12 to 18 gigahertz analog stage prototype in the center of the screen. These are occupying a sort of 10 centimeter scale, and they are right behind the cryogenic receiver. So all the analog stage is located immediately after the cryogenic stage. And coming off of this module, it's digitized signals on fiber optics. As part of this, we're working on actually improving upon the packaging that you see on the upper right by building our custom digitizer integrated circuits. These will be the full spec 8-bit 7 gigasample per second units. And you can see an early proto on the lower left sitting on the quarter. That'll allow us to shrink down the digital side of these packages, as well as mass produce them in volume, so we hit our affordability targets. So again, related to the original challenge. But the end result of all of this is a front-end package that's highly compact. So you can see here the cryogenically cooled front ends, the down converters, and the digitizers all reside in this front-end package that's sitting on this 2-axis indexer right by the subreflector. This is a 1 meter by 1.6 meter by 60 centimeter package. So it's size of your kitchen table, give or take. And coming off of it is fiber optics. So we've eliminated those paths, hopefully have a very stable system. And by moving the tuning to the digital domain, it's much easier to predict its behavior and to automate the pipeline process. Moving on to scale, data processing is the obvious example here. So I believe today, typical VLA data rates coming off the correlator are tens to hundreds of megabytes. NGVLA will have an average rate across a suite of use cases that we use as our canonical set for testing purposes of 8 gigabytes per second. And there's peaks for the most demanding cases that hit 132 gigabytes per second. So factors of 1,000 more data effectively. Now, we fortunately can still store that data to disk. We're projecting what the cost of storage looks like over the course of the construction phase, construction operations phase of the array. And saving that data to disk and still doing post-processing looks like a tractable solution, and that's our default plan. But the computing needs are quite significant as well. We're looking at a 60 petaflop per second system. So using it that same set of use cases, and assuming those data rates, it works out they need a 50 petaflop per second system to just keep up. And then of course, there's going to be reuse cases, right? People will want to gather data from the archive and reprocess it, or individual PIs will have a need for reprocessing data, or QA failures will happen. And so the 60 petaflops accommodates that. This, to put in perspective, would be number 7 supercomputer in the world today by capacity. Oak Ridge National Laboratories have the Summit system, which is the most powerful supercomputer in the US, and that's 149 petaflop per second today. So we are talking supercomputer scale today. Hopefully by 2035, this will be a more affordable system. But importantly, it's tractable by that time frame, but we also don't expect your MacBook is going to be providing it, right? So this has to be done as an observatory function with observatory provided resources, much like we do for telescope time. And we need to split our software tools into a data analysis toolkits that you can run on your client, and data reduction tools that run on the cluster centrally. And we don't move the data around too much that way. And this whole model turns into kind of a client and server model for data interaction. We realize our PIs will want to still interact with the data reduction process, but we can do it through this kind of more cloud-based model going forward.
2 minutes.
Thank you. So those are operational kind of process changes that we're working on, but we are also working on some technology solutions here as well. And the most intensive computing step is the gridding operations before the Fourier transforms. And you can see a T-clean execution loop on the left figure, and where you're grinding along at low arithmetic intensity is where you're gridding. What you can see on the right is a high throughput gridding prototype that's in development here at NRAO, using GPUs and some innovative ideas on how to correctly align and parallelize the data. And the cliff notes here is it's about 100 times faster than the current cost of implementation. So in addition to these operational solutions, we think we also have some technology solutions that will improve on the scale of the system. So some brief conclusions. Well, centimeter wave arrays have been built before, and VLA does have some unique challenges related to the scale of the data volumes, this desired operational support model, and the need for delivering high-level data products, and just more broadly, this need for affordability in construction and operations. But we're working to develop novel solutions to address these challenges and make this facility a reality. So thank you, and I can take any questions.
Thank you, Rob, for the exciting aspect of the project. Any question? Please raise your hand. Okay, I have one question. Okay, go ahead. Go ahead.
Sorry, Jen. Do you want to comment on the data backhaul issue, or where we are with thinking with that? I mean, I kind of know, but most of the people in this meeting won't.
Yeah, we're looking, so from antenna to correlator, we're debating the total bit depth we want to transmit, but the data rates vary. Most likely data rates at the moment are closer to about 600 gigabits per second. And so we're just under a terabit basically per antenna. It's the way to think of it by the time you're done. Most of those antennas are on the planes that can be point to point back to the correlator, but once we get about out of like a 300-kilometer radius, we'll need to rely on ISP networks. And so we have a scaling solution there that depending upon the cost, we can transmit full bandwidth or partial bandwidth for those antennas. And then the data rates from the correlator to the processing center are actually relatively modest by comparison, right? We're looking at sort of terabit links for that. And then we really want to leave the data in place and process it in place. Does that answer your question, Brian?
Yep, sounds good.
Okay, Gregory.
Yeah, I'm sorry if I missed this. I may have blanked out for a moment, but is the plan currently to archive all of the data, or are we in the same boat as SKA and thinking that that won't be a tenable solution?
Now we've done a preliminary model, and of course it's a bit sensitive to, or it's very sensitive to the projected costs of disk space. But our expectation is, based on the ramp up of during the construction phase, that we can afford to save the fundamental visibilities at their native resolution, just like the VLA does today, not like SKA. And so I think that is a great outcome for us in two respects. One, it's a lower technical risk solution because you don't need to have, you can afford to reprocess data. You can afford to have a failure in the pipeline, right? And it also enables reuse. And that's our fundamental data product in many ways is time, right? And so if you can get multiple scientific returns out of a single hour of observing, I think that's a really beneficial outcome. So yeah, saving the visibilities is absolutely the plan.
So is the main difference from SKA the extended timeline on which NGVLA will come online compared to, for instance, SKA1 mid?
Yeah, their data rates are also quite challenging too. And it has to do with operating frequency and primary beam size. And so time and frequency resolution go up for them, even though they process less bandwidth. It's kind of tied to the operational models being more survey driven in SKA sense versus deep field imaging in ours.
Thank you.
Okay, let's thank Rob and let's move on to the next speaker. The next speaker is Aishwarya Geha. Sorry, I don't think I am pronouncing your name right. Please introduce yourself with proper name. The talk is about radio jet and quasar feedback.
Sorry, I was on mute.
And could you share the screen?
Yes. You see it now?
Yes.
Great. Okay. Thank you. Greetings to everyone from different parts of the world. I'm very happy to be presenting some results from the Quasar feedback survey today. I'm Aishwarya Girdhar, and I'm a second year student at ESO. And okay, so firstly, we do know that there are supermassive black holes at the centers of the galaxy. And these black holes in an active state are actually also accreting a lot of matter and releasing huge amounts of energy. Now, this energy may come in different forms, like jets, radiation, or accretion disk winds. And the most luminous and highly accreting form of these active galactic nuclei are something that are called quasars. But precisely for the case of quasars, it's very unclear that which of these mechanisms have a significant impact and how much impact, and which are the most important ones, and also what impact do they leave on the galaxy. So the study of the impact and this relation is what we also call the feedback. So what do we know from simulations? Firstly, is that we have different models from simulations that have different predictions. For example, on the left, I show one of the prediction from a thermal injection model, which predicts that there may not be a rapid impact on the disk or on the star formation in the galaxy. And at the same time, there are models that predict that, let's consider a low power jet, which could be another mechanism for feedback. And we see significant impact on the disk and star formation in this case. Now, of course, that also depends on different properties of the jet, like the power, inclination, and disk properties. For a more rigorous discussion, there are some references that I would like to suggest, but for now, I wanted to mention these main models. But the idea then is that what we know from models is pretty varied, and then we need high resolution observations to be able to really see what may be happening there. So the key questions that we are trying to address here for the quasars is firstly, what is the origin of the radio emission that we see in these typical quasars? And secondly, what drives these outflows and turbulences in quasar host galaxies? For example, like I just discussed, like jets or disk winds or radiation. And then finally, what impact do the quasars have on their host galaxies? For today, I would like to keep my talk to the discussion of the first two questions. And with that, I would like to introduce the Quasar feedback survey. So we have data of 42 quasars at a redshift of less than 0.2, and we're building a multi-wavelength data set. This is a survey being led by Chris Harrison, and I would really invite you to take a look at the Jarvis 21 paper, where we summarize our results from VLA for all the 42 quasars. So how did we basically select the sample is that we tried to identify the most powerful quasars, which I showed through the plot on the left here. So this shows a comparison of the full width half maxima with the O3 luminosity for the O3 line profile. And as you can see, we select quasars that were really highly bolometrically luminous. And hence we have all these black stars that form our data set. And we also have like a good distribution of the full width half maxima in this case. And then in terms of the being radio quiet or radio loud, on right, I show a comparison of the traditional radio quiet criteria shown with this blue line from Zoo 99. And basically we're comparing the radio luminosity, in this case 1.4 gigahertz, and then the O3 luminosity here. And as you can see, most of our targets are actually radio quiet, with just like 5 of them being radio loud. So what do I want to show today is basically a summary of all these 42 targets and what we see from our VLA observations, which are high resolution. And then we have data for 1.4 gigahertz and 6 gigahertz. And then I also would briefly like to show what we see from integral field spectroscopy studies and with MUSE and GMOS, and also very briefly what we see with ALMA, like how this radio emission is kind of interacting or like affecting the host galaxy that it is seen in. Going on with addressing the main question then. So what is the origin of this radio emission that we see in quasars? That is basically told to study this AGN versus star formation contribution to the radio emission. So what we first realized with the morphology was that 2/3 of our sample actually showed a kind of a jetted morphology, that we saw nucleocollimated structures. And this is when, let me remind you that only 5 of our quasars are actually classified as radio loud, sorry. So the idea here is that are we actually, had we used, let's say, a criteria with FIRST and NVSS, we would have probably missed these galaxies, these radio loud galaxies that we were able to see with the VLA data. And then we went ahead to really study this radio emission using different parameters. So firstly, the far infrared and the radio correlation, then the spectral index and brightness temperature of the radio cores, and the jetted morphology as I showed on the previous slide. So to kind of take you through this busy plot on the right, we are basically showing the distribution of the brightness temperature and the spectral index. And as you can see, like most of the quasars have pretty negative spectral index and fall on the left. And with this dotted line actually presenting the flat core definition. And then we also tried to show this classification with the AGN morphology through this pinkish pentagon, and the blue circles showing if we see a radio excess for when we compare the FIR and radio correlation. And using this, we kind of, to summarize this busy plot, the results that we get here are that from the 42 of our targets, 24 of them were seen to say that the radio emission was confirmed to be coming from an AGN using all these parameters. And this is a lower limit because the other 18 were actually unclear if the radio emission is from the AGN or from star formation. And again, I would like to remind you that actually only 3 to 9 of our targets were classified as radio loud AGN based on the standard criteria. So what we're saying, what my first take-home message that I'm trying to drive here is that maybe the common radio loud criteria are not complete, and hence the study of these additional parameters actually helps not to miss these very useful radio galaxies. Okay, and then next I also want to just briefly show what we see when from from the IFU integral field spectroscopy studies, and how we see that these jetted morphologies that we have, they're also kind of interacting with the galaxy. So here in this plot, I show like a subsample that was studied for the ionized gas and radio emission comparison. So in the background, you can see the ionized gas emission with the darker colors representing higher emission. And this is overlaid with the VLA contours. And one of the quickest results we see here is that actually you can see these contours to be tracing regions of higher emissions, which kind of adds on to this growing evidence for seeing the interaction of this radio emission with the interstellar medium in the host galaxies. And then I tried to show like a more detailed study for one of the target objects for this case. And so I'm showing here J13161753, and we have the data. We study the ionized gas from Muse and the molecular gas from ALMA. And this is really zooming into the center of the galaxy, super close to the radio emission, which is shown with black contours here. And what we see is, I think, super interesting, because for the ionized gas, we see like going perpendicular to the radio emission, there is a highly disturbed gas emission. And the plots that I'm showing here are actually WAT, which is basically just saying the line width of the O3 emission line profile. And so for the ionized gas here, we see these darker purple colors, which actually trace this more disturbed gas. And then when we look at the molecular gas, we see that we also see this disturbed gas here, but in this case only on one side and way less extended than in the case of ionized gas, which also makes sense because of the higher density of the molecular gas. And interestingly, we compare this with the JET ISM simulations, and they qualitatively, the simulations also predict a similar thing, which is very nice to see. And this is just the beginning of deeper analysis into this multi-wavelength study. And we have more targets and more target observations from this survey that will be following up soon. So in that sense, please stay tuned. And
okay, 2 minutes.
Thank you. With that, I just want to drive home the conclusions. So we do see that there is a high prevalence of radio AGN emission, and that is associated with typical quasars. But most of these are not identified using the crude radio AGN diagnostics. And secondly, we do see a relationship between this radio emission and the ionized gas kinematics. And this is a good, interesting hint at the JET ISM interaction, which is being seen to be more and more common in quasar host galaxies. To know more, I would really direct you to the other studies done by the other members of the survey. I invite you to read them. And with that, I would like to thank you. And if you really are interested in the work we're doing in the group, I would also like to take this opportunity to advertise 3 positions, postdoc positions upcoming with my supervisor at Newcastle. And with that, I would like to thank you for listening, and thank you to the organizers.
Thank you, Aishwarya. Any questions?
Good.
Yeah, please pronounce your name first. Sorry.
Aish is good.
Aish? Okay, Aish.
Yeah,
thank you, Aish. Any question? Please raise your hand if you have any questions. Okay, so what do you want to do next? After observing all of these, how do you want to characterize the impact of feedback?
Sorry, the impact of?
The feedback, quasar feedback. How do you want to characterize the impact?
Yeah, so our main idea is to be able to really study this JET and ISM interaction that we are seeing as hints, and to really look at these different properties of the radio jet. These are low power radio jets, so based on like their inclination, their power, and how, depending on the different properties, this interaction with the ISM in the galaxy varies. That would be the next step.
Thank you. Any other question? Okay, if you have any questions, you can leave it in chat box or Slack. Okay, let's move on. Thank you, Aish, and thank you. Okay, let's move on. The next speaker is Subarada Day.
Hello.
Yeah, the talk is about physical properties of luminous infrared galaxies.
So I'm audible?
Yeah.
Okay, and the
we can see
slides
your
are
slide.
visible.
Mm-hmm.
Okay.
Yes.
Great, great. Hello, everyone. So I'm Shubrata Dey, and I'll be presenting about investigation of physical properties of LUGs using SED modeling. So this work I'm doing in collaboration with Dr. Arti Goel and Katarzyna Mawek. So I'm a PhD student at the Astronomical Observatory of Jagiellonian University, which is in Krakow, Poland. And both of my collaborators are from Poland, so from our observatory and also from National Center of Nuclear Research, which is based in Warsaw. So just to begin with, just a small introduction. So LUGs, or luminous infrared galaxies, are, as the name suggests, they're very bright. They're emitting mostly in infrared regime, and they are defined by their infrared luminosity, which is seen as greater than 10^11 solar luminosity. So as you can see, even in the SEDs, that it is mostly bright in the IR regime. Also, so what you have here is a plot of a spectra, radio spectra from radio to IR, I would say. And this is a spectra of a normal galaxy, normal star-forming galaxy from Condon 1992. But when we see LUGs, they generally at the low frequency show a flatter spectra. Now, this flatter spectra could be because of synchrotron self-absorption, which might denote that there's a presence of an AGN, or a thermal free absorption, which might be in a case of an starburst-dominated spectrum. Also, there are chances where we see there are much more complicated spectra, where there are multiple turnovers, which we'll see in coming slides. And we want to study what are the reasons for that. Also, we see that the Q parameter, that is IR to radio correlation, is between 1.9 to 3.1. So what is the motivation of our study? So, first let's talk why SED. So we know that the multi-wavelength emission, that is from the gamma to radio emission, is an outcome of a complex physical interplay between the main baryonic components of the galaxies. That includes the stars of all ages, the remnants, molecule, atomic, ionized gases, dust, supermassive black hole, etc. Now, what SED does is SED contains the imprint of these baryonic processes that drives the formation and evolution in the cosmic time. And via SED, we can study a lot of different processes that are contributing to its existence or in evolution. And that's why we are interested in studying the SEDs of LUGs. So why SED of LUGs? Because it is still debated what is contributing to its emission, that is, whether it's a starburst or AGN that makes it so luminous in the infrared regime. Now, this is our sample. So you can see there are 11 galaxies that were selected, and these galaxies were assembled from Condon's IRAS bright galaxies. IRAS bright galaxies that were that we had assembled, and we checked that these galaxies are existing in the TGS's data release 4 or not. So that's why you can see that all our galaxies have negative declination over here. And so talking about the data, so our data consists of our own observation, first of all. So these observations were made by our team using the GMRT telescope, which is located in India. And they were observed in June 2013 at frequencies 325 and 610 megahertz. And then these were further analyzed using standard tool APES. Further, we also made an archival radio observation. We also got archival radio observations, first from VLA, definitely, and it has been very, VLA observation has been very crucial to get a more comprehensive spectrum. So we got VLA data from 1.4 gigahertz to 14.9 gigahertz, which were further reduced by us using APES. Also, we could get a low frequency data from 70 to 300 megahertz using the from the galactic and extragalactic all skies MWS survey known as the GLEAM as well. So all this together gave us a much more broadband radio spectra from 18 megahertz to 15 gigahertz. Now, besides this, we were also interested in studying the since our main goal was to obtain a much more multi-wavelength SED. So we also focused from UV to IR SED modeling, and we could obtain the data from UV, optical, near infrared, mid infrared, and far infrared data. And you can see all the databases from where we got our got the fluxes. Using these fluxes, we wanted to have a much more broader SEDs. Now, here what I show you is an example of a radio modeling. So you can see here that we have plotted radio spectra of two galaxies, that is ESO 440 IG058 and ESO 507 G070. Now, so we tried to fit various models from power law to synchrotron free emission, free absorption, and further complex models. And this modeling was done using UltraNest package, that is open source package that is available. It's basically a nested sampling Bayesian inference method that is used to obtain constrain the model, the radio continuum model, and also used to and also can be used to compare the model. So this comparison is done based on the evidence value that we obtain. And using that, we found that that for our galaxies, at least for these two galaxies, synchrotron free emission with absorption was the best fit model. And this is the model what you see on the top. Along with that, for our ESO 507 G070, we saw that the mixed component model. So you can see it's much more complicated. It's not a straight power law model. And this was the best fit model for our galaxy, that is the synchrotron free emission with absorption and a power law. So you can see that a spectra of lurks are not that straight or not that simple, but rather more complex and needs a more complex modeling. Okay. So besides that, as I said previously, our main aim was to get a IR, multi-wavelength SED. So we focused on IR SED modeling as well. And we obtained this using the SIGAL code, that is the code investigating galaxy emission. So just telling a few words about SIGAL. So SIGAL is basically a SED fitting code, which is based on the energy balance principle. What do I mean by energy balance is that let's say the energy that is being absorbed by the dust in UV to near IR domain is being re-emitted self-consistently in the mid and far IR. So the logo is kind of a good way to show what they exactly mean. And SIGAL is extremely user-friendly because it is parallelized and modular. So being it modular, it's very easy for us to add our own models. Besides that, it is extremely time efficient compared to other fitting model as well. And hence it makes it extremely useful tool to obtain a multi-wavelength SED model. So here you see, here I'm showing two examples of the SED that we obtained using the SIGAL. So let me tell you that previously, I mean, a lot of studies has been done using SIGAL for lurks and new lurks and extra star-forming galaxies, but only few have included a radio regime as well, that is radio fluxes as well, and ours being one of them. So we have included, these are the VLA L and C band fluxes that we have included to get a much more broader range of SED. So here you can see from the UV till radio, we have included 5-decade frequencies in our SED plots, as you can see here. And this SED is based on different models that you can see: stellar, attenuated, unattenuated, dust emission, AGN emission, radio models, etc. And hence it gives us a very different information by these fittings. So these are the results that we obtained. So via fitting, we obtained different properties such as the stellar mass, the dust mass, the dust temperature, the star formation rate, the AGN fraction, the spectral index, the dust luminosity, and QIR, that is the radio to IR to radio correlation. So here what we saw is our results is very much in well constrained with the previous studies that have been done with a similar galaxy sample. But the interesting factor, what we saw was this AGN fraction of this galaxy ESO 440 IG058, which is 39.89, around 40%, let's say, and it is quite high, similar to your lugs. And in coming slides, I will discuss more about it. So further, we also wanted to see how our properties are behaving, whether they are well constrained with the previous studies being done. So here we are showing a characteristic plot of a comparison of star formation rate, M dust, and stellar mass with previous study. So in the first plot, what we see is a plot of dust mass compared to SFR, star formation rate. And here we have plotted besides, so here the stars are our galaxy, and we have plotted besides that the bullets or lugs, which are at a very high redshift. Further, besides that, we have also plotted the normal star forming galaxy, which are over here. So we wanted to study the evolution of such high star forming galaxies in redshift scale. And we can see there is a very strict, a tight correlation between the SFR and the M dust. Now, this is quite expected because of the dust cycle. That is, as the star formation rate increases, the supernova rate, etc., increases, and then we have more input of dust to the ISM. And hence, there is a very strict relation that we see with the SFR and M dust. Besides that, we also tried to plot the M star, that is the stellar mass with SFR here, star formation rate. And then you can see the stars that we do not really, it's rather scattered and do not see a very tight correlation between the two, which is again expected in such galaxies. And so this was, so we wanted to see how our galaxies are behaving with respect to that in the literature. And they are quite good, like results obtained are quite feasible.
2 minutes.
Yes. So talking about the conclusion, so first conclusion is that the radio spectra of our lugs are fitted with complex functional form, showing that the low frequency flattening and turnover. So this is what was expected and what we obtained. And this indicates that the free absorption in the star forming region vary with the optical depth. Further, we saw that the results that we obtained from the Seagal modeling on an average falls in the range exhibited by galaxies on the same scale. So our results were quite consistent with that of the literature. Also, we see that the AGN contribution is not found to be energetically dominant in our galaxies, as we see that the typical AGN fraction is less than 10%, except one galaxy, that is ESO 440 IG058, where it reaches as high as 40%, which is typical of a ULURG. Also, we see that the radio spectra of this galaxy shows a flattening. So we guess that this is due to the synchrotron self-absorption instead of thermal absorption. So yes. So thank you. And I would definitely like to say that these are preliminary results, and I really welcome comments and questions if anyone have. Thank you.
Thank you, Subrata. Any question? Please raise your hand if you have any questions. Okay, I have a question about the SED fitting from optical to radio. So the background of the fitting from optical to infrared is the energy balance, as you said. Can we stretch that physical motivation into radio wavelengths as well? Or in other words, are you checking the energy balance between radio and optical infrared part?
Yes, they do that. So this is there's a code that is available online, and they do that. They do the energy balance between the optical as well. And I would like to mention that the radio model is very strictly power law. It's not very complex. So hence they're trying to get not a lot of information, but strictly just the spectral index and the QIR parameter. Does that answer?
Yes, thank you.
Okay, thank you.
Any other question?
I can ask a question. Can I ask a question?
Yes,
Sorry.
Yes, go ahead.
Good talk, Subrata. I work on these ULERGs in general, and they are very compact. And I'm wondering, these are integrated values, right? So
Yes, yes.
yeah, okay. You did the matching because too much from 6, below 1 gigahertz to the 15. Okay.
Yes.
Yeah. Okay.
Yes, yes. Thank you.
Any other question?
Okay, thank you.
Min?
Yeah, just following up on that question and related to this plot on your final slide. You said this turnover in the radio spectrum is due to synchrotron self-absorption.
Yes.
Why is that conclusion rather than a free absorption associated with a dense ionized gas?
Well, our main conclusion, well, this again, I would say it's preliminary, and we are very free for to hear more comments. But what our guess is, because here the AGN fraction is so much high, so we thought that it will be rather synchrotron self-absorption rather than thermal absorption, which is due to the star formation. Or I understand. So also we compared our galaxies with the what do you say, with the contours. And in the contours, we saw that the emission was strictly very much concentrated to the AGN compared to the extension to the disk, thin on thick disk of the star, of the galaxy. So we kind of guess that this is major reason that we have the flattening is because of the AGN, and hence synchrotron self-absorption.
Okay, thank you, Subrata. Let's move on to the next speaker. The next speaker is, thank you. Next speaker is Ichin Son. And the talk is about high frequency radio emission in local ULERGs and LERGs.
Thank you for the introduction. Hello, everyone. I'm Ichin Song. I am a final year PhD student at University of Virginia, and very thankful for the organizers for putting together this event for radio astronomers from all over the world to come together and celebrate 40 years of VLA, and all the hard work and hardworking people behind it. And I'm very glad to be here to talk a little about my work the work that I've been doing as part of my dissertation project, looking at radio emission in local luminous infrared galaxies with the VLA. And I want to acknowledge support from the NRAO's Burt Reaper Dissertation Fellowship and the support from NRAO and VLA staff, and helpful discussions guidance from my advisor, Aaron Evans, as well as my collaborators. Some are listed here. I also want to thank the previous speaker for giving a really good introduction to LERGs and ULERGs, so I won't repeat them here. So basically the punchline is that these systems are luminous and infrared because they tend to be very dusty. This is one of my favorite example to show VV114, which is a pair of galaxy in mid-merging, and you can see from optical to the infrared and then to the radio, the heavily obscured eastern components in optical start to dominate the emission at longer wavelengths. So to be able to account for this full energetics of these complex systems, we need to get all the information we can get from different wavelengths. So I'm part of multi-wavelengths collaboration goals that look at the 200 or so LERGs and ULERGs in the local universe from the IRAS or bright galaxy sample. And on the right-hand side, I'm showing a non-exhaustive list of all the studies that's been done to look at these galaxies at various wavelengths. But I mentioned that these really highly energetic regions in these systems could be hidden behind thick layers of dust. And so this is where VLA observations can really help us. In the image cutout here, I'm showing some examples of the VLA 33 gigahertz continuum images mapping the brightest and most energetic regions in these dusty nuclei of these interacting systems. And these images are taken as part of the Equatorial Goals VLA survey, which is a snapshot survey that mapped about 70 goals targets that lie within the equatorial region. This is just to allow detailed follow-up from facilities in both northern and southern hemisphere. On the right-hand side, I'm showing the distribution of the basic properties of the sample. Basically, it's covering the full luminosity and distance range covered by the full goals sample. So we would expect the properties that we see in the VLA sample would be more or less representative. of the local Lurg and ULurg population. And so each of the system was imaged by the VLA in radio continuum at 3 different frequencies on both 100 parsec-ish and kiloparsec scales. So the first results from the low resolution studies are published in Linden et al. 2019. And before I dive into the high resolution portion of the study, just want to quickly mention that for the 30 systems in the sample, we also have kiloparsec resolution VLA L-band images from condensed IRS study, as mentioned by the previous speaker. This is before the VLA upgrade, and it is with the upgraded bandwidth of the JVLA, we're able to probe into this much fainter and thermally dominated regime of high frequency radio emission. So on the right-hand side, just to show a couple examples of different shapes of SEDs we're seeing from 1.4 to 33 gigahertz on kiloparsec scales in these systems. Now back to the focus of the talk, which is the high resolution study of these galaxies with the VLA. So in the panel images here, I'm showing, again, a couple examples of the different morphologies that we're seeing in high frequency in the center of these systems on about kiloparsec, well, sub-kiloparsec and 100 parsec scales. And so with these VLA images, what we want to answer is two questions. Is first, what powers these luminous high frequency radio emission at the center of these systems? And also in terms of star formation, how do they compare to those found in the normal star forming galaxy at similar scales? And in order to do that, first, I identified and characterized luminosity and sizes of individual radio knots using this Python package called Astrodendro. So about 100 individual regions were characterized this way. But this is not enough to answer the question because with the radio images alone, at least to my untrained eye, I'm not able to tell immediately what's going on, whether these regions are star forming or AGN dominated or something else. And this is where the multi-wavelength information from GOLS have been really helpful. So this is a whole process that I won't get into detail, but long story short, using the multi-wavelength information that we have, unfortunately, a lot of times at lower resolution, I was able to locate some of the regions in the relative position of these regions in the host galaxies. And for the nuclei, we were able to identify, we try to nail down whether they are mainly driven by AGN emission or something else using ancillary information from other wavelengths, like AGN classification from other wavelengths. And so the end product of this whole process is that I was able to characterize or classify these regions into different categories based on their location in the galaxy and also the properties of the host galaxies. And and now we have the luminosity and size measurements for these regions, and we have a rough handle on where these emissions are coming from. We can map them onto this luminosity and size relation. So the first thing that we notice is that the known AGN have the highest luminosities and luminosity densities at any given measured region sizes. This is perhaps not surprising because AGN are luminous and compact. And just to help navigate this plot a little better, so in the three regions I marked in red circle are the AGN and radio jet components from the nearby C41 galaxy and GC 1060A, which is also the closest galaxy in the sample. And in the magenta or pink, marking everybody's favorite ULurg, ARP220. This is measurements based on 33 gigahertz observation from Barcos Munoz 2015 and 17. And in the red dotted line, I'm showing a simplified theoretical limit for optical thick maximal starburst, which is about 10 to the 3 solar mass per year per kiloparsec squared. So beyond this limit, the radiation pressure from infrared will start to overpower the self-gravity of these simplified optically thick starbursts. So there's a lot of caveats and assumptions that go into this model, of course, but here I just wanted to show that a lot of these star forming regions do lie below these simplified theoretical limits. Well, at least most of them. So there are two really powerful extranuclear starbursts that we measured are as luminous and compact as some of the more, I guess, bright nuclei that we measure. And one interesting case is on the right, 2Zwicky 96. So this extranuclear starburst is, completely outside of the pair of interacting galaxy, but it dominates the emission in the infrared and also in the radio. So now here is a good transition perhaps to star formation. Now we know which regions are associated with HEN, so we can get rid of those and compare the rest with regions that we measure from normal galaxies from the star formation and radio survey specifically that Sean Linden talked about yesterday in his talk. And so both of these surveys achieve a similar range of sensitivity. And all these measurements that you're seeing here are done using astrodendral, using the same method. And we can see that these surveys also are probing like similar range of physical sizes as well, allowing for direct comparison between the two populations. And so what we're seeing is that the regions in the local lurks and U-lurks have about 1 to 2 dec higher star formation rate and star formation rate surface density. And I just want to highlight a couple points here. These blue points are from this beautiful nuclear ring in minor mergers 1614. So we actually detect a couple of these in the LURC survey, and by comparing them to the rings that are measured in the star formation and radio survey, we found that the nuclear ring star formation in these LURCs can account for a significant fraction of their total star formation in comparison to the lower luminosity normal star forming galaxies. And lastly, I want to mention the one caveat about the star formation rate measurements using the continuum. So we have 15 and 33 gigahertz observations in high resolution. So for a lot of these regions, we can actually measure the spectral indices between these two frequencies and perhaps infer the thermal fraction at 33 gigahertz, assuming a typical starburst SED. What we've found is that these regions in the local lurks and U-lurks, they seem to have a higher contribution of non-thermal emission compared to the regions in normal galaxies measured at similar sizes. So those normal galaxy regions are mostly thermal, like over 90%. But even after accounting for that difference, looking at only the thermal only components, we see that the star formation rate and surface density of these lurks are still higher compared to the regions in the normal galaxies. So this really is directly proving that, or showing that, why these systems are lying way above the star formation main sequence. So I'm putting my conclusion slides here, but just want to say that looking towards the future with NGVLA, with 10 times higher sensitivity, we'll be able to detect much fainter and more compact regions in these dusty systems, and not only with the continuum, but also with high frequency radio recombination lines, which can provide a direct extinction-free star formation estimates in these really heavily enshrouded nuclei. And also we'll be able to discover a lot more of these nuclear rings, hopefully, in these extreme systems, and be able to compare, have a more statistical sample of them, compare with the properties of the nuclear rings that have been widely studied in optical and near infrared in secularly evolved barred galaxies. So I will just end here, and thank you for listening.
Thank you, Yi-Cheng. Any question? Min, your hand is up. Okay, any question?
Sorry, that's a leftover hand raising hand from earlier. If there are other people asking questions, I can wait on that.
So I have a quick question. Did you find any trend with merger sequence?
Yeah, so that is a little difficult to do with our sample. I can show you here is that, the the merger sequence is not really evenly sampled in our subsample. So we only have maybe 3 or 4 mid mergers here. So that is a little bit difficult to do. But this is something that I'm working on, yeah, to try to see if the late mergers and early mergers and pre-mergers would have some differences. But thank you for bringing that up.
Okay, any other question? Okay, if there's no question, thank you, Yi-Chen, again. Okay, so I will pass the chairpersonship to Vinny.
Thanks, Jen. I'll take over from now. So the next talk is by Larry Rudnick, and it's an invited talk. It's titled 40 Years in the Desert, The Search for the True One.
Okay, can you hear me?
Yes.
Yep, good. I'm sure that most people don't appreciate the religious significance of what we're doing here, but the Israelites wandered for 40 years in the desert, just like the VLA, hoping to get to the promised land. And it is probably with some significance that we are on the plains of St. Augustine. And St. Augustine was a saint that you could invoke if you had sore eyes. And so it seems appropriate that the VLA should be on the plains of St. Augustine. And while you're trying to figure out what to make of what I just told you, here's what I'm really going to talk about today. And that is a bit of a journey going back to the early days of the VLA and our exploration of objects in different dimensions. So I'm going to start with what we could do in the very early days, which was look at 0-dimensional objects, compact sources, move to 3-dimensional ones, and then more isolated individual cases of 2-dimensional ones, and finally the true one that we're looking for, the exciting area of 1-dimensional objects that are starting to emerge. So we've talked a couple of times about very early VLA. So in 1977, we had 5 antennas and 1 program, and the program was Lister, as we've been talking about in the chat. And what you could do with Lister is you could look at all of your visibilities. And you could look at amplitudes and phases, and you could look at RMSs and things like that. And each of these points was cherished. And so some of you will be able to recognize this. This is 1328 plus 307, which is 3C286 by its 1950 IAU designation, which still warms my heart to hear those numbers. And I still remember sources based on those designations. And here is the Lister output. Actually, this is from APES, but it was very similar to what we had on site for 5 antennas. And we're looking at the left and right circular polarization. And what you can see is that the data are pretty well calibrated because the amplitudes are all consistent with each other at a flux of about 14.7 Janskis for 3C286. And down here, the phases are almost 0. So these are, nicely well calibrated data. Things are looking good. And we can do this in polarization as well with the RL correlation in the upper right and the left right in the lower left, and see the roughly 10% fractional polarization that we were supposed to get. And those of you with really sharp eyes will be able to see that we don't have the polarization angle completely calibrated yet, because these numbers should have been plus 66 and minus 66, 2 times the polarization angle of 3C286. So there was still a little bit of adjustment to be able to do, to be done. So the question is, what do we do with this kind of stuff? And the answer was there was a lot to do because of the sensitivity and the multiple frequencies and things that you could do with the VLA. There was a lot of ground to break, even though we weren't making maps at that time. We were just doing 0-dimensional objects. And here's an example of one of the early things that we did with this. And we were studying the highly variable source VLAC, the sort of the namesake for the class. And it over time had lots of fluctuations in its intrinsic position angle if you observed it over years. But the question is, how much of that was due to variable Faraday rotation, and what was the Faraday rotation of BLAC? And what we had was the black points, but the black points left an ambiguity. You didn't know whether the rotation took it down this way or you took it down this way. And one of the things that we could do with the VLA is we could tune it. So even though we only had 50 megahertz bandwidth at a time, you could move that within the band and you could get multiple frequencies within the band. And what we were able to do was to figure out what the rotation measure was of BLAC, and in fact, that it was staying relatively constant, even though BLAC itself was undergoing large rotation measures. So that's a little example of a zero-dimensional thing. It is hard to overstate how thrilling it was to be able to see the images of the things that we were mapping. I mean, we have been using at that time contour diagrams, printouts of numbers to show you the intensity on maps. We even had on the line printer overprinting to make it look like a grayscale kind of map. But to go into the apes room and see on the TV and been able to manipulate these images was really just thrilling. It was like, oh my God, that's what we're looking at. This was from a interview I posted in the scrapbook. A reporter from Minneapolis came out to the VLA site to interview me and to do a story, and you can see some of the antennas in the background. And as I noted in the scrapbook, he was trying to build his career while he still had his good looks. He figured he had a few more years and then it'd be done if he hadn't established himself. Luckily for us, we have a few more years to build our careers. That was the source we were looking at was 3C129, which I worked on with Jack Burns, and I think Jack is actually on the call with us here. And we did some detailed mapping of the front part of the tailed radio galaxy 3C129. And we were describing this as a precessing jet. So Catherine Blundell told us earlier today about precession in Cygnus A. You can see all the wiggles and stuff in here, and Vincent Ika was developing models of these precessing jets. And that this precession is important still today. In fact, it may even be more important in looking at the structure of radio galaxies. And here is an example, a very recent example by Marie-Lou Chandra-Marcellus and a group of us of NGC 1272 in the Perseus cluster. And you can see these beautiful sort of wiggles in here. And they sort of almost beg the question of how much can you go through before you completely disrupt a jet? And what we want to do is we want to use figure out when there's precession taking place, and combine that with perhaps some idea of what the orbits of the galaxies might be in the cluster, and try to diagnose the winds that are inside of clusters of galaxies, because that's what's blowing these tails around. And it's a unique probe of what's going on in the ICM if we can sort everything out. The other thing that's interesting about these precessing jets is that there's more interest now with LIGO and the possibility of binary supermassive black holes, about how their effects are going to show up either in torquing accretion disks or in orbits, and what those will do to the radio galaxies. And another thing that most of us have just sort of looked over, passed over, but I think is a new thing that's going to come out with the very high sensitivities that we're getting now from the Jansky VLA and also the new precursor telescopes, is strange features in the intercluster medium. And I invite you to look at this sort of channel of rings here, which we have no idea what it is that we're looking at. There is a cold front in the X-rays near here, but not directly associated with it. And I think that we're going to be illuminating plasma processes. I mean, Steve Spangler got us started thinking about the plasmas yesterday. And I think that we have a lot to learn. And I think that we're going to be illuminating plasma processes that we haven't even thought about yet. The other thing that you could do with the VLA is go to different configurations and work at multiple frequencies and match your resolution. So this is work that I did with Deb Katz in the late 90s, where we were mapping spectral distributions in radio galaxies. And one of the things that we found, we developed a technique for sort of separating out overlapping spectral indices when they were on top of each other and blending with each other and being able to separate the structures. And we found here in 3C449, which Rick showed us a picture of earlier, that the flat spectrum jet, which you can see in black here, was persisting down into the lobe. It wasn't just that the lobe was getting slightly steeper, it was actually a mixture of steep radiation and flat radiation that was still a flatter spectrum radiation that was still persisting in there. And this remains a very powerful tool for looking at blended structures and pulling out their spectral capabilities. And this was a real three-dimensional object that we worked on. I had a number of students working on CAS-A, starting with Martha Anderson, and NRAO made this beautiful poster. It was one of the early posters that was done with 7 different kinds of images. And this is clearly a three-dimensional object that we're trying to diagnose the structure of from the 2D map. But in this particular case, we were able to actually do a variety of different things. We picked up on early maps of CAS-A that Rick Perley had done and others, and took some additional epochs, and were able to actually trace the motions of the radio knots and make models of how this explosion was taking place and what was lighting up these radio knots. So this is just a zoom in over on the western side. And then a later graduate student, Tracy Delaney, put this together with spectral information from Spitzer, and was able to actually create a three-dimensional model by looking at the Doppler shifts of the argon radiation here and figure out where they were along the line of sight to be able to see what the structure of the explosion was. And her conclusions were that the outer shock, the initial explosion, was in fact spherical, but the ejecta, which came out afterwards and were colliding with reverse shock, were in a band that was almost in the plane of the sky. And so very important to understand the explosions in supernova remnants. And then we've now more recently been able to find clean examples of two-dimensional structures, and they offer some real advantages. You can answer questions that you wouldn't otherwise be able to answer. So this is a cluster of galaxies, and you're looking here at the X-rays in sort of the bluish gray here. And outside of the X-rays at the end are the radio features in kind of red orange. And those represent shocks that were set up because of the merger of the galaxies along this axis. And these shock waves can tell you, very important things about the energetics and the processes by which galaxies merge into each other. Clusters of galaxies are the result of mergers that have been taking place, over the last billions of years. And the question is, how do you diagnose what the history is? And the answer is the radio can show you some of the shock structures that were set up by these mergers, and we can learn about the explosion. But the other thing that we can do is we can again start approaching some interesting questions about the plasma. So for example, what we were doing here, and this is work that was led by Gabriele Di Gennaro, that looking at the polarization as a function of distance from the leading edge. And what you could see is that the polarization went down, became depolarized as you got further down. And we were able to separate out what was coming from Faraday rotation and what was intrinsic, and start talking about the development of turbulence post-shock, which is one of the things that you want to know, what happens post-shock and how much turbulence gets developed, how long does it persist, what role can it have, for example, in particle acceleration. And the isolating these 2D structures has enabled us to ask some of those questions. And this is another example, work that was led by Kamlesh Rajpurohit. And this is the toothbrush relic, and you can see kind of why it's named that way. But what we were doing here was looking at very broadband spectra using the VLA and the GMRT. And the striking result is that when you averaged over very large regions, what you got was power law distributions, extremely good power laws, and almost the same no matter what region you went to. But the surprise there was that if you looked at any little line of sight, what you would see is curved spectra due to radiation losses. And so the question is, what's going on? How can you take curved spectra and put them together and get power law spectra? Well, it's not that it's impossible. It's just that the statistics worked out to create these power laws. And you are averaging over, when you look along over any kind of large region, you're averaging over a range of Mach numbers, you're averaging over a range of magnetic field, of ages, since any particle acceleration was going on, and you end up getting these amazing power laws, which has now been seen in simulations as well. And the challenge right now is to figure out how to take the value that comes out of these power laws and their existence themselves and turn them into a statistical characterization of what must be happening in these shock structures. Which finally brings us to one-dimensional objects, which I think really is one of the new frontiers. And this is a picture of—
5 minutes left.
Thank you.
Sorry.
Abel 2256, some heroic work led by Fraser Owen. And this is a combination of X-ray and radio emission led here by Chung Jae. And what I want to focus your attention on is two structures. One is this broad structure, filamentary structure up here, and one is this very long tail. And you're going to have to ask Jean to try to explain this because we are struggling. The question is, why is there a 500 to 700 kiloparsec, extremely narrow long tail? Is it a one-sided jet? Is it a two-sided jet that's somehow been truncated by a wind? Lots of questions about physically, how can you make and confine the jet, and what can we learn both about jet physics and from the ICM properties by studying extreme type of objects like this. And then if we look at this thing which is called a radio relic, which is associated again with shock structures due to the collision, the mergers with the X-ray gas setting off shock waves. This is the most spectacular example, and there was early work done by Tracy Clark on this as well, with lots of just absolutely filled with filamentary structures in here. And the question is, why the filament? Why here? Why these filaments? Why are they this size? Why are they this length? What about the geometry? Is it possible the whole thing is filamentary? And that it's only when you get the right resolution and sensitivity that you can start breaking out, and maybe the entire structure is just made up out of these filaments. And the filaments now are becoming much more common. Some absolutely beautiful work by Marisa Brienza, and she and her collaborators have modeled this as a decaying radio lobe, which has broken into filamentary sheet and filamentary type structures. This is another example, and actually this is an image that Fraser Owen and I made with the Green Bank interferometer. And this was the head, and we thought that maybe this was the beginning of a tailed radio source. And of course it was. This is what LOFAR sees. And we were just sort of seeing the very bright region here. But what I wanted to call your attention to is all these filamentary structures that are going on. We don't know what they are. We don't know what causes them. We don't know whether they're associated with the radio galaxies or whether they were pre-existing structures in the intercluster medium. With Meerkat, we are finding lots and lots more of these, and you can just see these filaments are everywhere. There's some new plasma physics to be learned. There's new stuff to be learned about how they're energized, where they get their particles, their fields, lots to know. So just to conclude, I want to comment and echo Tracy Clark's remarks that none of this would have been possible without lots of people. The people in the background, the engineers, the software, the system scientists, the business people, the construction people. And then of course we have the colleagues, and this is what the new Zoom meeting looks like from a conference a little bit earlier, just a month ago. And then there's all the people that you argue with. And so this is a list of some of the top people in terms of number of publications that I have had the pleasure to argue with over the year. But the most satisfying thing, I think, professionally, is that when you start losing arguments to your students, that's when you've accomplished your goals. And so I've had the pleasure of losing arguments to all of my PhD students and some of the other students I've worked with as well. And so the message to students is keep arguing with your advisors, and the message to advisors is celebrate when you start losing arguments because you have done your job. And so I'll just close to say that we've been exploring things in a variety of different dimensions due to the fantastic capabilities of the VLA. And one of the frontiers coming up now is trying to understand what these 1D structures are. Thank you.
Thanks, Larry. Are there any questions? So there is one by Rick Purley in the chat. So he says, we observed CASE at numerous epochs for perhaps 10 years, but so far as I know, nobody is continuing the effort of tracking the evolution of the nodes and filaments in CASE. Has anybody taken up this effort?
Well, I think that the answer is yes, not in the radio so much. It turns out that the model that Tracy was able to put together showed that all of the emission, the radio emission and the infrared emission and the optical emission and the X-ray information, all of them have moving knots. And the question, and they're all on the same ring, and they're all moving with different speeds. And so the question is, how is that possible? How can you have a bunch of things at different speeds that are all in the same place? And the answer is that the reverse shock is moving its way back in. And as little clumps of plasma are interacting with a reverse shock, they get decelerated, heated, particle acceleration, magnetic field amplification, and the things that you see in different wavelength bands represent different densities of objects that have been decelerated by different amounts. It's not clear to me how much more there is to learn from tracking the radio blobs over time. We had hoped to study particle acceleration. That was the original motivation in there. It's not clear. It would be good for people to take a fresh look at this. I don't know that anybody's followed up on the radio. There have been lots of follow-ups in other bands.
Are there any more questions? So,
I would have a comment. Yes, Larry, you showed various objects, including 3C40 at the bottom right of your graph that is still up. I've been observing first M87 in my master thesis and 3C40 in my PhD thesis at very low angular resolution with the Effelsberg telescope. But already at that time, I was struck by the large variation in spectral index, spatial variation, but still the integrated spectrum is perfectly straight. So that reminded me of your comment. And I would like to learn more how this is possible.
Right.
But
so
you don't need to answer the details now.
Okay. And of course, I mean, M87, Fraser's old maps showed you the filamentary structure. We've known about filamentary structure inside of lobes for many years. Now we're starting to see filamentary structure outside. Clearly, anytime you add together things with sharp cutoffs, you're going to tend to smooth out the spectrum. But generating good power laws is still an interesting challenge.
Thanks.
Okay, if there are no more questions, maybe we will move on to the next speaker. So our next speaker is Sancheta Bortakur, and she'll be speaking about connecting the H1 disk to the circumgalactic medium, successes from the past and outlook for the future with the VLA.
Thank you, Vinay. First of all, thanks to the organizer for
giving me this opportunity to talk here. This has been such an exciting meeting, such diverse topics, and I feel very, very fortunate and privileged to be speaking in the same session as some of the renowned radio astronomers that I have looked up to, including my thesis advisor, Mignon. So today I'm going to talk about something that we call the circumgalactic medium, which is also known as the halo of galaxies. It is generally not seen in imaging because it's very, very faint. But the idea that there is this gas that is feeding the galaxies is something that we are getting more and more evidence of. And today I'm going to talk about how VLA can really make a very big difference in our understanding of how galaxy disks are growing and in the process getting more fuel to form more stars. I might win the contest for the longest title. So I want to sort of simplify what's the theme of the talk. So the simple idea is that we see galaxies even at higher redshifts, and today they have star formation rates that would imply that they use up most of their gas very quickly, at least well shorter than the Hubble time. For them to continue star formation, they have to be acquiring gas. And this is something that we sort of know, but we don't know how. And that's the idea. We want to know how exactly gas gets into the H1 disk. So let me start with this very simplistic schematic of something we call the baryon cycle. The idea is that baryons, or material in general, move around within the galaxy and also come into the galaxy from the intergalactic medium. And it goes through this halo, which is the circumgalactic medium. I'll be using this term quite a lot during the talk. It is 99.9% of the galaxy by volume. So it is an important component. And it can contain as much mass as the stars in the ISM put together. But it's very faint, so we can't really see it directly. In our current theory, what we believe is that the circumgalactic medium condenses into the interstellar medium, the 21 centimeter disk that we can see with the VLA or other radio telescopes. And then the gas moves around quite close to the center of the galaxy and then forms stars, which we can see in various optical emission, UV, and radio continuum. These stars produce galactic winds, the material moves out in the circumgalactic medium, the process continues. Now, this is exactly what I'm going to try to figure out with two different projects. These are two large VLA programs, and I'm going to talk about primarily one program which we finished acquiring data about in 2019, and we are processing the data right now, and another large VLA program which we are acquiring data as we speak, and we'll be acquiring with the current C configuration and the B configuration that's going to come later this year and next year. So we call this program the DISC survey, which stands for deciphering the interplay between the interstellar medium stars and the circumgalactic medium. Pretty self-explanatory. And since these phases don't show up in any single frequency, it's a very multi-frequency study. It uses HST to look at absorption spectroscopy of the circumgalactic medium, VLA to look at the ISM and radio continuum. UV comes from the GALAX survey, surveys, H-alpha optical studies, which we are conducting, and so on and so forth. It's a very diverse team. I have sort of highlighted people with the color where they are most contributing to, but it's a very big effort from all these people. So just to start with this, what we're trying to do is we have the sample, which is very special because these are galaxies at low redshifts where we can actually take images with the VLA. And they have a background UV bright quasar that allows us to map the CGM. This has never been done before. There have been many studies of H1 in galaxies, but the idea that we can combine the CGM and the H1 data together to see the flows is the first time we are doing so. Particularly for the VLA data, I think I want to stress one very important point, that we are going very high resolution in terms of the spectral resolution. It's about 1.7 kilometers per second. And some of you might think it's an overkill, but from our past experience, we have seen absorption lines at 1 kilometer per second. We have also seen clouds that are coming out. If you're expecting a small region, star forming regions to produce an outflow, it's not going to be 20 kilometers at 20 kilometer resolution, so you may not be able to see it. So this is something very, very new that we are trying to do. Image 35 galaxies at 1.7 kilometers per second. Now, just to give an idea of the galaxies that we are looking at, these are very, very sort of common galaxies, and lots of people have studied in the past. Some of these are mesosphere galaxies, M61, M100, M95, and then these NGC galaxies very nearby, very well resolved. We have a whole bunch of data on this so that we can actually trace different components. Now, I want to sort of jump right into some of the results. I'm going to show very few highlight results because I have lack of time, and I'll probably go through the slides very quickly because since we have a diverse audience, I'm not sure which ones will be most interesting. So please ask me questions. I'll come back to the slide and describe the details if you're interested. But simply put, one of the main ideas is to see how far the disks extend, even outside where the VLA can image. Is there something rotating? And the idea is very simple. We have VLA images shown in contours here. The kinematics is shown over here. We get spectrum of the quasar. We can see exactly where the velocity of that gas is right at this point, which is shown by quasar absorption lines. And then I'm going to just trace the velocity from here out to the edge of the disk and then to the quasar. In this galaxy, it's shown by here, the VLA data, here's the quasar, and it turns out that in most systems, we find that the circumgalactic gas, which is not seen in the VLA, is rotating at pretty much the same velocity as the outer disk. So what we find is co-rotating extended disk or CGM interface, which can contribute approximately 10% of the mass of the galaxies and probably feeding these disks in the long term. And this is very important. The kinematics and the size of these extended disks is particularly important in terms of understanding gas accretion. There are simulations that predict how these gas blobs come and join the disk. And having that information is really key to understanding the cosmological implications of disk buildup. And we have lots of different simulations that show these large extended disks. One example is here, it's a 100 kiloparsec disk. The H1 disk will be around 20 kiloparsecs. So you really expect really large rotating disk, and which is what we're seeing. So that's number one. And this is what probably the main motivation of the study is. But having said that, we found something very interesting. And on second thoughts, we should have expected that. Here is a complicated plot. So let me just go over what I'm plotting. There are two different colors. One is black, which shows the H1 spectrum, showing the interstellar medium, the rotating disk. That's that. And then in blue, I am showing the quasar absorption lines about 20 to 30 kiloparsec away. What we find is that there's a lot of absorption matching the velocity, but then we find these systems which do not match the velocity of the disk. And in Milky Way, we find such things, and we call them high velocity clouds. Now, a lot of studies have been done in the Milky Way, and we were not 100% sure if this can be extended, but now it looks like high velocity clouds exist in most Milky Way-like L-star galaxies. Here is just an example, but I'm going to just show you another set of examples where you see these high velocity clouds showing up pretty much in every galaxy if you look about 2 to 3 times the distance from the H1 disk of these galaxies, and they are pretty much ubiquitous. To add to that, I want to go to a specific example. This is M61, where we are fortunate to have a quasar that goes through the disk. And here is an example of the H1 data that we have. So that's the optical galaxy, that's the radio continuum from 21 centimeter, and that's the quasar. And this is exactly the same stuff in velocity. So I can pull the velocity of the gas, the ISM, and I get them the velocity about 70 kilometer per second. And if I look at the quasar, I'm sorry about that, quasar spectrum, what I find is that I see the ISM absolutely at 70, but I also find something which is like the high velocity cloud at
2 minutes
345
left.
kilometers per second. Thank you. All right, so basically what we think is that this is stuff that's probably flowing in because there is no star formation to sort of generate that kind of outflow. All right, I want to quickly go over this new disk survey, which we are just getting data, and we don't really have a whole lot of results except for one galaxy where we're trying different things. And I'm going to quickly go over some of these slides. So please ask me a question if you want to know more. But this is another large VLA program, about 300 plus hours, and currently observing in L band and C band. And what we're getting is these very high resolution spectral and spatial resolution images of 14 of these galaxies. And what we see is we get kinematics of the disk. We can sort of trace the ISM and the outflowing gas or inflowing gas in different cases. We can also model the disk as tilted ring models. These software exist. We can measure the position angle, if there is warp in the disk. And interestingly, at least in this case, we find that the position angle shows a warp where at the edge of the stellar UV disk. So this has been predicted for and seen in many galaxies that star formation and warps are related. We also see radial motions within the gas towards the spiral arm. So we can really see how gas is moving in the disk and even from outside into the disk. We can actually subtract the model to identify clouds that might be flowing into or out of the galaxy. This is work led by Hans-Ung Kim, who is talking next. There are many other things we can do. We can identify, do a resolved star formation law, which means that we can really pick out regions, different parts of the disk, and see how star formation and gas density matter in terms of the star formation law. And we see that star formation efficiencies drop. This has been known for a really long time, and we want to see why is that. And we can do that because now we have the data, we have metallicity information, etc. also, which I'm not showing here. But this is going to be really interesting to do a resolved star formation law. We also have radio continuum. We have UV, you have IR, we have H alpha. So we can try to see how these ratios change. And here is one of the very preliminary results, which shows the 3 different regions of this disk: inner, intermediate, and outer disk. And what we find is that the star formation rates that we calculate from UV plus IR and the radio continuum, the ratios change in the 3 different regimes. It could be because of some kind of star formation history or metallicity or stuff that we haven't explored yet, but this is very interesting to see that these indicators vary even within part of the galaxy. Similarly, these data allow us to measure kinetic energy line widths at very high resolutions compared to H alpha or UV data for similar individual clumps, where we can see that we can model the kinetic energy and see if the star formation rate, the supernova rate, is enough to generate these. People have also used power spectrum of the H1, which we are planning to do, to identify what kind of turbulence exists in these systems, whether it's cosmograph or more like a 2-dimensional sheet-like turbulence, which all have implications in the long run for star formation. Sorry, this is all these different things we can do. So if you're interested, please ask questions either here or later through Slack or just reach out to me. And I'm stopping here and leaving the conclusions from the previous program, which just showed that these disks are much, much larger than what we initially thought, maybe 2 to 3 times larger. And they can contribute to a significant amount of gas inflow. And we also find that recycling of material is going on. These are particularly interesting because they're metal-rich material that might help in future star formation. So I'll stop here and take questions, and thank you for listening.
Thank you, Sanchita, for the nice talk. Anybody have any questions? So there's one by Ilsang Yoon. Does your study make any suggestion or insight on whether gas accretion is clumpy or smooth continuous?
Yeah, that's a very good question. So far, we don't have a very good estimate because we do not have a good covering fraction. But if I can just, based on the little data we have, it seems like we are seeing these smaller clumps of gas coming in, but they are in a rather continuous part. They are not randomly distributed. These are not virialized systems that just randomly flowing into the disk. What we believe is that there could be these flows which have these like denser clumps, but they are part of a flow, or we are seeing this recycling of material, which is basically one of the fountain models, a prediction where you push ISM out, it stays in the CGM for a little while and then sort of lands in the different parts of the disk. So that's kind of what we are seeing, but at this point, we don't really have a very solid definition to distinguish between the two. Thank you.
So since we have run out of time, we'll move to the next speaker. Thanks again.
Thank you.
The next speaker is Han-Sung Gin, and he'll be talking about VLA disk, tracing the baryon cycle by mapping the interstellar medium at the Carl G. Jansky VLA.
Okay, thank you. Can you see my screen?
Yes, please go ahead.
Okay, thank you. Hi, I'm Han-Sung Kim, a postdoc at the Arizona State University. Since Sanchi gave a good introduction of the whole program, so I just focus on the preliminary result and our recently submitted papers of the H1 study at the Carl G. Jansky VLA. This study is being performed with Sanchi at ASU, and Immanuel Mamjan at the NRAU, Timothy Hengman at JHU, and other fantastic teammates. And before going to that, actually, so first, personally to me, so it was a great opportunity working on the VLA data and then with the NRAU peoples. So after the first visit to the AOC Socorro at 2011, I visited the AOC several times and meeting with the people. Every moment at the NRAU was very precious to me. I got a PhD degree with the VLA data and currently working on the VLA data too. But I want to share the one memory at the guest house. This is not the most memorable event, but the unforgotten memory to me. On November 10th, 2013, at the AOC guest house, the snake, a snake is trapped at the hinge of the door in my room. So this poor snake was still alive at these scenes. So okay, I just want to share that. Okay, it is a little bit hard to start with the science talks, but the why we should study the H1 in the galaxy evolutions. It is because the H1 atomic hydrogen is the root of the baryon cycles from the sucking galaxy medium to the molecular gas, and the most sensitive tracer of the galaxy kinematics of the structures at large radii. And it is also future fuels for the star formation and agent activities, while H2 is the immediate fuel for the star formation. And also it offers the best tracer of the tidal interactions and accretion to the galaxy. Actually, so there were several projects or several surveys of the H1 emissions for in the local disk galaxies. But why do we revisit local disk? Initially, our sample was selected by alpha alpha and high pass with a low angular resolution. So we need to localize the ISM of the local disk galaxies at the very large array. And also the several galaxies were observed previously at the VLA, but with the velocity resolution larger than the 10 kilometers per second. So the Jansky very large array offers the better velocity resolutions. So we can observe that with the high velocity, high spectral resolutions. The goal of the VLA disk is to inspect the H1 properties such as H1 distributions, structures, H1 mass, baryonic Tulip-Fisher relations, the H1 deficiency, and H1 asymmetry. And also we are investigating the H1 kinematics, such as the kinematics of the rotating H1 disk and the anomalous kinematic gas clouds. And the observations were performed from 2017 to until now, and then most of them were observed at the D configurations. And then for some massive galaxies, we have observations at the C and B configurations. The total integration time is about 350 hours for the D configurations. And then the velocity spacing is the 1.65 kilometers per second. I just showed some galleries of the images, H1 images we made. This pictures shows the column density over the optical images of 34 galaxies. And then velocity fields are shown here. Traditionally, the redder colors indicate the higher velocity, and the blue colors indicates the low velocity. And the same for the velocity dispersions. And also we calculate the H1 kinetic energy surface density by multiplying the H1 mass surface density and the square root of the velocity dispersions. And but the regions are saturated, but this is the preliminary result, so we need to inspect more detail. And among the 35 galaxies, I introduced the recently found result of the M100 in the Virgo clusters. I prepared the 6-tier cakes for the birthday of the VLA. The M100 was investigated by the Van Gokom and Kotani at first at the very large array, and then after that, after their pioneer works, there were several studies studying the H1 emission of the M100. Their studies revealed many aspects of the H1's distributions in the M100, even though those were limited by the poor spectral resolution at the VLA, such as like the velocity resolution of 10 kilometers per second or larger. We achieved the angular resolutions like this, but with a higher spectral resolution of velocity resolution of 3.3 kilometers per second after the Hanning smoothing. Thanks to the higher spectral resolution of the Kaji-Jansky VLA, we discovered two H1 clouds with anomalous kinematics from the rotating H1 disk of M100. Here we define the AHC as an anomalous H1 cloud. I just summarized the factor of the AHCs of the M100 here, such as the channel maps, position velocity diagram, spectrum, and the star formation activities traced at FUV and H alpha. The channel map shows that these anomalous anomalous H1 clouds have a distinct kinematics from the rotating H1 disk. And also we estimated the velocity offset of our AHCs from the rotating disk by about 40 kilometers per second. And the star formation activities shows that the AHC1 has an associated star forming region traced both at HPV and H alpha, but AHC2 does not have. Actually, there are some scenarios for the AHC formations, such as galactic fountain, land pressure, tidal interactions, and dwarf galaxies. Actually, so the AHC1 has associated star forming regions, so it could be explained by the galactic fountain, as it is the star formation driven outflow. And also we have to consider the land pressure stripping because M100 is in the Virgo clusters. It's plausible, but the M100 was classified as a pre-stripping galaxies by the UNEROR. So we cannot argue it strongly. And then also tidal interactions with the NGC 4322 and 4328.
2 minutes left.
Thank you. Are companions of the M100, but we cannot see the tidal tails in our H1 data, so we cannot argue it strongly. And however, the dwarf galaxies is a possible candidate, but our AHCs are placed in the with a galactocentric distance of 13 to 16 kiloparsecs from the center. So at the positions, H1 in the dwarf galaxies are not survived. So we can say that no single scenario explains the AHC formations. So that the multiple mechanisms might influence the formations of the AHCs in M100. I just like to wrap up the talks. The Kaji-Jansky barrier array offers the great opportunity to explore the ISM of the local disk galaxies with higher spectral resolutions. We completed the deconfiguration observations, and then we are investigating the H1 properties and kinematics, and also we found 2 anomalous H1 clouds in M100 with higher spectral resolutions at the Kaji-Jansky barrier array. And then one thing I note too, that we need a higher angular resolution data too, in addition to the higher spectral resolution. This NGC 3344 shows the deconfiguration only and the DCB configurations. When we compared that, DCB configuration data shows the more detailed structures of the H1 emissions. So we need a higher angular resolution. So to do that, we launched the XVLA disk, as Sanchi talked about that. Okay, this is done. Okay, stay tuned. Thank you.
Thank you, Han Sang-Lim. Are there any questions? Sorry, there is a question by Christina. Oh, sorry, that's not a question. Okay. Are there any questions? No. So I would like to ask one. So is the AHC seen in only M100, or are there other galaxies which shows are there other galaxies in your sample which shows AHC?
So we are working on that. Yeah, but not now. Yeah, we will trace the AHCs in other galaxies. It's one of our goals.
So what is the relevance of the AHC? Meaning from literature, are there other examples of AHCs from the literature?
AHC is the hydrogen clouds with the distinct kinematics from the rotating H1 disks. It's like the intermediate velocity clouds or high velocity clouds, or as the extraplanar gas shown in the vertically extended from the disk.
So if are there any other questions? Okay, if not, let's thank Han Sang-kim.
Thank you.
So those were all the talks for before the break. So I'll hand over to Anna if she has announcements.
Nah, probably I'm good this time around. So we are now coming back at 3:45, so it's 25 minutes. If any of the speakers of the very last, after the break, would like to check their screen sharing, we can do it at any time during the break.
Anna, can you hear me?
Yes.
Oh, okay.
Oh, you were, sorry. I'm really tired by now. I didn't see you were raising your hand.
Okay, let me see what happens if I try to
Of course.
play my. Can you see my first slide?
No.
So I have to somehow do a screen share.
That's right. There is this green icon at the bottom of the screen in Zoom.
Well, I don't see the green icon at the bottom of the screen, unfortunately.
Hang on. Oh, maybe you were already, no, but we should have, 1 second.
Do I have to start my slideshow?
Not necessarily. Sorry, I'll show you what I can see and where it is. So when I'm looking currently, oh, hang on, what are you seeing? Not much. Hang on, something is wrong here. Share screen. Oh, yes, sorry, my bad. Zoom doesn't like to show itself. 1 moment.
Jim, do you see the chat icon?
No, on my computer itself, I see the presenter view, and on my other monitor, I see the slide that everybody else should see.
Yeah, when you put your mouse over yourself, you should see the little bar come up underneath, and that shows the chat bar and the share screen bar.
Right. Let me go back and end my show.
Yeah.
Okay. Now I see a share screen.
Yeah. Okay. Good.
You cannot start a share screen while the other participant is sharing.
You can do now.
Okay. Now I can start my show. Can you see that?
Did you, so you selected which screen and then did you click share?
I started the share screen. I can swap displays here. Does that help?
You should choose the screen that shows all your screen and then select the window where you have the presentation.
And then click share button, which is blue.
Okay, I just ended the show again. The only time I can see the share screen is now.
So you click the share screen.
Right, and it says desktop 1 is being shared.
Not yet. So you click that you want to share the desktop 1, right?
Okay.
And then at the bottom of that window, there is a blue button share.
Okay. Press that. Allow Zoom to share your screen.
Yes.
Open system preferences. So, okay, so I'll put on Zoom.
Are you good? Do you want me to help you?
Let's see, choose to quit Zoom or do it on your own later. I'll do that later.
Yeah.
No, I think you probably have to restart Zoom.
Can I?
I have a guru coming by.
So you want to?
Oh.
We're now screen sharing.
And then.
Let your site play from start.
And then, so we're seeing now the presenter mode.
Okay, so let me.
So you have to switch the screens, I guess.
Oh, yes. Yes.
All right.
Well, is the guru coming again?
Yeah, I can stay here. So I'm in this session as well.
Like in 20 minutes?
Yeah, in 20 minutes I will be around.
Okay, cool. That would be fantastic because the other speakers may want to try sharing their screens. So that would mean that we'd have to stop sharing and then start again for Jim.
Yeah, including myself.
Does it make sense?
Yes. Here. All right. Right.
Okay.
I will be back in 10 minutes.
Okay, and what do I have to do to restart?
No, you're good. You're good to go.
Okay.
I think he'll come over and will help again. I think that's what he said. Who else we have there? Tom, Eric. Oh, there are 3 talks. Okay. Tom and Eric. So
There are 4 beyond Imans.
Oh, sorry. So what am I missing? Jörn. Yes. Okay. Sorry, I missed badly. Yeah, like he is here. His name is just in the wrong place. Oops.
Hi, Anna.
I'm so sorry, Björn.
No problem. Should I try to share my screen?
Yes, please. I just in a PDF. I just merged your name with the title.
Oh, no problem. Let's see if we can get this going. You see this?
Yes.
Oh, this is
Still slides, like all of I see 3 slides.
Oh wait, I need to start the presentation.
Yeah.
Now you see it, no?
Yeah.
Yes.
Great. Okay.
Okay. Cool.
Okay. Thanks.
Tom and Eric.
Should I try to share my screen?
Yes. Yeah, perfect. Here for it. And is Tom online or away from the screen? He might be away from the screen. Okay. Well, we have so.
Tom tested his earlier.
Oh, okay. Sure. Cool. We still have over 15 minutes. Break. I think we have still 5 minutes. I was just wondering, Jim, how are you doing? Oh, wait a second, you're muted. I'll ask you to unmute.
Okay, yeah, when I start, do I have to hit the share screen first and then start my PowerPoint, or can I just start?
Whoever was helping, they know best.
That was Eric. And Jim, yeah, you'll have to share screen before you start your presentation.
Okay.
I can
share your whole desktop.
You can actually do it both ways.
Share screen first and then, yeah, then start the PowerPoint.
Brian, how can you see who is helping? I only see a little bit of mask in the corner.
Well, I just recognize Eric. I've seen him in enough Zooms now.
Oh, I see.
Okay.
Ow. Boy. Given that it's been a very long meeting packed with a lot of good talks and discussions, there is quite a good participation thing going for the last hour of the meeting. I think when people come back from the coffee, we'll be back to around 8 or something. Well done, everyone.
Anna, this is Heinz. Just a question. What are your plans for the PDF files of the presentations? If you plan to offer them, I would like to submit.
Oh, I meant to actually email.
Version.
Maybe I'll email during this next session because Bini is chairing that. Yeah, I'll put on. I'll put up the slides on the website within a day, and we will do also. We will share the recordings, but we have to edit them first because they are recorded in one go. And sometimes I was forgetting to turn it off and we have the whole break and something. Yeah. So we just have to chop it into the talks. So that will take a little bit longer.
Yes, I'm just asking to tell people what to do with the PDF files. I did some edits in the last minute and I would like to upload the most recent version.
Sure. Please do. Mm-hmm. If you do, the best one would be probably either let me know with actually I will see the date when it's uploaded, so I may take just the latest version.
Yeah, so it would be good if you tell people what is going to happen with those PDF
Oh
files.
yes. So when we are during the closing time, there's a 5 minutes goodbye that Frank will convey. He will mention a number of things like that. And I will also send an email.
Okay.
Right, did you manage to get one of our photos yesterday?
Are you talking to me?
No, to Ray Norris.
Oh,
So I was trying to find the mute button. Yeah, I did. Pardon me. Yes, I did. Thanks.
No worries. I was just because I probably email about that one too to everyone who has not had the chance to be on a photo.
Yeah, I think I was in 2 actually. So
yeah, I will take the
overrepresented. That's a good idea doing that.
I would just say. Sorry.
I said it's a good idea doing that.
Oh yeah, it was just too many time zones to expect people to show up one time.
Yeah.
So I'll just And I probably will have people from the different photo shoots, so I'll take the best shoot. You have to just trust my judgment, as I said last time. Oh. We can start probably in a time, Benny, if you'd like.
Okay. So welcome back everyone for the final session of the conference. So we'll start with the talk by Jim Condon, who will be talking about the star formation history of the universe.
And you see my slide.
Yes, but not in presentation mode.
I think you have to stop sharing. Okay, switch it around.
Yes, now we can see it.
Okay, thank you. This project to determine the star formation history of the universe makes use of the VLA in a way that just wasn't imagined when the VLA was first proposed in 1967. At the bottom of this slide is the list of people that have been working on this project. And I point out in particular my former University of Virginia graduate student, Allison Matthews, for which this project was her PhD thesis. And she just finished up and will be going to Pasadena in another month to start a Carnegie Fellowship. The star formation rate density, psi, is the parameter that's normally used to measure the star formation rate on cosmic scales in a universe that's spatially homogeneous, but evolving with time and expanding so that the useful units of psi are solar masses per year per co-moving cubic megaparsec. And the standard result that everybody has been using is the Maddow and Dickinson result shown here, which plots psi as a function of redshift and look-back time. It can be measured by any tracer that consists of very short-lived stars, which means extremely luminous massive stars that mostly emit in the ultraviolet. So that the purple, green, and blue points on this diagram represent ultraviolet estimates of the star formation rate density, suitably corrected for dust absorption. The real problem with far infrared is that, the real problem with the ultraviolet is that most of the ultraviolet is absorbed by dust and re-emitted as far infrared radiation. That far infrared radiation is used to recalibrate the ultraviolet to make it agree with the far infrared. And the far infrared has the limitation that it's difficult to have enough high angular resolution to be able to go very deep. And finally, the properties of dust are not very well understood at high redshifts, so that there's always a concern about dust bias or, for that matter, dust contamination by cirrus and so on. So what is an alternative way to measure star formation is radio continuum emission. The decimeter wave radio continuum emission from stars comes almost exclusively from stars more massive than 8 solar masses, whose lifetimes are less than 30 million years, plus some free emission from H2 regions from stars that are even more short-lived. So the way you could measure the cosmic star formation rate history at, say, 1.4 gigahertz is first to determine the local luminosity function of star-forming galaxies, convert the radioluminosity function to a star formation rate using the far infrared radio correlation, which is our only legitimate way of getting the star formation rate from the synchrotron radiation. I always say that before the discovery of the far infrared radio correlation, continuum observing of spiral galaxies was a hobby, but now it's a science. Once the local properties have been determined and the local star formation rate today has been determined, then what we want to do is evolve it to higher redshifts. And that would require determining the sky density or source counts of sources that are powered by star formation. And the difficulty here is that star formation is only traced by the radio continuum emission. It's down by a factor of more than 10 to the 5 from the bolometric luminosity. And as a result, you need extraordinarily high sensitivities. At 1.4 gigahertz, our galaxy at a redshift of 4 is about 1/4 of a microjansky. And this was the sensitivity limit that was chosen by the SKA mid people when they were designing the SKA mid deep survey. And it's the goal that we've actually reached by nefarious means, namely the P of D distribution. And once the features of the source counts have been determined with sufficient accuracy, and the local luminosity function has been determined with sufficient accuracy, the evolution function of psi that matches the local luminosity function to the source counts is actually sufficient to determine the evolution of star formation without having to make identifications of individual galaxies, without requiring stacking, without really requiring much of anything at all. So stage 1 is to determine the local luminosity function. And that's a statistical property of nearby galaxies. So you want as many galaxies as possible. And the only way to get as many galaxies as possible in the nearby universe is to observe most of the sky. So we determined the local radioluminosity function at 1.4 gigahertz separately for star-forming galaxies and active galactic nuclei by cross-matching the 2-mass 2-micron sky survey, which is spectroscopically complete down to a magnitude of K equals 11.75, and matching that over 7 steradians of sky with the NVSS. So that it turns out that this luminosity function is limited by cosmic variance and can't be significantly improved on. Now, it looks like it's rather poorly determined at the very low and high luminosity ends, but they don't really matter. What really matters is not the space density of these sources, but the energy density produced by them, which you can get by multiplying the luminosity function by the luminosity of the individual galaxies. And so these two curves show the local luminosity function at 1.4 gigahertz. The blue line corresponds to star-forming galaxies, the red one to active galactic nuclei, and the green curve is the sum of the two. And remember this double-humped shape because it will turn out to have a very simple relation with the source counts. And you can see that the areas where the energies are highest, near the peaks, have very small uncertainties because those are the galaxies that are easy to detect. And the galaxies, say, down at very low luminosities are not well determined because only a few have been detected. But in any case, they're down so far that they don't matter. The next stage in going from the local luminosity function to the far infrared radio correlation is critical to get the star formation rate. And so we used over 4,000 galaxies in this same sample, selected only the sources that were stronger than 5 millijanskis, so that nearly all of them have IRAS far infrared detections. And we can make a plot of the far infrared radio parameter Q as a function of the log of the luminosity. And you'll notice that it's not a horizontal line. That is, the far infrared radio correlation is not a simple linear correlation. And the slope of minus 0.15 is not unlike the slope that was already determined by Ivan Delecchio. So using this as the far infrared radio ratio, we can calibrate the local star formation rate as 0.0128 solar masses per year per cubic megaparsec. Now, at this point, we no longer concern ourselves with anything but radio data. And we just make the assumption that the far infrared radio correlation is independent of redshift, but does depend on luminosity as shown. Now, what we need next is how many radio sources are there out to down to about 1/4 of a microjansky. And for that, we don't actually use the VLA, but rather the NG VLA Pathfinder, AKA Meerkat. Meerkat is more like the NG VLA in the sense that it has a fairly large number of antennas, 64, so that the dynamic range of an image can be quite high. And also it's using offset unblocked apertures the way the NG VLA will, so that the sensitivity is extraordinarily high. There are 64 13.5 meter diameter antennas here, but each one of those antennas has the same system noise temperature in Janskys as a VLA antenna that's 25 meters in diameter. So that after 150 hours of observing over a field of view that's more than a degree, because these are small antennas, we get the image shown here that is well and truly confusion limited. We can make use of that confusion limit and the beautifully Gaussian noise that comes from aperture synthesis to do the confusion amplitude distribution in this map. We're not concerned now with the individual sources, but rather every pixel in the map, or every independent pixel, which is essentially every synthesized beam. The dotted curve here on this semi-logarithmic plot has a parabolic shape, and it's a Gaussian, which accurately represents the 0.57 microjanskys per beam RMS noise down to a level of at least 10 to the minus 3. It's amazing how Gaussian the noise is. The heavy black dots are the actual amplitude distribution in that map after the correction for the primary beam attenuation. And it is the convolution of the Gaussian noise and the noiseless P of D distribution, which Allison generated by simulations to make this map and to make the match, so that the solid curve is the actual P of D distribution that we would get with a 7.6 arcsecond beam if we had no noise at all. From that, we can deduce the source counts. Above, well, look at first at the top plot. This is the normal way to plot source counts in a static Euclidean universe. Above 2.5 millijanskys, we counted sources from the NBSS, which is most of the sky. Between 10 microjanskys and 2.5 millijanskys, we counted the tens of thousands of discrete sources in this Meerkat field. And below 10 microjanskys, down to 1/4 of a microjansky, you can see the counts implied by the confusion amplitude distribution. The heavy line is the best fit, and the light colored curves are the 1 sigma errors, so that you can see that the source counts have been determined over 8 orders of magnitude with extremely high precision. Now, I prefer to show the source counts in the way that it's in the bottom plot, where it's weighted by the brightness of the contribution of sources, so that the height of the curve here is proportional to the sky brightness temperature contributed per decade of flux density. you can see that half the sky brightness at 1.4 gigahertz is contributed by the star-forming galaxies and the other half by active galactic nuclei. Now we try to model these source counts using our local luminosity function, or rather the local energy density function, which, to remind you, is in the upper right-hand corner what that looked like. In the main plot, what we're plotting is the source counts contributed by star-forming galaxies, that's the heavy blue curve, and by active galactic nuclei, that's the heavy red curve, and the sum, the green curve, which ought to match the data points. Now, it clearly doesn't. And furthermore, these light-colored curves show different epochs of the universe. Each curve corresponds to one more gigayear of time. So that this curve here, for example, is the star formation contribution to the source counts below a microjansky from star-forming galaxies between 12 billion years ago and 13 billion years ago, which is going out to a redshift of 10 or so. Now, how are we going to make this green curve match the data? Well, we can choose either density evolution, which says there were more galaxies in the past, and that would just move the source count in some redshift range straight up. We could choose luminosity evolution, where every galaxy's emission is stronger because there's more star formation, and that moves equally up and to the right. And so you can see, for example, to get from here to what we want, oops, I moved ahead. In order to go from where we were to where we want to be, we have to move up and to the right. So we considered a whole range of luminosity functions and their evolution, and finally came up with a match to the source counts. That is really quite a good fit and tells us how quickly the rate of star formation had to go up in the past in order to match what we see now. And the match is very good, and it accounts for at least 99% of the sky brightness from star-forming galaxies and AGNs, so that at lower flux densities than a quarter of a microjansky, I don't think there will be much more to learn about the star formation history of the universe. The background that we predict at 1.4 gigahertz can be compared with the background measured at 160 microns as a function of either 1.4 gigahertz flux density or 160 microns flux density. Blue curve is the radio curve, and the red one is the 160 micron background determined from Herschel. And of course, the total background is confirmed by Kobe. And indeed, we seem to have accounted for more than about 99% of the total background. So what do the evolving luminosity functions predict for the star formation rate? And this is our result, in which I've plotted as a function of time since the Big Bang or redshift. And I like it to be as a linear function of time since the Big Bang, because after all, the star formation rate density is measured per year, not per Z or something like that. So a much more realistic view of what the star formation rate evolution looks like is given on this type of plot. The black line is now the McDowell and Dickinson plot based on infrared and ultraviolet data. The heavy blue line is what we determined at 1.4 gigahertz. And the two thin blue lines are the range of acceptable fits using the standard MCMC way to search parameter space. Roughly speaking, for times between now and say a time of about 3 gigayears, which corresponds to a redshift of 2, the star formation rate density can be accurately described by an exponential growth with a time scale of about 3.2 gigayears. At earlier times, it clearly has to fall off, or we would have higher source counts than we actually observed, down to 1/4 of a microjansky. And you'll notice that the error bars grow very rapidly at the earliest times, or at the highest redshifts. And that's because decay correction is very unfavorable for sources that have spectral index of about -0.7, typical of optically thin synchrotron radiation. So that out to a redshift of maybe 4, we have a pretty good idea of the star formation rate density from the radio continuum alone. And at higher redshifts, that's really going to be the domain of the far infrared people and ALMA, where they can benefit from the negative K correction. I want to finish up with a quick comment about how does this relate to the history of the VLA. The VLA initial proposal was made in 1967. As you can see from the summary in chapter 1, the thought was that each observation would take 8 to 12 hours. And the main goal, the one that actually convinced Jesse Greenstein of the Greenstein Committee to recommend the VLA to be funded, was to do source counts. But of course, of AGNs, not star-forming galaxies, which hadn't really been appreciated yet. The source counts, even though they were the main goal, were dropped not too long thereafter. So that 5 years later, in 1972, when Barry Clark was trying to think of use cases for the VLA, he made this trenchant comment: observer B wishes to measure the log N log S relationship at all 4 VLA frequencies. Because he is rather discouraged by what the relation has done for science so far, he decides it's worth only a half a day at each frequency. Well, fortunately, the VLA turned out to be a lot better than was thought. And it's possible now to really do something like that. So my comments are, first, is 40 years is forever in radio astronomy. And that's echoing the comments that Ron Eakers made as well. That if you're building a satellite that's going to do one particular project and then run out of gas in 5 years, it makes sense to try to make a scientific justification and say exactly what that satellite will do and why it's worth putting up. But if you're building an observatory like the VLA or the NG VLA that's supposed to last for 40 years, it's a fool's errand to try to say what it will do. And nearly everything good that the VLA has done was either not predicted in the first place or done in a different way, or otherwise not predictable. And so even though the actual scientific justification that was submitted for the VLA contains almost no science and mostly performance, that's really what was the best way to go. And then my last comment was, I clearly used Meerkat to do the deep observations instead of the VLA, but the Meerkat is really an NG VLA pathfinder and looks a lot like the NG VLA, except it isn't quite as big and doesn't go to such high frequencies, but stresses the utility of keeping the low frequencies on the NG VLA. At first, the NG VLA was thought to be something that would only go up to 116 gigahertz, but only down to maybe 8 gigahertz, and certainly not to 1.4 gigahertz. But you know, the sky is full of synchrotron sources that are mostly stronger at lower frequencies. And so I think what Meerkat shows us is that it's essential that we keep the low frequency capability on the NG VLA. And those are my final thoughts on this business. Thank you.
Thank you, Jim, for that wonderful talk. So there are a few questions in the chat box. From Min Yun. Jim, the non-linearity of radio FIR correlation as a function of 1.4 gigahertz luminosity is interesting. one concern is that low luminosity objects are more nearby, and the NVSS is not a great data set for nearby resolved sources. For the IRAS-Tujansky study, we had to dig into old GB single dish measurements. Otherwise, many extended galaxies look underluminous in radio. Did your team look into the effect for the 2-mass NVSS sample?
Yes, I did. I agree that is a problem. Even though the NVSS has extremely low resolution, it's a 45 arc-second beam, and very high surface brightness sensitivity, the nearby galaxies are very extended and have very low surface brightnesses. I don't think that that's the actual explanation, though, because this effect is occurring over luminosity ranges that are much higher. And even if there was a problem with the low luminosity galaxies, it wouldn't really matter to the conversion between radioluminosity and star formation rate density. And then one final point is that since then, we've used Meerkat to study all of the sources south of the equator in the IRAS bright galaxy sample with approximately 20 microjanskis per beam RMS noise. And it turns out that the NVSS photometry is actually remarkably good.
Okay. The next question is from Ron Akers. How do you convince non-radio astronomers that this result is sound? We have no detailed model to explain the radio FIR, and it's very hard now, as in the past, to convince people that BFD works.
Well, I think what we can do is say that we understand the far infrared radio correlation locally, because we get essentially the same answer as the far infrared people do. Remember I said that the local far infrared radio correlation and the radio data came up with a local star formation rate density of 0.0128, and Medow and Dickinson, just using infrared and ultraviolet data, came up with an answer of 0.015, so that's within the errors. I have to admit that I, like Ron, am bothered by the fact that the theoretical background for the far infrared radio correlation is weak. So I have to say right up that we basically assumed that the far infrared radio correlation didn't evolve with time or redshift. And probably the biggest concern with that non-evolution is that you would expect at high redshift that eventually inverse Compton scattering off the microwave background would weaken the radio emission. But the evolution that we discovered actually is a little bit stronger than the far infrared and ultraviolet evolution. That is, if there's some failure in the far infrared radio correlation, it must be in the sense that's opposite of that it makes the radio sources a little bit too strong at the highest redshifts.
Are there any other questions? If not, let's thank Jim once again, and let's move on to the next speaker, who is Bjorn Imons from NRIO. So he'll be talking about cold molecular gas on intergalactic scales.
Yes, thank you. I am Jim. I think, yeah, okay, thanks for stopping the screen share. Okay, can you see this and hear me?
Yes.
Okay, thank you very much. Let me also thank the organizers for this this wonderful conference on the VLA. I'm going to tell you in this talk a bit about cold molecular gas on intergalactic scales and how the current as well as the next generation VLA will provide a very unique window on this aspect of early galaxy formation. And to start with a short introduction, we heard earlier today about the importance of the circumgalactic medium and the fact that at low redshifts, the CGM is rather difficult to see. At high redshifts, we know about these giant Lyman alpha structures. So the Lyman alpha line is very bright at high redshifts. So we know about these large structures of gas. And we know from models that these gas structures must be very important in the evolution of high redshift galaxies. The big problem with both the simulations and the observations is that Lyman alpha only traces gas down to about 10 to the 4 Kelvin. So if you want to know about how these gas structures really relate to the formation of galaxies inside them, you really need to look at the molecular gas at a temperature of 10 to 100 Kelvin, because that gas is the raw fuel for the star formation. There are some technical limitations, though, if you want to trace molecular gas really on large scales of the circumgalactic medium. The first issue is that most millimeter observatories, for example, ALMA, they target the higher transitions of CO at high redshifts. And the higher transitions of CO trace warmer, denser gas. And I think most of you know that CO is the most used tracer for molecular gas overall. But if you want to trace the extended reservoir of gas, including any low density extended component, you really need to go to the lower transition of CO, and especially the ground transition CO120. Another issue is that at millimeter frequencies, and I'm having trouble going to the next slide. Okay. So at millimeter frequencies, it's very easy to resolve out emission, especially at frequencies of ALMA. It's really easy to resolve out emission, even on scales of several kiloparsec. So you need ultra compact array configurations to trace very extended emission. And these are configurations with baselines that are very short, especially in terms of kilo lambda. So also here, you're better off going to the lower transition of CO because you can really get compact array configurations. The VLA is an excellent instrument for targeting the ground transition of CO. Basically, it can target CO throughout the history of the universe, except for the lowest redshifts. And people have done CO120 studies with the VLA for a long time. The big problem was that before the upgrade to the wide-arc correlator at the VLA, the bandwidths were very narrow. So even a continuum bandwidth only had a width of several hundred kilometers per second, which is really not much wider than the lines themselves. And we saw some results earlier today from the old VLA, but it was tricky. Here's some work that you see of one of these massive systems at redshift 4. Some heroic work done by people back in the early 2000s, where they measured line and continuum at the same time and then tried to subtract the continuum with an offset observation. After the WIDAR upgrade, things became much easier. So the WIDAR bandwidth is over 10,000 kilometers at these redshifts. And you can see here, this is an observation of the same target that we did last year. And you can now see that it's much easier to detect these emission lines. You still need a lot of observing time, so you're still a bit limited in sensitivity. And this is where the NG VLA will do a great job at the highest redshifts. Let's go a bit lower in redshift, where you can target the molecular gas in a bit more detail. So this is a spiderweb galaxy at redshift 2. You can see here beautiful HST imaging, which was obtained by George Miley and his team in Leiden. And you see these galaxies here that are surrounded by a giant Lyman alpha halo, and this will turn into one giant central cluster elliptical eventually. If you look carefully in the color image, Nina Hedge in 2008 did a careful study of this, and she actually found that in between the galaxies is this diffuse blue light. So this is actually star formation within the circumgalactic medium itself. So we observed this system with both the VLA and the ATCA, which is the Australia Telescope Compact Array. And we looked for cold molecular gas in the ground transition of CO. And we basically found this enormous reservoir of cold molecular gas on the same scale as where this in situ star formation was found. Also interesting, if you look at the VLA data, mostly taken in C configuration, you see this blob of emission right there where there's the star formation. And basically, if you look in the literature, most studies show this, blobs of CO where you have star formation. But if you go to the ATCA, we saw this enormous reservoir of gas. And the reason is, and you see that on the bottom left plot here, is that you need ultra compact array configurations to trace this emission. The ATCA only has 5 antennas that you can put really close together. And you see that the VLA data is entirely consistent if you taper it heavily enough. Ideally, you would want a VLA in E configuration, because you see that baselines of 100 to 200 meters can really pick up this very extended emission. The gas itself is pretty settled as well. The velocity dispersion is very low compared to that of the galaxies. So this really is this large reservoir of settled gas within the CGM. I told you earlier that this gas is actually forming stars. It follows this in situ star formation, the same kind of morphology. And if you look at the star formation rate and you plot it on the Schmidt-Kennicott relation, then the CGM falls right in there. So this is a large reservoir of gas, likely fueling star formation. And another indication for this is that we have some ALMA data of this system, and I don't have time to go into details. But basically with ALMA, we found also that CO43 as well as atomic carbon was found in the circumgalactic medium. And we managed to do some line ratio work here. So the CGM showed excitation conditions as well as carbon abundances very similar to the ISM and star-forming galaxies. So what we see in the spiderweb is not some diffuse halo. This is really enriched gas on large scales and likely forming stars. Okay, so the spiderweb gave us some interesting results. So we looked at another system. This is Mammoth-1. This is an enormous Lyman alpha halo. And we observe with the VLA the ground transition of CO. And you can see here on the right-hand side that CO was found at several locations within the halo. But when we look carefully, actually half of the emission also here is spread throughout the circumgalactic medium. Now I'm going to zoom in on one of these regions here. So this is a galaxy to the north. You see the channel maps of CO at different velocities. And you can see that half of the CO is locked up within this galaxy, but the other half is stretched in this wide tail of gas. And interestingly, if you look with ALMA, and this is work that was done by Shane Bechtel a few years ago when he was here for an NRAO summer program, and we actually saw that the C1, the atomic carbon, is spread on similar scales as the CO1 to 0. But if you look at the CO4 to 3, you see this bright blob of emission just on top of the galaxy. So this is another indication that you really need to go to these lowest transitions of CO to see the overall gas reservoir at high redshifts. Looking at the core, the story gets even more interesting. Here you see the channel maps of CO in the central region. If you look carefully, the CO actually doesn't really align with the central galaxies. And much like in the spiderweb, it seems to co-align with this diffuse emission in the HST imaging. Most importantly though, if you look at the velocity dispersion of the gas, it's very, very narrow. The full width half max is only 85 kilometers per second. So we believe what we see here is dynamically cold gas in the very core of this protocluster. And if you compare it to ALMA studies of local systems, we wonder if this could be related to cold filaments that people have seen in nearby cool core clusters. So just to summarize what we saw in the spiderweb and the mammoth, we saw that there's a significant fraction of cold molecular gas in the circumgalactic medium. And there's other studies that hint to the same thing. And we see also a variety of physics going on. We see halo gas, we see tidal debris. In other studies, we saw alignments between the jets and the molecular gas. Personally, I have not seen convincing evidence that this is really diffuse molecular halo gas. It looks more like tidal debris and star forming gas in the halo and just on large scales. but there's a lot more research that needs to be done on this. In order to do so, we started a survey called the Supercold CGM survey. So we actually have ALMA data taken in cycle 7 of 10 enormous Lyman alpha nebulae around bright quasars at redshift 2. And we really tried to push ALMA and the ACA to very low resolution. We even tapered the ACA data to get to the results here. And we basically observed CO43 and C1 simultaneously. So this is work that's done by Jerry Lee. He's a PhD student at Tsinghua University in China. And Jerry is working together with Chen Kai and myself. And he's looking at these ALMA data. He very quickly became an expert in really analyzing this sample of ALMA data. And he's finding really interesting results. So again, a variety of systems. Some of the data sets don't show any extended emission in CO or C1. But there's also interesting systems like you see here where the emission is really spread on large scales. So if you look, for example, in the top image, on the left, you see the Lyman alpha. On the right, you see a position velocity plot along the dotted line on the left. And you can see that even the CO43 seems to be spread on a scale of more than 100 kiloparsec. And very interestingly, it seems to be very turbulent gas, much wider profiles than what you typically expect for a galaxy. On the left-hand side, you see another system where you have a central QSO and what looks to be 2 companion galaxies, but the line ratios are all over the place. They're very different for the 3 different systems. And there seems to be gas in between these systems as well. So Jerry is actually hoping to get some VLA data to trace CO1 to 0, both to get extended emission, the very extended component, but also to get line ratios and tell something about the gas physics in these systems. And just to conclude my talk, I'm going to show you a slide about what the next generation VLA can do. Well, the next generation VLA will be a fantastic instrument to take this work to the next level and really study the cold molecular gas on large scales. Most of the antennas in the NGVLA you won't be able to use because you won't be able to get the surface brightness sensitivity. But the NGVLA is going to have a very dense core of antennas, and that will be a very powerful instrument by itself to do this kind of work. And especially if the shortest baselines, about 100 to 200 meter, can be filled up, we'll be able to see all this emission. And this is just a simulation that Chris Corelli did for a chapter in the NGVLA science book that we wrote. You can see here, if you take the intermediate array, the intermediate baselines, you can trace all the CO nicely within the galaxy. But if you look with just the NGVLA core, you should be able to pick up this gas on very large scales. So let me conclude by giving you kind of a provocative statement here. We may be missing a large fraction of the cold molecular gas in the universe. And we know that cold molecular gas plays a crucial role in galaxy evolution. There are some low surface brightness challenges, but the VLA, and especially the next generation VLA, are fantastic instruments to start looking for the full content of the molecular gas in the universe. That's it. If anybody has questions, please let me know.
Thank you, Bjorn. So, are there any questions? You can either put them in the chat or raise your hands. I was just curious about the jet alignment that you had mentioned in your one of your slides. Yes. So how much is, what is the role of jets in
this? Yes, I didn't have time to go into this in any detail in this talk. But for example, if you look in the spider web, if you look carefully at the distribution of the CO, we found that the brightest clumps of CO are found along the radial jet. And interestingly, this is also work that was done by Bitten Goldberg, Carlos de Berg, and Matt Leonard. They looked at water emission in the spider web, and especially in the halo environment. And they also found that water was found along the radio jet, not in the central radio galaxy, but at 2 locations along the jet, in the same region where we find this enhanced CO1 to 0 emission. So this really seems to indicate that the radio jet plays a role in cooling the gas locally. We have other examples that we studied earlier with the ATCA, where we saw these blobs of emission right outside the radio jet. So really aligned with the radio jet, but found just outside of the radio jet. We found, I believe, 3 cases of those. I couldn't show them here, but there is evidence, indications that the jet has something to do with this. And in one of the galaxies that Jerry Lee is currently looking at with ALMA, we see a big outflow and extended emission. I think I included that one here as well. And that's actually the only radio loud system in our sample. It has a radio source, and it seems to be that there are some hints of alignment there, even though the radio source is very, very compact. So there are indications that the radio source is actually pretty important in some of these systems. But I have to say, we mostly selected initially our systems in terms of radio loudness. The first galaxies we looked at were high redshift radio galaxies. So there's some bias there.
Okay.
Yeah.
Interesting. So there is one question. What's the lifetime against photo dissociation in the CGM? Is the molecular gas self-shielding?
Oh, that's a good question. We know actually very little about how the conditions are for the gas there. If this is really star-forming gas, it must to some extent be self-shielding in order to survive. The gas is very settled, for example, in the spider web, so that it must have taken quite a lot of time to settle and cool down. So to some extent that must be going on, but this is something we need to look into in more detail. Good question though.
There is a question by Mignon. Would you like to ask?
Okay, this is more of a history question, but you know, when I finished my PhD 30 years ago and wanted to do something different, some prominent scientists told me, don't bother looking for these starburst galaxies in early universe because there's no metal. And I'm glad they were wrong, but at some point you're gonna have to run into this problem of metal production, and especially on large scales. Because on a small scales, time scale is short, you can produce a lot of metals in a small area, and seeing this out to a redshift 6 or 7 or 8 may not be a problem. But when you talk about hundreds of parsec scales or megaparsec scales, that would require some different explanations. Well, just for us, simplicity, simple questions, how much prior star formation would it require to produce the amount of metals you see in these systems? And is that a trivial amount, or is it something we have to start worrying about?
That's a good question. We haven't done those calculations actually, but that's very interesting to have a look at, because we do think that to a large degree there must be metal enrichment going on in these environments, and especially the systems where you have these radio jets. The fact that we see CO along the jets could really indicate that maybe the metals are even brought out by the radio source. Like some people have shown at low redshifts. I haven't shown that in my talk, but there must be a lot of metal enrichment going on. Same in the spider web. There's a lot of galaxies there. But to what extent that's feasible, that is a very good question. We should definitely do those calculations.
So Ron Akers has a question.
Oh, hi, Bjorn.
Hi, Ron.
The answer you gave is exactly what I was going to say, but I'll just repeat it again. Maybe the role of the jet actually is to take heavy metals out into this pristine medium, because it'll change the situation pretty dramatically, and maybe that's what triggers the star formation.
Yes. Thanks, Ron. And Ron was heavily involved as well in the work that we did in the jets. It's a pity that I couldn't show in this talk, but maybe in the next one.
Okay. Thanks, Bjorn, for that talk. We'll move on to the next talk by Tom Scott. He'll be telling us about galaxy clusters, what we are learning from the cold gas in the late type galaxies.
Can you see the screen okay?
We can see and hear you.
Okay, great. Thank you. Hello, everyone, and thank you, the organisers, very much for the opportunity to present the work that we're doing, looking at cold gas and late-type galaxies in nearby galaxy clusters. The image that you see here is showing the H1 in the Virgo cluster, and this is the most extensive mapping of resolved H1 so far. As well as the very well-known morphology density relation, we also see that there's been an evolution of colour and morphology over fairly short timescales from redshift 0.4 to the current era. And in this time frame, the colour of blue star-forming galaxies has continually declined, and there's a decline in the spiral fraction and a corresponding increase in the S0 fraction over the same time period. So we're seeing here evidence of S0s, spirals being converted to earlier Hubble types by something in the cluster environment. And there's a very nice, so the role of the removal of ISM is very important in this process. And in particular, the H1 deficient fraction of galaxies increases with proximity to cluster cores. And this H1 deficiency is correlated with truncated star-forming disks and dust disks. And there's a very nice cartoon here from Eri Chung, which summarizes the dangers for ISM in the cluster environment. And we can really look at these in two parts: the hydrodynamic mechanisms, of which ram pressure stripping probably works on the shortest time scale. And we also have tidal effects, both from harassment, where we have multiple rapid low impact interactions, and most, I was going to say most, but many galaxies join clusters as parts of groups, and tidal galaxy-galaxy interactions are still possible, and these have higher impact than the harassment. And there's a very nice animation here from Elke Rodiger demonstrating ram pressure stripping, and we see from the right-hand panels that ram pressure increases quite dramatically as the galaxies transit the cluster core. And on the left panel, we see that the galaxy, the ISM, is truncated from the outside in, and some ISM may survive a core transit. And so now I'll look at a few examples of the impact of the cluster environment on the galaxy ISM. And the first one is ISO 137001. And this displays the typical signatures of ram pressure stripping: a one-sided gas tail, unperturbed stellar disk, and is projected within the X-ray emission from the ICM of the cluster. And we see in the inset that in this case, ISO 137001 has a quite spectacular twin X-ray tail. And looking more closer up, HST image with overlays of H alpha in green, and the X-rays are the contours. And we were lucky enough to get ALMA mapping of the molecular gas in the tail. And interestingly, no H1 is detected here. And there's very significant amounts of molecular gas. This galaxy is projected very close to the cluster core. And we also saw star-forming clouds associated with the molecular gas, which generate the stellar streams, which I think you can see in the HST image. And we should also just note that we've just recently heard that collaborators have received time on ALMA to map do a survey of molecular gas in ground pressure stripping tails. Another cluster that we've looked at, and we've done multi-configuration H1 mapping in ABL 1367. And we see down in the bottom left part of the figure, the yellow contours outlining the X-ray emission from the ICM. And two galaxies that are interesting lie just on the northwest edge, and that's 97079 and 97073. And we mapped with HERA a molecular tail in 97079, and we see from the VLA C array, the H1 is quite significantly offset from the center of the galaxy. Now, we were very lucky here that Boselli got some deep H alpha of these two galaxies, and we see two quite long H alpha tails. And what's understood to be happening here is that these two galaxies on their orbits of the cluster core have tidally interacted where the tails meet. This has loosened the ISM, and this has allowed ram pressure stripping to more effectively work. So we have an example here of where two processes, ram pressure and tidal, are working together to strip the ISM. One of the most interesting parts of this, the H1 surveys that we've done, were where we found an extraordinarily long H1 tail out at about the virial radius of the cluster. And you'll notice that this is actually quite distant from the detected ICM, which is shown with the cyan contours. The other interesting thing here is that the bulk of the H1 is actually detected in the tail and not in FGC 1287's disk itself. And it's because this looked like a ram pressure stripping case, we had an XMM pointing at the position of the triplet, but made a non-detection. We also went back to the VLA and asked for high resolution BNC configuration mapping. And we see that the tail is quite clumpy. And in fact, we found 3 star-forming clumps within SFC 3 at 1 and 2. And for the closest clumps, we confirmed that with VMOS that they're at the same redshift as the H1 tail, and that the gas has a metallicity in those clumps, which is consistent with it coming from one or more of the triplet members. We see over on the left, this is a sample of tails in clusters which are attributed to ram pressure. And we see that if we look at the tail length and the normalized distance, FGC 1287 is a significant outlier, both in terms of projected length and distance from the cluster center. So with these properties, you would think if you see this near a cluster core, this might be a classic case of ram pressure stripping. But this is projected over a megaparsec from any detected ICM. And both the beta models and the upper limit for ICM density imply that the ICM is 2 orders of magnitude at least lower than we find near cluster cores. And we saw from the B and C configuration H1 that the disk of FGC 1287 is quite significantly truncated almost down to the optical disk diameter. And we used the disk truncation model to work out the velocity that would be required even at the upper XMM upper limit for ICM. And this is about a factor of 3 higher than the velocity dispersion in groups. So we've looked at a number of possible scenarios to produce this tail, and none of the ones that we've looked at so far are either tidal or ram pressure, including looking at the possibility that the triplet have interacted, and in fact the tail consists of stripped intragroup medium, but none of these really can account satisfactorily for the properties of the tail, particularly the large mass of H1 in the tail. So what we've concluded so far from what other people have done and our own studies is that ram pressure stripping is a viable and observed mechanism close in towards the cluster cores. We also see that a number of galaxies arrive at the cluster already H1 deficient from pre-processing, and that there are a number of cases where tidal and ram pressure operate simultaneously, but we're pretty unclear how common this is so far. We also see in galaxies that are close to the cluster core that the stripped gas can undergo phase conversions. And these are complex environments, and we already know that things like the cluster dynamical state can affect H1 profiles. So what we really need is more resolved H1 and molecular gas and relate that to the response in star formation and the evolution of the galaxies. So thank you very much.
Thank you, Tom. Are there any questions? So yes, one from Fawn. Have you considered interactions with shocks occurring in cluster-cluster mergers for stripping?
In fact, that's a very good point. And one of the things to investigate for that FGC 1287 case is merger shocks. Although we point out that the orientation of the tail is perpendicular to the center of the merging cluster. AOL 1367 is on merging cluster, so merger shocks are very likely.
So there are no more questions. We'll move on to the next speaker because there are no more questions apparently. And the final speaker of the day is Eric Faustino Jimenez Andrade, and he'll be speaking about the VLA Frontier Fields Survey.
So, hi everyone, can you hear me and see my screen?
Yes.
All right. So first of all, thanks for taking the time to listen to my talk, and thanks to the organizer. I know that this is already Friday afternoon and even evening. So yes, my name is Eric Jimenez Andrade, and I'm a postdoc working at the National Radio Astronomy Observatory. And today I will be presenting some results about the VLA frontier field survey that delivers deep, high-resolution radio continuum imaging of the max length clusters at 2 different frequencies. So for this particular project, I have been working in close collaboration with Eric Murphy, Jan Hewitt, and even an NRAO summer student, Crystal Corsi, as well as many other researchers that are listed here. So quite briefly, this is the old note of my talk. First, I will introduce the Hubble frontier fields. I will then try to convince you about the need for deep radio continuum surveys. I will present the VLA frontier fields survey, and then I will describe how we can combine this new data set from the VLA with HST observations in order to study the growth history of galaxies. And finally, the summary and the future work. So the main takeaway from this talk is essentially that this is a public legacy survey. So in case you're interested in using the images and catalogs, please go to this website that we have prepared for you, or send me an email and I will be happy to help you to download the data. So in short, the Hubble frontier fields is an extensive observational campaign to target massive galaxy clusters and parallel fields. The idea is to leverage the power of gravitational lensing to detect galaxies that are either very faint or very high redshifts. And these 6 massive galaxy clusters from the frontier fields have been observed with both space and ground-based telescopes, including HST, Herschel, ALMA, etc. But no deep radio continuum observations have been obtained in the past. And I think that Jim and Jackie already answered this question, why do we need deep radio continuum surveys? So let me just briefly summarize here. So as you remember, here in the y-axis, we have a star formation rate density, that is the amount of stars that are being produced per year per commoding volume as a function of redshift or cosmic time. And what we have seen is that we have a contribution from unobscured star formation that we can measure from the UV. And also we have the contribution from those obscured star formation that can be traced by infrared and radio observations. But as you can see here, the contribution, I mean, most of the star formation in galaxies remains obscured by dose of the redshift 4 to 5. So in order to study the distribution of star formation activity in galaxies on kiloparsec scales, we need radio interferometric observations, because those are the ones that allow us to get high angular resolution, and also we can penetrate into the dose obscured regions of star formation. As you know, we can use a VLA and ALMA, but perhaps one of the main advantages of the VLA is its large field of view, so that we can carry out deep radio continuum surveys, so that we can assemble large compilations of galaxies at high redshifts. So this was one of the motivations behind the VLA frontier field survey that was led by Eric Murphy. So in summary, we obtained 3 and 6 GHz imaging of 3 of the 6 out of the 6 frontier fields. So max 0416, max 0717, and max 1149. So these are massive clusters around redshift of 0.5. Here you can see the spatial coverage of these images at 3, 6 GHz, and also for comparison, you can see the footprint of available HST imaging that actually has been recently expanded by a factor of 4 with the Buffalo survey. But coming back to the radio images, we are reaching an RMS of around 1 microyansky per beam, a resolution of 0.6 arcseconds. So this is one of the deepest and sharpest extragalactic radio surveys, which combined with the power of gravitational lensing allow us to trace star formation activity in distant galaxies without being affected by dust obscuration. Some general properties about the catalogs. So we are reporting maybe 2,000 compact radio components. Around 70% of them have an optical counterpart. They span between redshift 0 to 5, and a median redshift of 1, and a median magnification factor of 1.2. We also have some strongly lensed galaxies with magnification factor above 2. Here you can see 2 examples of them. We also have some extended and complex radio sources. They mostly lie below redshift 1. These are essentially FR1, FR2 radio galaxies, radio halos and relics, and also low redshift disk galaxies. I would like to mention some interesting sources in the catalog. So, as I mentioned before, the goal of the frontier field survey is to study the galaxies that are at high redshift, but also we can study the clusters themselves. And with 1 microjansky per beam sensitivity and super second resolutions, the images that we're obtaining towards MAX 0717 and MAX 1149 are actually one of the deepest and sharpest radio images ever obtained towards a radio relic and halo. And in particular for MAX 0717, we also obtained 10 GHz imaging. So I should stress that this is one of the very few radio relics that has been detected at such high frequencies, which now combined with 3 and 6 GHz imaging will allow us to study the acceleration mechanisms of cosmic ray electrons in clusters. Another interesting source is this low mass star-forming galaxy at redshift 1.1. In the background, we have an RGB image of the HST, and the contours show the VLA emission at 3 GHz. So its magnification factor of around 6.5 allowed us to detect it with a peak, intrinsic peak brightness of 0.9 microjansky per beam, which makes this one of the faintest radio source detected today. In general, this finding demonstrates the advantage of combining gravitational lensing with deep radio continuum surveys in order to study the faint population of radio sources in the unexplored sub-microjansky regime. So in general, here I will show you the description of the catalog, the data products that we're offering. So as I mentioned before, you can go to this website that looks like this, and there you can find a description of the project, the publications, and of course the data that comprise the images at 3 and 6 GHz at 2 different frequencies, different resolutions. We also have the catalogs that contain information of the optical host, including the redshift and magnification factor. Also, we have spectral indices and radio sizes. Now, in the final minutes of my talk in the conference, I would like to describe the science that we can do by combining this new VLA data set with extensive imaging of from the HST. So one of the things we can do is to investigate the growth history of galaxies by comparing the morphology in the red range UV, in the optical, and in the radio of these massive galaxies that span over this redshift range between 0.3 to 3. So the idea is here to compare the size of the stellar disk that is traced by the optical with respect to the extent of star formation that is being traced by the radio continuum emission. And by making this comparison, we can address this question. So where do new stars preferentially form in galaxies? Here I'm showing you the effective radius as a function of the redshift, effective radius or half-life radius. So we have the size evolution measured from the UV, the optical, and in black we have the radio, and in gray we have the constraints at low redshift from 6 GHz emission. And the first result that we find here is that the trends that we derive from this radio-selected sample agree well with the previously reported redshift evolution using mass-complete samples of galaxies, and the same for the radio. So we can take this sample as representative of the total population of massive galaxies with a stellar mass about 10 to the 10. The second result here is that I should stress that in this study, we are making for the first time a systematic comparison of the multi-frequency or multi-wavelength structure of galaxies at high redshift. So we simultaneously measure the radio, UV, and optical size, and what we find is that they grow at a similar rate. So the size increased by a factor of 1.5 to 2 from redshift, going from 3 to 0.3. another important result is that the optical emission appears to be more extended than that from the radio, which suggests that massive star-forming galaxies tend to harbor centrally enhanced star formation activity, which could be contributing to the growth of a galactic bulge. But of course, there are some systematics that we need to explore. For example, the obscuration that might affect the way that we measure the UV and optical sizes, and also differential cosmic ray electron propagation in the radio. So these are the two open issues that we need to address in this field of galaxy evolution. So finally, this is the summary of my talk. As I mentioned before, the main takeaway is that I have presented a public legacy survey, the VLA frontier fields, so that all the images and catalogs are available at this website. This contains radio continuum images at 2 frequencies of 3 frontier fields, max 0416, max 0717, and max 1149. We currently have a catalog of 2,000 compact radio sources. They contain information about the magnification, the spectral indices, and radio sizes. And for the future, so we are planning to complete the VLA frontier field survey by observing these two Abel clusters that are visible also to ALMA and to the BLT and MUSE, so that these two are perhaps the two most heavily studied frontier fields out of the 6. We will be also working on the polarization products. So in case you're open to collaborate or you're interested in this data set, please let us know, and we are welcoming any potential collaboration with all of you. I will stop here, and thank you very much for bearing with me for the last 15 minutes. Thank you.
Thanks, Eric. Are there any questions? You can either put them in the chat or raise your hand. I'll ask one. So you mentioned about the radio sizes are smaller than the optical sizes. Could that be because of sensitivity limitations if you go deeper?
Yeah, I mean, the way that we are measuring the size is by measuring the half-life radius. So indeed, what we are looking is that if we go deeper, we will retrieve the very diffuse emission that is in the outskirts, but will not significantly change the effective radius, the half-life radius.
Okay. Okay, we could probably continue this on Slack. So the session comes to an end with that talk. I would like to thank all the speakers for sticking to time. And now I would like to hand over this to Anna.
Okay, Frank, please come in.
Okay, yeah, so I'll actually say the final words of the meeting. So thank you for staying all the way to the end. For those that are still online, we had a fully packed program and showcasing all the wide ranges of the VLA, the great VLA science that has been done over the last more than 40 years, and I hope it will continue like that, at least for the foreseeable future. And so I would like to say, well, first of all, I would like to say thank you, and the meeting has shown that there's a strong community that has been supporting the VLA over the last 40 years, and without that community, the VLA wouldn't have been around for that long. So I think that's quite a remarkable achievement by the community, and I would like to thank all the speakers, everybody who has contributed to the last 3 days, and especially also the session chairs to keep us on track and on schedule. And I would also thanking, I mean, I was the co-chair of the SOC, so I'm also thanking the other SOC members for helping setting up the science program of the meeting. Originally, we were planning for an in-person meeting, and now we ended up on Zoom here, and this was hopefully a great experience despite the circumstances. And I want to give really special thanks to Anna about organizing and dealing with all the logistics and running the meeting. And so really, really great thank you for making this a successful meeting. I also would like to acknowledge the support that we had from other NRAO staff, like Laurie Appel is always helping with logistics in the background, and also especially this time in this virtual environment, we had the EPO team help with the live streaming and tweeting about the event. And I would like to remind everyone also about the public event. This is not completely over yet. There's the public event tomorrow, organized by EPO, and also the EPO shop that has been advertised for the participants of this meeting. Just a few more words about so Anna sent around an email about the talk recordings. They will be made public and probably earliest next week. We'll see them posted online, but in the meanwhile, any slides that we have available will be posted online over the course of the next week. And also the scrapbook, we will keep that open for probably another week until next Friday. And so if you want to contribute some more things to it, we'll try to make sure that there's some pages that remain blank for people to contribute, because this Google Jamboard only allows up to 20 pages. So we'll try to keep that in mind. And yeah, and then we'll probably freeze it and post it as a PDF on the conference webpage. And also, as a reminder, the Slack workspace will stay where it is for the foreseeable future. So if participants still want to continue interacting through Slack, that possibility is given even after we conclude now. So I have spoken my final words, and I think this was a great meeting, and I'm looking forward to the future and hopefully more great science from the VLA and leading us into the NG-VLA era. Thank you, everyone.
Thanks to all.
I should say see you all at some conferences sometime soon, hopefully, fingers crossed, right?
Yes.
Right. Hopefully we'll be able to have a VLA conference.
Yeah.
Hey, that would be nice. I need more green chili.
Yeah.
It'll be with the NG VLA probably.
Yeah, Tracy missed her summer visit.
I know. I didn't restock. Didn't get VLA fixed. Take care, all. Thanks. Bye.
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 Where's the after party?
I'm going home and I'm falling asleep. Honestly. Oh, hang on. I should actually stop the